In this course, I don't want to limit you to just one language, because we all code in different languages, and throughout your career, you're most likely going to use multiple languages. Now, this course specifically, I will have to use a language to demonstrate code and write some code. And I'm going to use JavaScript for this because it is similar with a lot of common languages, and it's also the most well-known. However, you can use whatever language you want in this course and follow along. Even the exercises will give you solutions in different languages. So pick whichever one you want. But how are we going to run all these different languages when you're following along? Maybe I'm demonstrating something in JavaScript and you're coding along in Python. Well, we're going to use a couple of neat little online tools. The first one I'm going to show you, and the one we're going to use in this course, is REPL.it. REPL.it, as I like to call it. And you can pick any language that you want here to code along. And like I said, I'm going to be using JavaScript for this course. But all you need to do is to sign up with your GitHub account, and you'll have a little IDE that you can run your code in. And you'll see me using this throughout the course. Another one that I really like is glot.io. And it's open source, which I'm a big fan of. And you can see over here that we have a lot of different languages that we can use. Again, if I go to JavaScript, it gives me a nice little area for me to write code and run it. Another option, especially if you're using JavaScript, is to just go to View, Developer, and Developer Tools in Google Chrome. And this allows you in the Console tab to just write JavaScript. So that's another great option. Or if you prefer, you can always use your favorite text editor, write your code, and then run it whichever way you want. Again, keeping in mind that this course is language agnostic. That means it doesn't matter what language you use. What we're learning are foundational computer science principles that you can take anywhere throughout your career. And as you'll see, whether you know JavaScript or not, I'm going to keep the code very general and simple so that it's easy to replicate it into other languages, and also give you resources and sources with other languages when we get into more nitty-gritty coding. All right, set up your environment, get ready for some code. I'll see you in the next video. Bye-bye. In my opinion, this section is one of the most important topics for any software developer or engineer. It also happens to be my favorite section of this course. No matter what company you work in, where you live, or even if you're coding 10 years from now, this is a concept that will be around for a long time, and something that will truly make you a better developer. Big O is something that I learned about 2 to 3 years into my career as a developer, and it's so important. It has made me a better developer, a better engineer, and it will for you as well. Big companies like Google, Facebook, Alibaba, Amazon all know this, which is why you won't get by any of their interviews, any of their phone interviews, any of their screening interviews without encountering this topic. So we're going to learn all about this very important topic, and that's why it's at the beginning of the course. All right, did I grab your attention enough? So what are we talking about here? It's called Big O, and the official term is Big O asymptotic analysis, if you want to sound super smart and impress your friends. You see, any coder, given enough time, can solve a problem. What matters is, though, how well the problem is solved. And this is where Big O can help us. It can tell us how well a problem is solved. We're going to find out about what that means in this section. We're going to talk about Big O, what it is, how we define it, and then we're going to use Big O and its different notation to distinguish bad code from good code from great code. We are going to become comfortable with this topic, that we are going to not be surprised when this comes up in our interviews. But we are also going to build this big foundation that is important to be a great developer. The reason this topic is at the beginning of this course is that you will see this big O notation come up again and again as we go into topics such as data structures and algorithms. Like I said, this is my favorite section, so get ready because it's going to be a lot of fun. See you in the next video. Bye-bye. There are two main things we talk about when we say this is good code. But before I show you, what do you think good code is? Think about that. What would you tell somebody if you're asking them to write good code? All right, I'll just give you the answer. You see, good code can be described in two things, or 2 points. One is readability. Is your code just generally clean? Can others understand your code? And then we have scalable code. What does that mean? Well, big O notation is what allows us to measure this idea of scalable code that can scale. Something that we're going to get into and you're going to become more familiar with as we go through this section. We're also going to talk about readable code throughout this entire course, but touch upon it a little bit more in the next section. But for now, because this is the big O section, we're focusing on this idea of scalable code. Okay, what does this really mean though? Well, I want you to imagine we have a task where we want to bake a cake. We have a recipe over here, and this recipe we're going to use in our kitchen to bake a cake. And there's a good way of baking a cake and a bad way, right? We give it the instructions, that is the recipe, and hopefully this recipe and instructions work well with our kitchen so that we can bake a cake quickly, and a good cake at that. Well, computers are machines, and these machines need to work in order to produce something for us. And computers work in the same way. We have these instructions that we give it through code, and these instructions that we give to our machines, our computers, give these instructions that provide for us some sort of an output. For example, to turn on the light. We give the computer instruction to say, hey, turn on the light in our room. A coder is someone that gives these instructions. Just like there are many ways to take a cake into a kitchen, or just like there are many ways to bake a cake in the kitchen, with many recipes, ingredients, and instructions, there are many ways to solve a problem through code. There are efficient and inefficient ways to give instructions. So let's go to a coding example. I'm going to use REPL.in, and if you're not familiar with this, make sure you check out the video that I've listed down below here, which explains how you can run your code in this course. I'm going to just log in, and I already have my JavaScript environment set up over here. And I prefer having the dark theme. I think that looks better on your eyes. For you at least, I hope you don't mind the darkness. But how can I demonstrate this idea of code? Let's do something fun here. Using JavaScript, I'm going to say const Nemo. We have an array that contains the string Nemo. And we want to create a function here that is called find Nemo. And this function is going to receive an array. And it's going to be a very simple function. We're going to create a loop that you'll see in most languages. In JavaScript, we can do that easily by saying for, and we'll give let I equals 0. And as long as I is smaller than the array.length, that is the length of our array, and then we're going to increment I every time. Again, this isn't a JavaScript course, so hopefully this is familiar to you. Any sort of loop that you want in your language. And we're just going to simply say that if array I equals Nemo. So if we find Nemo, we're just going to console.log found Nemo. We're very excited we found it. All right, that's it. And if I just simply run the function now, find Nemo, and we'll just give it the array Nemo over here, and make sure that I spell length properly, and we click run here, we have found Nemo on the right. Let me make this a little bit bigger so you can see. So we found Nemo. This is the instruction that we gave the computer. We told it that we have an array and we have a function, an action that we want to perform called find Nemo that takes an array, which is Nemo. It's going to receive this array. Then it's going to loop over the array. We're going to say that I is going to equal 0. And because I is 0 right now and the array.length of Nemo is 1, we're going to go through the loop. We're going to check if array index of 0, which is Nemo over here. So this is going to turn into Nemo. And because this is true, we're going to console log found Nemo. Now, why did I just show you this example? Let me just bring this back to the way it was. I showed you this example because this is an instruction that we're giving our computer to find Nemo. You see, we call this the runtime. How long does it take to run a certain problem through a function or a task? How can we measure the big O of something like this, or the efficiency of this code? In the next video, we're going to get a little bit deeper. We're going to try and measure the performance of this code and see what happens when the array gets larger and larger. And we're going to tie things together as to what scalable means and how big O allows us to measure this scalability. See you in the next video. Bye-bye. Welcome back. Let's continue our discussion of what this scalable idea means. You remember that we talked about the kitchen and how, similar to a kitchen, we have to give instructions to our machines to produce a result. And in the previous video, we talked about this function, finding Nemo. Let's measure the performance of this function. Well, JavaScript gives us a nifty little tool that comes built in to the browser, which is where we're running this code. So depending on your language, you might not have this option, but you will have different ways of measuring this. Don't get too hung up on this. We want to use this as an example to measure how long it takes for this function to run. We can do this in JavaScript by saying, let's say time 0 is going to equal performance that comes built in to the browser. And we just say now. And this T0 is going to start this timer before the loop happens. And then when the loop ends, I'm going to have another timer called T1. And this is going to equal performance.now. So we have two timers, one at the beginning, one at the end after the function goes through the loop to find Nemo. And then at the end, we'll just do a fun little console.log, and we'll say that the call to find Nemo took, and we can just do a simple T1 minus T0, and then we'll say milliseconds, because it's going to give us the results in milliseconds. Let's see if this works. I'm going to run this code. And let me add a space in here. And we see that it took 0 milliseconds for this code to run. Let me run that again. 0 seconds, again, 0 seconds, 0 seconds. And if I keep clicking it, I see that, oh, now it takes a little bit longer. And that's because this is really fast, right? Our computers, machines are extremely fast in this day and age. And because we're only looping through this once, well, it takes almost 0 milliseconds. And the display just rounds this down. But what if we had a bigger array? Let's say that we have an array over here that has const everyone, and it has all the characters, or at least a lot of the characters from the movie Finding Nemo, which, if you haven't watched it, amazing movie, highly recommend it. Anyway, we see that we have a lot more characters now. So instead of just having a single array, let's have the array everyone in here. And this array now has a lot more items. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 loops in here that we're going to do. If we run this, we see that the time is still the same, pretty much 0 milliseconds, sometimes a little bit more, and the time changes all the time. But we don't see that much of a difference, do we? I mean, we went from 1 loop to now 10 loops, but it's still super, super fast. And again, that's because our computers in this day and age are quite fast. The difference between 1 loop and 10 loops is not that big. But let's do a little fun trick here. In JavaScript, we can create a large array. Let's just call it large. And we can create a massive array by just saying new array. And we'll give it 100 items. And this 100 items in the array, we can fill it with, let's say, Nemo. And this is just going to create an array that has Nemo 100 times. So instead of everyone, let's do large and hit run. All right, we see here that it's found Nemo 100 times because, well, we just filled it with Nemo. And at the bottom, we see that it took 0.5 milliseconds. That took a lot longer, didn't it? Let's do even bigger. Let's do 1,000. Hit run. It took 7 milliseconds now. What if we do even bigger? What if we had a massive array of 10,000? If we hit run, 46 milliseconds. It's still pretty fast. And then just for fun, one more. If I hit run, you saw that delay and how long that took. That took 343 milliseconds, or 3.4 seconds. Now, what do we just see here? Well, we see that as our input grew, our function, find Nemo, became slower and slower and slower. Our runtime, how long it takes to run a certain problem through a function, increased. But here's the problem here. If you take this code and run it on your computer, well, your time is going to be different than mine. And I'll leave this code at the end of this video so you can play around with it. You're going to get frustrated because every time you run this code is going to be different than my number. It might be a lot faster or a lot slower. You see, this all depends on how powerful the CPU in the computer is and what other programs are running on your computer, what programming languages you're using, and many other factors. So there's all these factors that play here in our runtime. Therefore, if I speak to my friend across the world, let's call him Johnny, and if I tell him, hey Johnny, my code is so amazing, I've created this find Nemo function and it runs in 3 seconds, 3.2 seconds with 100,000 inputs. How good of a coder am I? And then Johnny says, that's really awesome, but you know what? Mine runs a lot faster. It runs in 1.5 seconds. So I win. What do you think? Do you think Johnny wins? Does Johnny have better code than I do? Well, here's the thing. Not necessarily. This doesn't really mean much. Because it matters what type of computer Johnny has, what other factors, as I mentioned before, the code is running in. So how can we determine who wins? Do I win or does Johnny win? Who has better code? And this is very common in the computing world. We code on our laptops, our computers, but that code doesn't necessarily run on those devices. If we have something like a server, we may have that code run somewhere else on a different computer around the world. So how can we make sure that there's a way for us to measure, in terms of efficiency, what is good code and what is bad code? And what is code that can scale, that as the number of arrays or inputs increases, it doesn't constantly slow down more and more. Big O notation is the language we use for talking about how long an algorithm takes to run. We can compare two different algorithms, or in this case functions, using big O and say which one is better than the other when it comes to scale, regardless of our computer differences. And we can measure big O like this. I'm going to warn you that this will look really confusing at first, and this is the first time we're seeing this diagram. And don't worry, by the end of this section, this is going to make sense and you're going to be completely fluent in this. So just trust me in this. Keep following these videos. I know I'm kind of circling around the topic and not being direct as to what it means, but I promise you, by the end of this, this is all going to make sense and you're going to be a big O ninja. When we talk about big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm or function slow down? If the list of characters, let's say elements here, so that is Nemo, so characters in Finding Nemo in our array, as that increases, how many more operations do we have to do? That's all it is. This is what we call algorithmic efficiency. Big O allows us to explain this concept. Remember how in our function we initially had an array of just one, which was Nemo? So that is the number of elements, number of inputs in a function. It was right here. But then as we increased that array to have more characters, and then we created that massive array of 100,000. So as that increases, you saw that the number of operations or the number of things we do in the loop increased over and over. And different functions have different big O complexities. That is, these number of operations can increase really, really fast, like this one, which is not good. You can see here that it's horrible. And things that are quite good, actually, and don't increase as much. And we're going to look at examples of different ones and how to actually measure this and what this entire notation means. But to end this video, so we can dive deeper into the topic, just remember this point. When we talk about big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm slow down? The less it slows down or the slower it slows down, the better it is. So instead of using performance.now and using time to measure the efficiency of our function, we can just calculate how many operations a computer has to perform, because each operation takes time on a computer. So big O allows us and concerns us with how many steps it takes in a function. All right, let's dig in deeper and deeper into this topic. I'll see you in the next video. Bye-bye. What would you say if I asked you, what is the big O of the function Finding Nemo? Well, to make this a little bit cleaner, let's just remove performance.now because we've learned that it's not very, very important. And we can remove the console log as well. And looking at this and this loop, what would you say the big O is? In this video, we're going to learn about our very first big O notation. As we said, a runtime is simply how long something takes to run. How does this function and its runtime grow as our input increases? As our input goes from just a single item in an array, Nemo, to 10 items in an array, to 100,000. How does the efficiency of this function increase? If we look at this graph and we say we have 4 items in the array, well, the number of operations is going to be 4, right? Because we're going to loop through each item and say, is this Nemo? Is this Nemo? Is this Nemo? Is this Nemo? 4 times. No matter what, we're looping 4 times, at least with the way that we have this code set up. If we have 5 items in the array, it's going to be 5 operations, 5 loops. 6 is the same, 6 items is 6 operations, 7 is 7 operations, and 8 is 8 operations. Do we see a little bit of a pattern here? Well, we can draw a line through it. This is linear, right? As our number of inputs increase, the number of operations increase as well. And here, ladies and gentlemen, we've learned our very first big O notation. We say that the Finding Nemo function has a big O notation of O n. That's a little bit strange. This is just a notation that you have to get used to. But we say big O of n, or what we call linear time. It takes linear time to find Nemo. Now, where does this n come from? This n can be anything, really. I could put x, I could put fish in here if I want. It's just an arbitrary letter, and we usually give n when it comes to big O. This is just a standard that you'll see across the board. N simply means the big O depends on the number of inputs, the number of fish. So if we just had the Nemo array, this would just be 1. If we had the everyone array, this would be 10. And if we had the large array, it'll be 100,000. But as the inputs increase, you see that the number of operations increase linearly with it. ON is probably the most common big O notation you'll find. If we go back to the graph, you can see that ON is right here in the yellow region that says fair. As the number of elements increase, you see that it's just a straight line. The number of operations increases by the same amount. Because keep this in mind, big O doesn't measure things in seconds. Instead, we're focusing on how quickly our runtime grows. We simply do this by using the size of the input, which we call n, or anything else that we want really, and compare it to the number of operations that increase. That's what scalability means. As things grow larger and larger, does it scale? So the Find Nemo function is O of n, linear time. Another way to think about it is this. If we had a compression algorithm, let's say this function is this little compression, and the input is this little box. What's the big O notation of this function? Well, if we had one element, it will just compress one item. If we had multiple elements, again, we still have to run each box through the compression algorithm to compress the box. If we look at the function for the compress boxes, well, we're using the ES5 and ES6 syntax here, but we're essentially looping through each box. And in our case, we're just console logging it. But you can see here that all of these, all we're doing as the input increases, the number of boxes increases, the number of operations increase. And that is ON, linear time. Congratulations, you just learned your first big O notation. And this is probably the most common. But there's a few others. So, what other big O notations do we have other than linear time? For that, you're going to have to keep watching. I'll see you in the next video. Bye-bye. Welcome back. We just learned our first notation, O of n, or linear time. And we see here that we have a few others remaining. So let's talk about the next one. Another very common big O notation that you're going to see. What happens if we have a function like this? A function that says compressed first box that receives an array of boxes. And this function simply has console.log boxes 0. So that is, it's logging out just the first item in the box. What would you say the big O of this function is. How many steps or operations does this function take if the boxes increase from 0 to maybe 10, to maybe 100, to 100,000? What would happen here? Ready for the answer? Well, this is what we call constant time. It's an O of 1. That is, no matter how many times the boxes increase here, or however many boxes we have, we're always just grabbing the first item in the array. If we look at this with an example, if we had an array of boxes here, and we run it through the function that just takes the first item in the array, well, the number of operations is 1. No matter how big the number of boxes are, we're only doing one thing. So it's a constant time. If we look at this on a graph, if we have one element or one box, we do one operation. If we have 3, again, we still do just one because we're just grabbing the first item in the array. If we have, let's say, 5, same thing. 7, same thing. And what about 9? Again, same number of operation. And this is, I don't know if you can see the line, but this is just constant time. It's not linear time like it was, where it increases and increases with the number of operations. The number of operations just stays flat. But I have a question here. What if we do something different? What if we do something like this? What if we have a function that says function grab or log first 2 boxes. And this takes an array of boxes and is going to console.log the first item in the array. And it's going to console.log also the second item in the array. How do we measure the big O of this function? Well, let me just comment this out for a second because we don't need this right now. And just create an array called boxes. And this boxes has, let's just say 0, 1, 2, 3, 4, and 5. So 5 items, or 6 in this case because we include 0. And if we run this function, log first 2 boxes, and we give it the boxes array, and we click run here, we have 0 and 1. So we've logged this one and then this one. What's the number of operations here? Well, we have O of 1, that is one operation here, and then we have over here O of 1 again. Each time, this function runs 2 operations. So this function in total is actually running O of 2 operations every time. So no matter how big the boxes get, the number of operations here is going to be 2. If we look at this on a graph, instead of having O of 1 like we had before, we have O of 2. And then if we had 3 operations, it'll just be O of 3. But overall, it's still a flat line. And this is something we're going to get into later on. But when it comes to constant time, we don't care about the nitty-gritty O of 1, O of 2, O of 3, O of even 100. We round this down to just simply saying O of 1. That is, we have constant time. It's a flat line. In terms of scalability, it doesn't matter how big our inputs are. We're always going to do the constant amount of time on a function. And if we look at this on a graph, we see that O of 1 over here is the dark green area. It's excellent. We love O of 1 because it's very scalable, right? It doesn't matter how many elements we have, it's always going to run the same. Predictability when it comes to computing is very, very nice. And O of 1 is definitely excellent. Okay, so we've learned about linear time, O of n, and then constant time, O of 1. Let's do a bit of a fun exercise to really solidify our knowledge here. Welcome back. How much did you hate me after doing this challenge? Now, this was specifically supposed to be hard and difficult and frustrating, and most likely you're not going to get right the first time around. This was done on purpose to illustrate a point. What we're actually doing here, well, you won't be asked to do in an interview. But I wanted to show you how to think about things because later on, I'll show you how it's actually a lot simpler than thinking about each individual step in a function to calculate things. There's not much math involved, and this is as mathy as we're going to get in this course. But again, I just want to show you the nitty-gritty details so that you can think about it and have a nice foundation so that moving forward, we can simplify things a lot better. Now, let's look at this function. It's the fun challenge function that takes some sort of an input. The very first thing is within this function, when we run the fun challenge, let's just say we'll have fun challenge and we run this function and the input doesn't really matter. It could be an array, it could be an object. For now, let's just keep things simple, say it's an array of 5. Now, when we run this function, the first thing we're going to do is an assignment. We're going to assign variable a as 10. Now, based on convention, and this is why you won't encounter this in an interview because a lot of people interpret this differently. Some people say that assignment you shouldn't count towards big O, and some people say that you should. In our case, just to simplify things, let's count every single step and what the function is doing. Let a equals 10 is just O of 1 because this is only running once when we run fun challenge. That's it. It doesn't matter how big the input is. This just runs once. And then 50 plus 3, we're reassigning a. This, once again, is O of 1. And then we get into a loop. We know that with the loop, it looks like we're looking at the length of the input and looping over depending on whatever the input is. In our case, this is going to be an O of n. Let's add that comment over here. And this n is the input. Remember that I can change this to input, I can change this to x, it doesn't really matter. It just reflects how big the input is. That's how long this for loop is going to take. And we know this by now that loops are linear time. And then within here, another function. We don't know what this function is, but it's calling to another function outside of the fun challenge function. This is also being called how many times? Well, it depends on how big our input is. So once again, it's O of n. What about this? Let variable stranger equal to true. Again, another random assignment here, but this runs as many times as this loop happens. If input was 5, this will run 5 times. So again, this will be O of n. And then over here we have a++, which in JavaScript simply means a plus 1. So we're just incrementing the whatever the number a is at this time. So 53 will become 54. And then as we loop through it, it'll keep increasing by 1. 54, 55, 56. This, once again, runs O of n times. It depends how many times it runs by the input because, again, we're looping through it. And then finally, another thing that some people don't count, but just to keep it consistent, every single step that we do, return A. This runs just once. Every time fun challenge gets run, the return statement only runs once. All right, so we have all these big O notation. And now we're starting to think about how a function runs and how efficient a function is. If we actually calculate all of these, If we total all these up, we see that we have 1, 2, 3. So we have 3 steps plus O of n, O of n, O of n, O of n. So that means we have n plus n plus n. So that means we are running the calculation n plus n plus n plus n, which turns out to be 4n. So 3 plus 4n is our big O notation. There it is. Like I said before, when it comes to big O, don't get too hung up on, did I get this right? Because in an interview, you're not going to need to know this. But you are able to now think about how a function runs more deeply than just simply writing the code. As we progress through the videos, you're going to find out that this actually, at the end of the day, gets simplified to just O of n. And we're going to go through that and why that is. Now that we have a better understanding of how to calculate big O, let's look at another exercise that should be a little bit easier than the first one that we did. What would you say that the big O of this is? Well, if we go one by one, we see here that we have O of 1, again, O of 1. And you know what? If I keep typing this is going to get tiresome, so I'm just going to copy and paste. So O of 1 here, we're just assigning variables. And then we also see here that we have a for loop that is running based on the input. We don't know what that input is, but we can just assume that we're looping based on however long this input is. In which case, we're running each one of these O of n times, or whatever long the input is. So again, these are going to be run O of n and O of n times. And if we go down here, again, same thing. We don't know what the input is, but these are being run O of n times. And then finally, this last line is just run once. So it'll be O of 1. So looking at this function, another fun challenge function, we see that our O of n, our big O, is 1, 2, 3, 4. So we have 4 plus, because we're just adding up the steps here, we have O of n that's happening 1, 2, 3, 4, 5. So 5n. So the big O here is we have 4 constant times, and then 5 things that we're doing n times, or however long the input is. All right, that wasn't so bad, was it, compared to the first time around? I think you're starting to get the hang of this. So let's dive into the next video. Let's start to figure out how we can simplify things for us so that we're not doing this mathematical step-by-step count. I'll see you in the next video. Bye-bye. Welcome back. Now, in the previous exercise and the exercise we just did, we see that we had to do a bit of calculation. It was kind of annoying where we had to add things up and have this, plus 5n plus 4. In interviews, you're never going to do this. And you're asking yourself, Andre, why did you just teach me this? And you're right. But now you at least understand how big O gets calculated. But most of the time, when you go into interviews, there's these set of rules that you're going to follow, where you don't need to do this, and you can just take a look at this function and immediately say what type of big O it is. For example, this function actually just turns into O of n. This function, again, turns into just O of n. And this is a nifty little trick. When we talk about big O, in interviews, most of the time, you're only going to give one of these answers. You're most likely never going to actually calculate precisely O of 3n or of 3n plus 2 plus 1. So how was I able to simplify our exercises and just say that they're ON? And luckily for you, there are just several rules that we can follow when it comes to big O. And there's only 4 of them. By following these 4 rules, instead of doing those small little calculations that we've been doing up until this moment, you can just simplify your life so that big O becomes really, really easy to calculate. Let's tackle the first one. That is rule number 1, worst case. Let's talk about that in the next video. Welcome back. Let's talk about the very first rule when it comes to big O. That is worst case. When calculating big O, we always think about the worst case. What do I mean by that? Well, if we go back to Finding Nemo example. In the Find Nemo function, you may have been screaming at me while I was going through the function saying that, Andre, this is not efficient. What are you doing? Because if you look at this function, we're looping through the entire array to find Nemo. Remember how we had the everyone array with about 10 different characters from Finding Nemo? Well, Nemo was only the 1, 2, 3, 4th member on this array. And when we run this function, we found Nemo. But the funny thing is, this function ran 10 times, not 4 times. If I do a console log here, and I say running, and let's click this, we see that this function ran 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, we already found Nemo. All these runs are pretty wasteful. So we can make this function a little bit more efficient. In JavaScript, we can just have something called break. And again, different languages have different ways of exiting out of a loop if a condition is met. In our case, if we find Nemo, just break out of this loop. If I do this and click run, look at that. Once we found Nemo, we're done. We're not going to loop through the rest of the items. Congratulations, we just made our code a little bit more efficient. That's a good thing, right? Well, when it comes to big O, although this is important, and when you write good code, this is something that we want to do. In the big scheme of things, big O only cares about the worst case. What is the worst case here? Well, the worst case is that Nemo, instead of being the 4th item, is at the very end. So even if we have this break statement, we're still going to run this 10 times because Nemo at the end. Best case is if Nemo's at the very beginning and we only have to loop through it once. But worst case, we're still going to have to go through 10 loops. Still big O of n. So this is our very first rule. The very first rule is we always care about what is the worst case scenario, because when we talk about scalability, we can't just assume things are going well. Even though the find Nemo function might be O of 1 if Nemo is the very first item in the array, it doesn't matter. In the grand scheme of things, because we can't be certain of what the input is going to be, we're going to assume that O of big O is O of n, linear time. Again, if we're finding a yellow box and the yellow box is at the very end, we have to iterate through all the boxes. If the yellow box is at the very beginning, you see that we don't have to iterate through these boxes. But big O doesn't really care. Even though this function, yes, is indeed more efficient, at the end of the day, when we talk about big O, we're talking about worst case. All right, I hope you got that point through. I feel like I've beaten it to a pulp, so you should be comfortable with it by now. Let's talk about the next rule in the next video. Welcome back. Let's look at rule number 2. That is, remove constants. Let's see what I mean. I've written here the most ridiculous function ever. The function is print first item, then first half, then say hi 100 times. Probably not the best named function ever, but as the name describes, all we're doing is we're going to console log the first item in the array, and then we're going to print the first half of the items. So I'm finding the middle index of the items. So I'm saying items.length divided by 2. And I use math.floor here in JavaScript as a way for us to make sure that we get a whole number. And we're going to say variable index is 0. I'm using a while loop here instead of a for loop. And I'm saying as long as middle index is greater than 0, I want you to console log the items. So that means console log the first half of the items. So if we had 10 items, I'm going to console log the first 5 items. And then I'm going to do another for loop and say I'm console logging hi 100 times. Pretty useless, I would say. Not a very useful function. What is the big O of this function? Well, looking over here, it's going to be big O of 1 over here. So we have 1 for just logging the first items. Then we have half of whatever the items is. So in our case is n divided by 2. Because even though we have a for loop or a while loop, we're only logging half the items every time. So we can just do n divided by 2. And then finally, we're doing a for loop. But again, this is a bit of a trick. We're not looping over the items array. We just have 100. No matter how big the items array is, this is going to be always 100. So I just say plus 100. It's another step. Because again, we're just adding each of the steps that we see here. So this is our big O for this function. But rule number 2 states we want to drop the constants. We simply are saying that we don't really care that this big O is actually n divided by 2 plus 101. Remember, in an interview, we only care about the things that we saw on the chart. Nothing specific like this. So this turns into 1, and this, even though it's divided by half, in the grand scheme of things, we only care about when it scales, when the inputs are getting larger and larger. So as n gets bigger and bigger, we don't care about adding an extra 100, because if n is 1,000,000, adding an extra 100 on there, another 100 steps, doesn't really matter. And same with dividing by 2. As n gets larger and larger, dividing by 2 has a decreasingly significant effect. So we drop the constants like this. So this becomes O of n plus 1. Okay, and because 1, if n was 1,000,000, is very insignificant, we can just drop this as well. This function just becomes O of n. What if we had another function that had, let's say, O of a plus 50? Or a of 50 with a ton of zeros? It doesn't really matter. We drop the constants. It's going to be O of a. What about this other situation? What if we have this function here, compress boxes twice, where this function actually has 2 for loops, where it does the same thing, but it's 2 for loops. So we have O of n in this for loop, and then O of n in this for loop. And because these are 2 separate steps, well, we add them together. So it becomes O of n plus O of n equals O of 2n. But again, in an interview, this doesn't really matter because we drop the constants. And if we drop the constants, what does this function equate to? Well, it's just O of n. To prove that I'm not lying to you, if we look at this function on our graph, we see that the elements, as the elements increase, we have two operations because we have two for loops. If we have two elements, in that case, we do four operations. If we have three, then we do 1, 2, 3, 4, 5, 6. And you see how it increases. But at the end of the day, even though the line is steeper, we have a lot more operations to do. The way the line increases is still linear. And that's the key here. With big O, we don't really care about how steep the line is. We care about how the line moves as our inputs increase. Makes our lives a whole lot simpler, doesn't it? So remember, drop the constants. You're never going to really see numbers in big O notation. Most likely the notations that we've seen in the past before on our graph. Usually these, and the only time you see numbers is when you have O of 1, O of n squared, or O of 2 to the power of n. Which we'll get to later, don't worry. I'll see you in the next video. Bye-bye. Welcome back. Let's talk about rule number 3. That is, different terms for inputs. And this is one of the trickiest parts of an interview that a lot of people make mistakes on. But once you understand it, it becomes really easy to spot. So let's look at an example. I have the exact same function we saw in the last video. Compress boxes twice. We have the boxes array. And we just have two loops here. I'm using the for each syntax in JavaScript, but we're just looping twice over the same array. And as I said before, the big O of this is going to be 2n. But because we drop the constants, it becomes O of n. But the third rule states that different terms for inputs. And what that means is, well, first of all, let me ask you a question. What if here I have boxes as the first parameter, and then we have boxes 2 as the second parameter? And maybe this second for loop actually loops over the second boxes. What happens here? What is the big O? And during an interview, a lot of people trip up and say that this is, well, still O of n. It's going to be O, 2n, drop the constants, O of n. Now, is this right? No. Because the third rule states that different terms for inputs. And remember, boxes, the first one, and then the second one are two different inputs. One could be 100 items long. Another one can be just one item. So this first for loop is going to depend on how big the first item or first input is. And then the second for loop depends on how big this one is. And n is just an arbitrary letter that we decided on. In this case, the big O of this function would be something like A for the first for loop, which is the first input, plus B. The big O of this function is actually A plus B, or n plus m, or boxes 1 plus boxes 2. So keep that in mind. Just because you see two for loops, one after another, doesn't mean that they're looping over the same items. Now, you might be asking yourself, Andre, what happens if these loops are nested? So far, we've only worked with loops that are one after another. What if this loop was inside of this loop? Well, let's get into the next video and talk about another common pattern we see with big O, that is nested loops. one common interview question that you might get is something along the lines of log all pairs of array. Now, what does that actually mean? Well, if we had an array, let's just say boxes, and this array is just contains boxes numbered 1 through 5. Now, this array, if I want to log all pairs, it means that I want to log 1, 2, then 1, 3, then 1, 4, then 1, 5, then 2, 1, then 2, 2, 2, 3, 2, 4, 2, 5, so on and so forth. How will we go about doing that? And if you want, you can pause the video and try to attempt this problem yourself. Now, in this case, what we want to do is, well, we create a function and we'll say log all pairs of array that receives an array. Let's just say array. So we're descriptive here. And in here, we will do a for loop. So for let I equals 0. And we've done this before. So if I is less than the array.length, and we'll increment I. Now in here, we want to loop. So now in the first iteration of the for loop, we'll grab 1. But then we want to loop through the boxes again and log 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. So we have another for loop. And this time we'll say let j equals 0 if we want to loop from the beginning. Or I could even say 1 if we want to start off with 1, 2, because we're starting off at index of 1 right here. For now, we can just leave it at 0. And we'll say that as long as j is less than array.length, and we'll increment jj. And now finally in here, I can just say console.log I and j. Let's run this function and see what happens. Oh, I have to actually call this function. So let's do that. Log all pairs of array, and I'll give it the boxes array. Oh, and we want to make sure here that we're logging out the actual items and not the index of the array. So we'll just say array I here and the array j here. And just so you don't get confused with the numbers, maybe we'll change these into letters so that it's more obvious what we're doing. C, D, that's not D, that's D, and we'll say E. So if I click run here, we see that we're logging all pairs. AA, AB, AC, AD, keeps going until EE. You can see the log over here. What is the big O of this? And this is something that you're going to see a lot of in interviews. And a good rule of thumb is if you see nested loops, that means instead of having 2 for loops, one after another, where we use addition, when you see loops that are nested, we use multiplication. So this becomes O of n times O of n, which when we multiply them becomes O of n squared. O to the n to the power of 2. And that's a good rule of thumb. And if we go back to our graph, this function that we just created, and I'm using the ES5 syntax here instead of the for loops we did, this O of n squared is what we call quadratic time. That means every time the number of elements increase, so let's say we have 2 elements, we have 4 operations that we do. If we have 3 elements, this actually increases quadratically. That means instead of 4 operations, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9. Because we have 3 elements to the power of 2. And you see here how the line is now bent and it increases, well, quite fast. If we go back to our big O notation or big O graph, we see that O of n squared, well, it's horrible, as in it's pretty slow. As the number of elements increases, the number of operations increases significantly. And a lot of interview questions are questions that ask you to solve a problem that initially is O of n squared and make it faster by perhaps making it into something that is a bit low over here. That is bad, fair, good, excellent, but definitely not horrible. If we go back to our rule number 3 that we were discussing, different terms for inputs. Well, going back to that example we had in the previous video, remember this? Well, we said O of A plus B because we had 2 different arrays or inputs. Now, if these loops were actually nested and they're not one after another, the big O would have been O of A times B. And that is rule number 3. Making sure to know that we have different arrays, that means different notation for each array because we don't know the lengths. And an easy rule of thumb is any step that happens in the same indentation, so one after another, you add. And anything that happens with indentation that is nested, you multiply. So again, different inputs should have different variables. Let's move on to the last rule in the next video. Oh, we can feel the end, almost. We're in rule number 4, the final rule in our rulebook. Drop non-dominants, or drop non-dominant terms. What do we mean? Let's have a look. Let's say we have a function, again, with a really long name that says print all numbers, then all pair sums. Maybe not the best name for a function. We can probably work on the readability here, but let's see what this function does. Well, this function takes numbers, and these numbers variable, we're going to loop over them with a for each loop. So again, just looping over and logging out the numbers. And then we have another step, which should remind you, that's probably an addition that we're doing. We're adding another step. And in here, we're summing the pair sums. That is, we're adding each number one after another. Let's show you with a little bit of a demo here. If, let's say, we create, actually, we'll just print numbers. And in here, for the numbers, let's just give it an array of 1, 2, 3, 4, 5. If I click run here, we see that these are the numbers 1, 2, 3, 4, 5. Because this is the step, we're just logging it out, nothing too difficult. And these are their sums. All we're doing is adding 1 with 1, then 1 with 2, which equals 3, 1 with 3, which equals 4, 1 with 4, which equals 5, and 1 and 5, which equals 6. And then we move on to the next loop, which is 2 and 1, which equals 3, 2 and 2, which equals 4, and it keeps going on and on and on. So we see the loops that we've done here. And problems like this is something we're going to do later on in the course. Right now, we're just worried about big O. What do you think the big O notation here is? Well, once again, if we do O of the first part is the for loop. So we can say that there's O of n. And then the second part, which again is another step. So we're going to say add plus. This one has 2 for loops nested. So that means O to the power of 2. All right, so that's our big O notation. But rule number 4 states that we want to drop the non-dominant terms. That means we care about the most important term. In this case, we actually drop the n and just have n to the power of 2 because as the input increases, the size of n to the power of 2 is way more important than the n. So we always just keep the dominant term. Let me give you another example. What if we had a function that had a big O of, let's say, x to the power of 2, and then we'll say that it has 3x plus 1000, and maybe we'll say plus x divided by 2. All right, that's really, really confusing. That's math. We're not gonna want to deal with that too much. How do we simplify this based on the drop non-dominant terms? The 4th rule states that, again, we worry about the most important dominant term. Because x to the power of 2 is the most significant, that is, if x is 5, 5 to the power of 2 is 25. 5 times 3 is 15. This is 100. And 5 divided by 2 is 2.5. In this case, the dominant term is 100. But remember, with big O, we're worried about scale. And as things go larger and larger and larger. So when this becomes 5,000, well, 5,000 to the power of 2, or 500 to the power of 2, that's 250,000, if I did the math right. 3 times 500 is only 1,500. 100 is now insignificant, and 500 divided by 2 is 250. You see how this has grown significantly more? Again, because we're only worried about scale here, we drop everything else and we can just ignore it completely, and this becomes x to the power of 2. How nice is that? Just makes things so much simpler. So there you have it. We have now a way to simplify everything. If we go back to our past examples, remember this one? Remember this one? It now makes sense why we've just said big O of n. Because we don't care about the insignificant items, only the most important ones. And same with this one. By the way, a fun little note here. If we had another loop inside of these two loops, well, this would become O to the power of x cubed, or n cubed, doesn't really matter what we have, but it's going to be to the power of 3 because we have 3 nested layers. And you can keep going. You can have to the power of 4, to the power of 5. But here's the thing. If you have 3 nested loops, 99.99% of the time, that's usually a bad idea. It scales really, really badly, and most likely you're doing something wrong. And there you have it. We've gone over the 4 rules. And with this in mind, we're going to take a look at the cheat sheet that I've prepared for you. So from now on, instead of having to calculate everything and really look at every single detail of a function, you can right away figure out what the big O is, or what the time complexity of a function is. Now, I've created for you a nice big O cheat sheet. Although we've taken a lot of time to go through everything, at the end of the day, when it comes to preparing for an interview, this is pretty much all you need to know. And you can use this to review some of the topics we've covered, as well as what we're going to cover for future sections. We see here that the big O's, they're mainly these ones over here. Now, we haven't gone through everything. We've gone through constant time, but we haven't gone through something like O log n, or On log n, or O to the 2 to the power of n, or even this one with the exclamation mark. I wonder what that is. Well, we're going to get into that. But the reason I haven't talked about them yet is because they're going to come up when we talk about data structures and algorithms. these commented out big O notations are very specific for certain algorithms and data structures to optimize code. So we're going to get into that when we talk about these topics because they'll make more sense to you. Such as O log n is used a lot when it comes to searching algorithms. Or on log n is used a lot when it comes to sorting algorithms. And something like O2 to the power of n comes into play when we talk about recursive algorithms. So again, don't get overwhelmed. We've talked about these three major ones, and we're going to come back to the rest throughout the course. Now, when it comes to big O's, I want you to keep in mind two things. When you're iterating through half a collection, it's still O to the power of, or O to the n. Remember, O(n) divided by 2, it's still, at the end of the day, O(n). Remember our rule book. And again, another trick that often comes up in interviews is that two separate collections should be A plus B, or if they're nested, A times B. So two separate inputs should have two separate variables in big O notation. And just to keep in mind what causes time in a function, because that's what we're measuring right now, well, operations, comparisons, looping, we know that takes a while, and things like outside function calls when you have a function inside of a function. And then finally, we talked about our rule book. Always, big O measures the worst case. We want to remove constants. We want to have different inputs that have different variables. So O, A plus B, A and B are arrays. If they're nested, are A times B. Again, something that we've mentioned up here. The easy way to remember this is addition for steps in order and multiplication for nested steps. And then finally, rule 4 is to drop non-dominant terms. Pretty simple, right? I'm going to bring this big O cheat sheet back when we start talking and filling our gaps with the rest of the big O notation. But for now, let's get into the next lesson. Welcome back. You may have noticed something while talking about big O. Scalable means we worry about large inputs. What does the end of the graph look like? So if our function is only worried about really small inputs, or we know that our inputs are only going to be, let's say, an array of 5 items, big O won't matter as much, does it? Because over here, if the elements are small, all these lines are kind of bunched up together. They're all the same. But is that real life? No, because as humans, we tend to think in here and now. We tend to think that, oh, our website's only going to have 100 users. That's it. But what if that user base grows? What if our inputs grow? We never know. When we write code, we want to write code that can scale so that we don't have to constantly go back and fix things, or when things get out of hand, the code breaks. And that's why big O is so important. To write scalable code means thinking outside of just this small little section over here. It means thinking long term, thinking big about your code and what could happen in the future. Now, you're thinking to yourself right now, hey, Andre, I feel like I just learned a whole bunch of theory and no practical information. Andre, I want to know exactly how I can use this in my day-to-day life as a coder. I'm kind of getting bored here. Well, with this newfound knowledge, you're going to look at code differently now, right? Let's have a look. You see, now, when we look at methods that we get in a language, such as methods in an array, when it comes to JavaScript, we have things like push, pop, shift, unshift. You see, all these methods, which are functions, have a cost associated with them, a big O cost. For example, when it comes to arrays, when we search for an item, or when we access the first item in an array, for example, it's O of 1. But when we use something like unshift, well, it actually turns out to be O of n. And why that is, we're going to get into when we talk about the data structure array in the data structure section. But you're going to start to see for the rest of this course how we use big O to measure why one data structure might be better than others. Why should we use an array instead of, let's say, an object? Maybe object has better functions that we need for our data. This graph that we've talked about up until now is actually part of bigocheatsheet.com. And if we scroll down here, you'll see that each data structure, that is an array, and in this case, objects on this table is a hash table. Again, something that we're going to cover in the data structure section. But we see that we have different big O notation for different data structure. And some data structures have really good search big O. Some have insertion, some have deletion. And you can see here that there's different pros and cons to each of these data structures. As you'll find out in this course, data structures are simply ways to store data, and algorithms are simply functions or ways to use data structures to write our programs. Remember our instructions for machines, for our computers. And great programmers have this knowledge where they pick the right data structure, the right algorithms to write good programs. Remember our two rules of good code: readable and scalable. And what we've learned is the foundation for us to make a decision of which data structure is going to be best when we get into the data structure section, because we're going to know, arrays allows us to access at O and 1 constant time. But when it comes to searching through an array, it's going to give us linear time versus perhaps maybe an object. So behind the scenes, even though this section may be a little bit theoretical and boring, what we've just learned is going to lay the foundation for the rest of the course for us to be able to write good code. For the rest of the sections, we're going to use Big O to see what is a good solution to a problem and what is a bad solution to a problem. And most interviews have this core concept. What's the right data structure? What's the right algorithm to write good programs? Google hires engineers and developers that know this because they have a lot of scale that they have to think about, a lot of inputs. And people that know how to handle these programs are the ones that are going to be able to build great programs. I'll see you in the next one. Bye-bye. Let's quickly talk about a Big O notation that you're most likely not going to encounter. And if you're writing any code that has this Big O notation, you're definitely doing something wrong. It's the most expensive one. It's the steepest of them all. And this is called factorial time, or as I like to call it, the oh no. We're not even going to do a demonstration on this because you're just not going to encounter it. I just want to show you that it exists. With O and factorial, and this is a mathematical notation with an exclamation mark. You can search for it and see how it works underneath the hood. But with this, it means that we're adding a nested loop for every input that we have. Yeah, that sounds pretty terrible, doesn't it? Again, just to keep in mind and to get this out of the way, O(n) factorial, probably never going to see it, but it's there, and it kind of looks cool. So we can cross another one off our cheat sheet. O(n) factorial, you're adding a loop for every element that you're iterating over. Yeah, it's an expensive one. I'm not going to see it much. So I'll see you in the next video. Bye-bye. What is good code? By this point, you should be able to talk a little bit, especially about scalable, right? I mean, readable, we're going to talk about in the next section, but scalable, we understood was Big O, right? Well, here's the thing. Don't hate me, but I may have slightly lied or simplified things, but not that much, so don't worry. We're going to build on that. When I say scalable, there's actually two things that we want to consider as engineers. One is speed. That's what we've been talking about up until now. How fast is our runtime on the code? how much time does it take for a function to run? How many operations does it cost? Well, there's another aspect when it comes to machines. Two valuable resources. One is the time and speed of our code, and the other one is memory. You see, computers have limited memory. Back in the day when computers were just being born, memory was very, very expensive. We only had a little bit of it. And as time has gone on, we have more and more memory, but it's not infinite. Our computers run based on speed, which is usually dictated by the CPU, and memory, based on how much memory, such as RAM and random access memory, the computer has. And those are two valuable resources. So how can we talk about memory? We've talked about speed. What about memory? And the good news is that memory is fairly simple, not as complicated as speed, and it won't take as long to learn as much as we have about speed. Right now, which code is best can be answered with the 3 pillars of code, something that I want you to take with you for the rest of your career, and something that's going to grow you as an engineer, because from now on, when you write code, you're going to have these 3 things in mind. One is you're going to write readable, clean code that others can read, that is maintainable. The other one is speed. The type of code that we call time complexity has a big O time complexity that is efficient. It scales well. But we're going to talk quickly about this third pillar, and that is memory. What's the memory usage of code? If it uses a lot of memory, that's not good. We might have limited memory on our machine. With this one, we use big O once again to talk about space complexity. The same notation, but different topic. One is space, the other one is time. One is speed, the other one is memory. I'm going to give you a quick little preview. Most programming code solution, there's usually a trade-off between speed and memory. You want things to go faster? Well, then you might have to sacrifice more memory. You want less memory? Well, then you might have to sacrifice with increased speed. Let's get into the nitty-gritty of how we measure space complexity. When a program executes, it has 2 ways to remember things: the heap and the stack. The heap is usually where we store variables that we assign values to. And the stack is usually where we keep track of our function calls. Sometimes we want to optimize for using less memory instead of using less time. Talking about memory or space complexity is very similar to talking about the time cost. We simply look at the total size relative to the size of the input and see how many new variables or new memory we're allocating. How much memory is being used. So let's look at an example. Up to this point, we've talked about time complexity and how if we want to compress, let's say some boxes, we just talked about how fast and how many operations this would take. But in real life, there's this other factor of memory. And we have this pink little box of how much this function can take, how much input it's able to take. For example, if we had a ton of boxes that we have to create to run this function, well, it has limited capacity and it might overflow. By the way, things like stack overflow is something we're going to be talking about and how it's an issue when it comes to memory. Something we'll cover when we get into recursion. What causes this space complexity? Well, luckily for you, I added this to our cheat sheet. What causes space complexity? Well, adding variables, adding data structures like arrays, objects, hash tables, again, things we'll talk about, function calls, and allocations. We don't need this period. But let's actually code something and show you an example. In the next video, we'll go through some space complexity exercises and figure out how we can give big O notation to the subject. Welcome back. Let's talk about space complexity. What if I have a function that has the name of Boo, and all it does is it takes an input, and within this input, it's going to simply have a loop that we've seen before. And this loop, let's make sure that I do this properly. Let's say that n.length, and we'll say I++. And this function is a really useless function that just simply logs out console.log Boo. Scary function. So now in here, if we just run the function and just give it an input of, let's say, 1, 2, 3, 4, 5, and run it, well, we have Boo running 5 times. And we know that the space complexity of this function, or time complexity of this function, is O(n). But when it comes to space complexity, let's think about this. What is the space complexity of this? Now, try to guess before I go into the topic. The one gotcha when it comes to space complexity is that when we talk about space complexity, we're talking about additional space. So we don't include space taken up by the inputs. So we don't really care how big the input is. I mean, we do care, but when it comes to this function, we don't really have a control over what sort of input it receives. We only have control of what happens inside of this function. So within this function, are we adding any space? Well, not really. The only thing we're really doing is we're creating this let I equals 0 variable. And that's it. Other than that, we're not really adding any more memory. So this function has a space complexity of O(1). Nice and simple. But what if we have a different function? What if we have something like this? This time we'll have a function that says array of, I'm going to give it another terrible name, high and times. God, that's a terrible name. But let's say that this function takes, again, an input. And within here, we're going to create a new variable. We're going to say let high array is going to equal an empty array. And within here, we're going to have a loop. I'm just going to copy this for now so I don't have to bore you with my typing. And in here, I'm going to simply say high array in the index. So as we're looping, we're going to fill it up with high. And we're going to return this array, high array. All we're doing is we're creating a new array, and for the number of items in our input, we're going to just fill up high array with repeatedly high string. So if I do this again and I say array of high and times, and I give it, let's say we'll give it, and you know what? Instead of length here, let's just leave it as a number. So I'm going to say n, and I'll say 6 times. So if I run this code, we see that even though we have the boo 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 over here from the beginning, the other function, array of high and times, returns us a new array with 6 items, and each item just simply says high. What is the space complexity of this? Well, this should give you a hint. Remember our cheat sheet. Variables, data structures, function calls, allocations, those things take space. And in our case, we created variables in our loop, variable I equals 0, but we've also created data structures, right? We created a new array. So now if we go back, we see that in here, we've created a new array and we fill this array with n loops. And again, because of our rules when it comes to big O, we ignore the constant time, let I equals 0 space, and instead this becomes O of n, because we're creating a new data structure and adding memory, so each item is an additional memory space on our computers n times. And you know what? That's pretty much it when it comes to space complexity. I think you're getting the idea, and we'll get a little bit more into it when we talk about recursion. But when it comes to space complexity, you're either adding additional memory that you need to use, and that's sometimes a big concern, and sometimes there isn't. And something that comes up a lot in interviews, and something that we'll talk about in the next section. That is, sometimes there's a trade-off between saving time and saving space. So you have to decide which one you're optimizing for. Let's get into some fun examples based on what we've just learned in the next video. See you in that one. Bye-bye. All right, let's do a fun exercise to show you that you've actually just become a better engineer. Let's have a situation. Let's say you're working at Twitter. And I hope everybody knows Twitter here. If you're working at Twitter and your boss asked you to build a feature, perhaps a feature that allows anybody to click a button next to their name and retrieve their most recent tweet and their oldest tweet. So that is their very first tweet and their very latest tweet. Based on Big O notation and what we know about Big O notation, what can we assume about this problem? Well, without coding anything, we know that we have to find first and then find nth, or whatever the last item is. Now, we don't know how the tweets are stored in our database or whichever way Twitter organizes these things. But based on how they are stored, we might be able to just grab, let's say the tweets were in an array. So let's say const array, and we'll have an array of tweets. And let's just say we have 3 tweets here. There you go. Just 3 simple tweets. We'll say that this one is the oldest and this one is the most recent. If we have an array here, we know that it's going to take us, if the tweets are stored in an array, it's going to take us, well, if we go array 0, we get the oldest tweet. And if we go array dot length minus 1, we get the 3 minus 1, so that is 2. So that is 0, 1, 2. This is going to be 2. We're going to get Teddy, the most recent tweet. And because of the way arrays work, we know that both of these operations will be O one time. And this one will also be O1, or constant time. So a total of O2 operation, but we, again, use our rule book and simplify it to constant time. So that's great. We build a nice little simple Twitter application and we can get that information very easily. But now our boss comes back to us and say, hey, I want you to compare the dates of tweets. So I want you to look at every tweet. Now within each array, there's an object with each tweet. Now we have, and This person does not tweet a lot, 3 tweets in 6 years. But now we have to compare each tweet with all the other tweets and compare their dates. What is the big O of this operation? Well, because we're comparing each item in the array with the other, this should sound familiar. We're doing nested loops. So this is going to take O and square time, at least with what we know right now. So we know that this is going to take a lot. And if it's a person that has a lot of tweets, a lot of inputs in the array, this operation might cost us a lot of money at Twitter. So you might want to tell your boss, we might have an issue here. We might need to do something else. Perhaps store this information in a better format or do something different with our program in order to avoid something that might be inefficient. It might be expensive for the company. And just by thinking like this now, you have this ability to think long term, think scalable code. By the way, as a fun one, what happens if I ask you, what is the operation and what's going to cost us if I have a string and I do dot length here? In JavaScript, that just means what is the length of our string? That is 20. That means we have 20 items in the string. What do you think the big O notation of this is? And this is a bit of a trick question and something that you might get asked in an interview, because the answer to this is depends. It depends on the language that you're working with. We need to know how the method works on the string here, and that's built into JavaScript. And you'll have a different built-in method for your language. Based on how the language was built, this dot length might go one by one and iterate over each letter and count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way until 20. But JavaScript actually has dot length property built in to each string. So for JavaScript, this dot length property is just a simple lookup. It's not a function. We're not running this function to calculate things. Instead, it's simply a property of an object. And because of that, and again, if you're not super familiar with JavaScript, this may be a little bit confusing, but don't stress out. The idea is that this operation in JavaScript is O constant time. But without knowing how your language works, you don't know how this property might work. How perhaps if you had a method, how that might work. But now you have a powerful foundation, powerful pillar to start thinking about code in a different way. Start looking at space and time as something that are valuable to us as engineers, as resources that we must be careful. We don't have infinite amount of resources. We have to be careful when we code how we use up these resources. And that alone makes you a better engineer. I'll see you in the next video. Bye-bye. Welcome back. I just wanted to show you a quick video, especially for those that are familiar with JavaScript, that there are many, many ways to do loops in JavaScript. And same with other languages as well. There's many ways to do these loops. So I just want to show you some quick ones that you might see throughout the course, just so you're familiar with them. For example, the find Nemo function that has a for loop can also be written with something like a for each function. So I can say const find Nemo 2 takes in an array. And we can say that for each array, for each, which is pretty much the exact same thing as a for loop, but requires you to not have to type this entire thing. For each item in the array, so we'll say I, we're going to say if I equals Nemo. because in this case with for each, we're not taking the index, we're taking the item in the array. So maybe we could just say fish in here, just so it's more, or it makes more sense. And if that is the case, we'll just console.log found Nemo. Again, that is the same thing as this. For each just allows us to simplify things a little bit. There's also another way that we can do this in JavaScript with the for of loop. If we just copy this code and do find Nemo 3, this time the array that we're going to take, we're going to say, instead of the for each, this time we're going to say for let I of array. And again, this gives us the same thing, the I, or we can just say fish here, just so it's more clear, is equal to Nemo. We're going to say found Nemo. And if we run these functions, let's make sure that they both work. So find Nemo 2, find Nemo 3, and we also run find Nemo. If I click run, and I don't need the bracket for this one. If I click run, we see that we found Nemo all 3 times. Different ways of solving this problem. All of them are using loops, but you can see some are more readable than others. And that's something that we've encountered before, right? Remember, a good code means something that is scalable, but also something that is readable. Depending on your situation, and something we'll get into later on, how maintainable and how others on your team can understand this code, there's different ways of doing things so that it's easier to work with. But I hope that if you see this syntax throughout this course, you at least are familiar that at the end of the day, all we're doing is just loops. I'll see you in the next one. Bye-bye. Big O says, which function, algorithm, or code is best? We learned that when it comes to good code, we're concerned about readability and scalability. And Big O allows us to measure the idea of scalable code. And why do we care? It's because there is no such thing as a free lunch. You save time and money for a company, you're a superstar. Knowing how much time your code takes, how much memory it uses, is very, very critical. Those are expensive things for a company or a product. Now, Big O is a very important concept that you won't find in your day-to-day job, but it's something that should always be in the back of your mind. And good developers and engineers always have this knowledge. That is why it is such a popular topic during interviews. Big O is used to describe how efficient we can run our code. It saves companies a lot of money if people they hire know how to write efficient code. And in this section, we learned about the idea of time complexity and space complexity, how we can use Big O to measure both things, but each one is a trade-off between the other. And Big O describes the upper bound of our estimates. We're always looking at the worst case scenario. We want to be pessimistic and say, what is the worst case scenario here with our code so we can be prepared when the time comes? Now, time complexity and space complexity. Time is how long it takes the algorithm to run, and space is the memory that is required by the algorithm. The important thing that we learned here is that Big O is about how you can scale. It doesn't necessarily mean that O(n) is better than O(n) squared, because scalability wasn't the only factor, right? Readability is something that we were concerned with as well. Sometimes readability maybe matters more than scalability. Maybe time complexity is less important than space complexity. And that's something that you want to be careful of now with this newfound knowledge. Premature optimization can be the root of all evil. It's a famous quote that a lot of developers know. Sometimes optimizing for time or space can negatively impact the readability of code. So if you're working at a young startup, for example, it might be more important for you to write code that's easy to ship and perhaps easy to understand later. Perhaps not take as much time to write the code and think about the code and its implications for long term, because maybe the startup has limited budget and needs things done fast. That doesn't mean startups don't care about big O analysis. A great engineer at a startup or at a big company knows how to strike the right balance between runtime, space, and of course, readability. The thing to keep in mind is that data needs to be sufficiently big to talk about big O. It's about scaling. If your function is linear time, but the input is always, let's say, 7 items, then the linear time algorithm might be better than the constant time algorithm. So it really depends on your situation. I introduced Big O here because we're going to be using it throughout this course. And as we learn more about data structures and algorithms, we're going to learn more about Big O and some other things we saw in this graph that we haven't talked about. But I hope you now look at a code differently, and you had a few aha moments throughout this section. It's certainly my favorite section and a great topic that really made me a better engineer once I learned this topic. So I hope it did for you as well. At the end of this all, you have a way to look at code differently. And when someone says, "Hey, how good is my code?" you have a nice new way of looking at things and measuring things. I'll see you in the next one. Bye-bye. All right. So we have an idea of how to increase our percentage of odds of getting an interview. We also learned about Big O notation and how we can use it to look at our code and analyze whether it is efficient or not. Using our knowledge up until now, let's move to another important topic. At the end of the day, an interview is a way for the company to find out, can you solve problems that the company or employer has? Because if you're able to solve their problems, then you're valuable and you will produce more value to them than the salary that they're paying you. That is what a technical interview tries to answer. Now, we can be smart and strategic about where we apply and how we apply to a company, and we learned about that in the previous sections. But here comes the big challenge. You got an interview. What do you do? Over the next couple of sections, we're going to tackle this question and get you as prepared as possible for the coding interview. And we're going to get very technical. I know up until now we haven't seen that much code, but we're going to get into the nitty-gritty details over the next couple of sections. But before we dive into coding problems, data structures and algorithms and all of these fun coding details, we must first understand this one principle: how to solve problems. You see, if we know every single algorithm in the world, inside and out, you know all the data structures, you're the best coder in the world, well, it doesn't guarantee that you will succeed in a technical interview. This section is meant to prepare you so that you have the foundation laid out, so that after this, all you need to succeed in the technical interview is the actual coding aspects of the questions. You see, it's not the smartest interviewer that gets hired most of the time. It's the interviewer that is able to answer this fundamental question. Will you solve the company's problem? If you're a genius, but you can't talk to people, you don't work well with others, or you write ugly code that people don't understand, or you can't communicate a solution to a problem, then you won't get a job. You see, it's not necessarily about the solution to a problem in a coding interview. It's about the thought process and knowing the trade-offs between data structures and algorithms, space and time complexity. Just like in real-life coding, you don't memorize things. You have to deeply understand them. Understand the trade-offs. So That's what we're doing here. I know I'm taking a long time to get to my points, but we're trying to build the fundamentals before we dive in really deep so we understand the why of each thing. We're building this foundation by first understanding the big O, which we did in the previous section, and then learning how to solve these problems. In this section, I'm going to show you step by step what we need to do to solve problems in a way that companies really like, so that you succeed in this coding interview. We're going to look at some sample coding interviews from Google and see what they did and what is the ideal process to ace this interview. So that once we have these foundations, we can use data structures and algorithms to solve our problems. Because the interview isn't about your ability to memorize data structures and algorithms. Most people make that mistake. And interviewers can detect right away who actually knows these things versus just memorizing them the week before the interview. So, how can you ace the coding interview? In this section, we're going to talk about the technical interviews and how to succeed in them. I'm going to show you what a successful interview at Google looks like, and then break everything down step by step as to what you need to do. I will also give you a nice little cheat sheet to summarize everything in this section so that you can always view it before an interview. At the end, we're going to solve a coding problem ourselves, just like you would in an interview, and analyze different solutions to that problem based on what we have learned up until now. We're going to figure out the best way to solve the problem, but also analyzing different big O solutions when it comes to space and time. By the end of this section, you're going to have a big aha moment. I guarantee it, where we're going to take everything we've learned up until now into our data structures and algorithm sections to really understand the trade-offs. Let's get started, shall we? So what are companies looking for? Most people tend to think it's just coding skills, but as you can see here, there's actually 4 things that they're looking for. One is analytic skills. That is, how can you think through a problem and analyze things? And when you're coding during an interview, they want to hear your thought process and how you go from not knowing the answer to solving the problem. They're also looking at coding skills, which is, do you code well? Is your code clean, well organized, readable? They also want to obviously know their technical skills or technical knowledge. That is, do you know the fundamentals? Did you just memorize things? Or do you understand the pros and cons of different solutions? And then finally, your communication skills. Does your personality match the company's personality? Can you communicate well with others, with the team? Most likely, you won't be working by yourself. You're working with others, with other teams, with bosses, with managers. And they want to know whether you're the type of person that's going to fit well and work well within the company. Again, most people get hung up on the idea of learning every single algorithm, data structure, doing 1,000 problems to practice before an interview. And these are important. But in most companies, you won't actually need to know how to write a binary search tree or write a sorting algorithm from scratch. I mean, we're going to go through that in this course, but most of the time, you learn it on the go, on the job, when you actually need it. And let's be honest, as engineers, we know that most of the time, when a problem presents itself, we're good at searching the web on Google for answers. Not a single one of us has everything memorized in our head. Companies know this. They're not dumb. What they're looking for are people who know how to look for answers. And they want to know that you know your data structures and algorithms, and you know of their existence. That's the key. They want to know when you should use a certain data structure over the other. Why should we use a certain algorithm over another? At the end of the day, companies want smart people. They want people that can solve problems that they cannot solve themselves because that's what they're paying you. And having worked at companies and also hiring people, it's surprisingly hard to find people that can solve problems themselves without holding their hand or walking them through a problem entirely. So moving forward, I ask of you to just do this one simple thing. Do all the exercises in the course, pause the videos if you need to, rewatch the videos if you need to. you need to understand the why of doing things. Why are we learning this? Why is this the answer to the problem? Why is this answer better than the other? Again, don't worry. We're going to practice this muscle throughout. Okay, let's dive into the next video to see what we're going to learn. I'll see you in the next video. Bye-bye. In order to solve coding problems, we need to learn these data structures and these algorithms. It doesn't look that bad, does it? Here's the big secret. There are a lot more data structures than this, and a lot more algorithms than this. But just like when you learn a new language, you don't read through the dictionary and learn every single word in that dictionary and that language. Instead, you focus on being able to communicate with others. You only focus on things that are being used most of the time. And when it comes to data structures and algorithms, these are what you're going to get asked on in interviews because these are the ones that get used the most. And 90% of the time to solve a really complex problem, you're only using these things. Doesn't look that bad, does it? All you need is the baseline skills. And companies just want to know that you've prepared for the interview and can succeed within their system. A lot of people complain about coding interviews or whiteboard interviews and how useless they are because they never use some of these algorithms or data structure in their day-to-day job. But they're just a way to weed out people that aren't willing to work hard. Look at this as an advantage. Not many people work on their interview questions. You're going to work harder than 99% of the people out there because you know that getting a good job will have a big impact on your life. And I mean, that's why you're taking the course. And as you see here, the good news is that it's not as hard as you think. You just have to put your time and effort into the right things. As long as we learn our right data structures, when and why to use them, how to implement them, how to solve problems with them, and same with algorithms, and we combine it with our cheat sheet that I'll create for you, when we compare our code that is readable, that is memory efficient, and time efficient, using Big O. Between these two, that's all interviews are. That's all coding interviews ask for. If we go back to our outline of the course, we're now getting into the technical interview section. And when I click over here, it's going to look overwhelming at first. And we're going to go over this diagram so it all makes sense. We're going to talk about different data structures that we have. Let's zoom in a bit here. You can see we're going to talk about arrays, trees, stacks, and graphs, and a lot more. We're going to talk about the big O of each one of these data structures. We're going to talk about different algorithms, when to use what. And like I said, this is going to look overwhelming at first, but we're going to go through this step by step so that at the end, all of this makes sense to you. We're also going to use the cheat sheet right over here to help us solve these coding problems. Now, in this cheat sheet, we've already covered the 3 pillars of good code. We already talked about what skills the interviewer is looking for, but we haven't talked about this part. So let's start with this section in the next video. Welcome back. We're going to do a fun little exercise here. Now, instead of me just reading off what I wrote, I have a little ask for you. You're going to use this cheat sheet and look at the step-by-step through a problem, which is a 15-step guide of what you should do when you're in a coding interview to solve a problem. And I want you to use this as you watch a little video. Now, this video is actually produced by Google. And it demonstrates, it's 24 minutes, so it's a little bit long, but it demonstrates how you should answer a coding interview. And in my opinion, this is the best coding interview that I've ever seen. Now, I want you to watch this and keep in mind that because we haven't learned data structures and algorithms yet, this is going to be quite difficult for you to understand. And that's the goal here. When you watch this, it's going to be really, really hard to follow the actual coding, maybe some of the language that they use. I believe they're writing the code in C++, so if you don't know C++, it might be difficult, but that's not the point. The point for you here is to watch this video, but also read the step-by-step through a problem and see how the interviewee, in this case, in this video, follows these steps. And these steps are what you're going to do when you solve a problem in a coding interview. The fun thing is that at the end of this course, we're going to revisit this video. And you're going to notice a difference from this very first time you're going to watch this video to the very end, where what the interviewee does becomes second nature. You understand what they're coding in, what they're doing to solve the problem, and all these little steps, so that I succeed if you completely get this video and you understand how to run a successful interview at a company like Google or any large company, or maybe even startup, depending on what you like. So to get started, I'll be right back. You go watch this video, you follow the 15 steps, and after this, we're going to do a little problem of our own and follow the guide, the 15-step guide to solve our own little problem. I'll see you in that one. Bye-bye. Welcome back. By this point, you should be familiar with how a typical successful coding interview should look like, especially how to solve a problem in front of an interviewer. And we're going to do a fun little exercise here. An interviewer just asked us a question. And this is the question right here. Given two arrays, create a function that lets a user know, true or false, whether these two arrays contain any common items. For example, if we had two arrays here, one containing A, B, C, X, and the other one Z, Y, and I, it would return false because there's nothing common between these two arrays. However, in this example, array 1 and array 2 both contain X. And because they have a common item, it should return true. So an interviewer just asked you this question. How will we go about solving it? Well, let's go step by step through our little guide. When the interviewer says the question, write down the key points at the top. Make sure you have all the details. Show how organized you are. Well, in this case, I've kind of done this for you over here. Ideally, you would write this out as you are coding and make sure that you show the interviewer, okay, if I had this example, it should return false. If I had this example, it should return true. Now, let's say the interviewer only gave you these points and no other information. At least now you have an idea of what our problem is going to look at and whether we want to return false or true. But we have two things that we want to do with our function. One is we have two parameters, and this function is going to return true or false. Now, in the second point, make sure you double check. What are the inputs? What are the outputs? Well, we've kind of already done that, and we've confirmed with our interviewer that we have two inputs, which are arrays. We can even ask the interviewer that, are they always going to be arrays? Is it possible that the input might not be arrays? Maybe an object, maybe a string. And we can confirm with the interviewer what those cases are. In our case, let's say that the interviewer says that these two parameters are always going to be arrays. And we always want to return true or false. And number 2 is really important here because we don't ever want to jump straight into coding. Even if you think you know the answer or you've seen this problem before, you know exactly what to do, don't jump straight into coding. First, explain your approach, like I'm doing here, talking it out. Because if there are any problems with your approach or with your understanding of the question, your interviewer is going to often point them out to you here before jumping straight in and looking at your code and saying that, no, this is wrong. This way, both you and the interviewer know exactly what the steps are that you need to follow. Now let's look at point number 3 here. What is the most important value of the problem? Do you have time, space, and memory to run this function? What is the main goal? Now, because this is a simple question, we might want to ask the interviewer how large this array is going to get. Because if the interviewer says the array is never going to be more than 5 items, well, then maybe we don't have to worry about big O or time complexity or space complexity as much. And then you can ask the interviewer, is our goal here to be as efficient as possible with our function? What's more important to us? Is time complexity more important, or is space complexity more important? Maybe the interviewer might tell you that we just want the most efficient function that you can come up with, assuming that the array can get very, very large. So let's say in here we have 2 parameters arrays that have no size limit. So these arrays can get really, really big. And in terms of returning true or false, that's all we want. We just want a Boolean return. Now, number 4, don't be annoying when asking too many questions. And we're kind of getting to that territory where we've asked a lot of questions to the interviewer and we kind of have an idea of what we want to do. We can keep asking them questions, but remember, you usually have a time limit. You don't want to keep bothering them, annoying them, and just asking them all these small little questions before we start coding. Keep time in mind. And I think at this point, we have an information that we can move on with our assumption to start solving the problem. So, number 5, start with the naive brute force approach. First thing that comes into mind, it shows that you're able to think well and critically. And you don't even need to write this code, just speak about it. This is always a case when an interviewer asks you a question. They usually have an easy solution that we call the brute force, which is not the most efficient, but usually is the easiest one or the first one that comes up in mind. So in our case, if we look at this, during an interview with a time limit, you might say, this looks like a nested loop where we're comparing A with Z, and then A with Y, then A with I, and then we go to B with Z, B with Y, B with I, and then so on and so forth. So immediately this looks like we're comparing 2 different arrays, and we're going to have 2 for loops, one nested on top of each other. And right away we know that that's a big O, which we've talked about, of O n squared. Most likely during an interview, nested for loops is something that we want to avoid. Just telling the interviewer this solution, even though it's not the best solution, already shows that you're thinking clearly about the problem. And it also gives you a point from where to improve from. Now, you don't necessarily have to code this part, and it's usually enough just to describe how it works, kind of like I just did now. But depending on your time, you may or may not want to code this as well. The important thing is that you let the interviewer know that this is the brute force or the easy, naive solution that may not be the most efficient. At least this way you have the right answer than running out of time and not even having an answer. Number 6 here is tell them why this approach is not the best. So in our case, we said that the code might be not efficient, or we might have not readable, or a code that is going to be really complicated and hard to read for other developers. With my demonstration, because I just want you to think about this and so I can be more clear of why this is O(n) squared, I'm going to just code, and most likely you wouldn't do this in an interview. I'm just going to code the brute force solution so you can see what I mean. I'm going to have a function, and this function is going to say contains common item, and it's going to receive 2 arrays, array 1 and array 2. Now, we are going to take the first array and do a for loop. So I'm going to say for let I equals 0. And we'll say that as long as I is less than the array 1.length, so that's the length of the first array, we're going to increment I. And within this loop, we're going to have another for loop. So in the first time around, we're going to grab A from the first array, and we're going to compare it to the second array, Z, Y, and X. So we're going to have a for loop here, and we'll say that we'll have the same thing. This time, instead of I, we'll say J equals 0. And this J, as long as it's smaller than array 2.length, it's going to increment every time we loop through it. And finally, within here, we're going to do a bit of a comparison. We're going to compare A to Z, then A to Y, then A to X. So if I go over here and say if array 1, index of I, so array 1 at index of I, so the first time around, I is going to be 0. So that means array 1 is going to contain A. Let's actually grab this so we can see it better. At the top over here, I'm going to have two arrays here. And we're going to say that array at 0, first time around, is going to grab A. And if that equals array 2 at whatever J is the index of array 2. So first time around, it's going to compare it to Z, so A and Z. And then as this increments, it's going to compare it to A and Y. And then this is going to increment, compare A to X. And then we go to the top loop again. I gets incremented, so it becomes 1 now. So we're going to start comparing B to Z, B to Y, B to X, and then C to Z, C to Y, C to X, and so on. If that's the case, and if this is true, we just want to return true. Otherwise, if we loop through this and this never matches, well, in that case, we can just return false here. Now, let's see if this works. I'm going to just say contains common item, and we're going to give it the two arrays, array 1 and array 2. If we run this, and let's make this a little bit smaller so you can see, if I run this, I get true because there's a common item of X. If I change this to now have R and I click run, I get false. Again, if we change this to A and click run, we get true because A and A match up. Looking at this, and we look at number 6 over here, that is, let's make this screen a little bit more organized so we can read this. Number 6 is tell them why this approach is not the best. Now, again, you might not have time to even code this, but we can right away see that we have two for loops, one nested after another. And because we've already talked about this in the big O section, we know that we have a big O when it comes to time complexity here of, well, we have an array A and another array, so that means multiply by B. Again, this is a bit of a trick because these two arrays can be different sizes. We can't just say O(n) squared because these two arrays can have, again, like I said, different sizes. So this is a bit of a trick, and it's a good thing that we wrote it out because now we see that instead of O(n) squared, this is more like OA times B. If the array sizes are the same, they'll be the same as O(n) squared, so that's pretty slow. So number 7, walk through your approach, common things, and see where you may be able to break things. Any repetition, bottlenecks like O(n) squared, or unnecessary work? Did you use all the information the interviewer gave you? And so on and so forth. Now, looking at this, I can say that we could probably do better. You might not see a solution right away, and that is because you need to practice a few of these problems to understand a common pattern. But one of the most common patterns when it comes to nested for loops is that you might be able to use something called hash tables, which we'll get to. In JavaScript, they're called objects. in order to speed things up. Is there a way to turn this O, A times B time complexity into something faster? We are doing a bit of unnecessary work where we just keep looping AZ, AY, AA, and then we go BZ, BY, BA, and we're doing this comparison and the same work over and over. What if we have a better solution? I'm going to comment this out for now and scroll all the way to the bottom, and we don't need this anymore, and try a different solution. I'm going to bring the array down here just so we can see it. Now, before we start actually coding, let's think about what steps we want to take. Well, what if we had a function that takes the first array, so let's say array 1 is going to be converted to an object. And this object is going to contain something like this. It'll contain, and let's make sure we comment this out. It's going to contain A equals true, then B equals to true, C equals to true, and then finally it's going to have X equals to true. Now, if we create an object like this, we can now use this object with our array2 to just say, array2, can we check each item in array2 to this object and see if a property exists? Ideally, we can do something like array2 index and see if this equals any of the object dot properties. Okay, let's walk through this one more time. This is a common pattern that you're going to see a lot when it comes to improving time complexity. So if you don't get this right away, don't stress out. This is something that will become more and more familiar to you as we do more problems. But if I'm able to convert the first array into an object that looks like this, now instead of having to loop over both arrays, I can just loop through the second array and just simply check if the property Z exists on this object that we created. No, it doesn't. Does the property Y exist on this array? No, it doesn't. Does the property A exist on this object? Yes, it does. That means we have a common item. Now, to show you how this actually works and why this solution would be better than the first one, I need to actually start coding it. But as we go through number 8, we see that before you start coding, we want to walk through your code and write down the steps you're going to do. So let's start doing that. I'm going to say that we're going to create a new function, contains common item, and this one I'm going to add 2 because this is our second function. It's going to take in an array of 1 and array 2. And now this function, let's make this a little bit smaller so it looks nicer. There you go. This function is going to say, first, I want you to loop through first array and create object where properties equal items in the array. And then the second thing will be to loop through second array and check if item in second array exists on created object. Now, before we even start coding this, I can right away sense that we're going to have a better performance than the first array that was O, A times B. Because what we're going to do is have 2 loops, but these 2 loops aren't going to be nested. Remember, in the first solution, we had nested for loops. In this solution, in our second solution, we're going to have 2 separate for loops. And if you remember our big O analysis, when we have steps one after another instead of nested, the big O becomes A plus B. We have a potential solution here, have a time complexity of A plus B instead of A times B. Those are big savings. We need to start actually writing this code to see if we can solve this problem. And because this video is getting long, we're going to do this in the next video. But I want to show you right here what we've just done. And that is, although we haven't given a clear solution, we've been talking about how we solve the problem. The interviewer sees how we think, sees what steps we take, and sees that we're making smart, critical decisions to go from understanding the problem to solving the problem in a naive way, understanding why this might not be the best way, and then start to think about possible solutions. And the beauty of this approach is that no matter whether we get this part correct, maybe our assumptions are wrong and we can't do this, we're showing the interviewer that we're thinking through a problem and we're making small logical steps towards a solution. And this is a lot better than just coding right away, trying a solution, and see if you get it right or wrong. An interviewer is going to have a good understanding of your abilities and your thought process this way. And these are the type of people that they want to hire. So in the next video, let's finish out this problem, let's code it, and see if we can make this solution more efficient by converting it to OA plus B. I'll see you in the next one. Bye-bye. Welcome back. Let's get back to where we were. We want to start actually writing our code, keeping in mind that the more you prepare and understand what you need to code, the better the whiteboard will go. So never start a whiteboard interview not being sure of how things are going to work out. So, we've talked it out. We have a plan in mind. Let's start to code this. Let's do the first loop over here. That is, we want to loop through the first array. And let's remove this code just so it's a little bit cleaner. We want to loop through the first array, create an object where properties are going to match the items in the array. I'm going to create an object. Let's just call this map. And this map, we've created it, but we want to loop through our array. So I'm going to say let I equals 0. And we've done this before. I is less than array1 dot length. We're going to increment I. Now within here, we're first going to say if there is no property, so we want to check whether map.a exists, map.b exists, map.c exists, map.x exists. So if that doesn't exist, in JavaScript, we can just use this syntax. We can say if no map I. So again, if map I, which the first time around is going to be A, so if map.a is the opposite, so this exclamation mark in JavaScript means the opposite. If map A exists, it's going to return true. If it doesn't exist, it's going to say false. So this might be a little bit confusing, but we want to say if this doesn't exist, in that case, we want to do something. Now, the way if statements work in JavaScript, it needs to be true in order to execute whatever is in here. So we add the exclamation mark here to turn false into true. I know that can be a little bit confusing. You can read up on it, but essentially what we're doing is we're just checking for the property, if it exists or not. If it doesn't exist, then we're going to add it. So I'm going to say const item equals array1 I. So that is A. And this item is going to have map item equal to true. What did we just do here? Well, we said if map A doesn't exist, in that case, let's make array1 which is A, equal to item. So map item is going to equal to true. All we're saying is map A, in this case, equal to true. So by the end of this, we're going to have an object that is going to have property A true. And we're going to keep looping through it until we have an object called map that has all these items, map A, map B, map C, map X equals to true. All right, it looks like we're able to achieve this. And we can just console.log here just to check what we have. I'm going to say console.log map. If I run this function, let's do contains common item 2, array 1, array 2. And let's minimize this a little bit so we can see. And if I run this, I'm going to make sure I spell that right, array 2. Let's run. We see that we have A true, B true, C true, X true. Awesome. So now we have that working. Let's go through the second step. And actually, I just noticed here that this, the way it is right now, is checking I, which is 0, 1, 2, 3. But instead, we want to check A, B, C, X. So instead of I here, it should be array 1, bracket notation I. So that is A, B, C, X as the property of the map. Lots of brackets here, but I hope that makes sense. So if I run this, we should still get the same answer. Perfect. Now, let's look at the second part here. We want to loop through the second array and check if the item in the second array exists on the created object. This should be fairly simple. All we need to do, and let's remove the console.log map here. All we need to do is to loop over the second array. Let j equals 0. J should be less than array2.length. And then we're going to increment j. And all we're going to say is if map, what do we want to check? Well, we want to check if it contains the first item in the second array, that is z, as part of its properties. Remember, our map object contains these properties. So all we're going to say is we're going to check the array 2, and we're going to check the j index. So the first index, 0 of array 2, is going to be z, then y, then a. And if that's true, if it does contain those things, because remember, when we evaluate this, it's going to return true if it exists. If not, we're just going to get undefined. We're going to say return true. Otherwise, at the very end, we can just say return false. Okay, let's see if this actually works. I'm going to just click run. And I get true. Okay, so I see that A and A match. What if I change this to something that doesn't exist, like R? If I click run, I get false. What if I change this to C? I get true. If I get this to X, I get true. If I change this to W, I get false. Awesome. So we've just coded something new, a new function that, if we look at, makes things possibly better, right? Because we have two for loops, one after another, which is OA plus B, versus before, where we had nested for loops, which was OA times B. At this point, we can tell the interviewer, If the arrays are substantially large and we can get really large arrays, then this solution, when it comes to time complexity, is better. How cool is that? Now, let's go through the next steps because we're not actually done yet. Let's make this a little bit bigger. Number 11 is think about error checks and how you can break this code. Never make assumptions about the input. Assume people are trying to break your code and that Darth Vader is using your function. How will you safeguard it? So always check for false inputs that you don't want. But essentially, I now look at this code and say, how can I break this? Well, let's think this through. If I go through this code and let's say, what if I have two A's here and I run? Does this still work? Okay. What if I have A and A here? What happens? All right, I get true. That's good. But what if I have a number here instead of a string? We just assumed that the array is going to contain strings. I get false. Okay, what if I do 1 here? I get true. Okay, so that works. What if I do an empty array here? Okay, I get false. What if I do another array here? Okay, I get true. What if I do null here in JavaScript, which is a little tricky? Okay, I get false. What if I do null? I get true. Okay, that works. If we go back to what we had before, we want to now tell the interviewer how we might be able to break this code. For example, what if we don't receive a second array? What if this function is called with just one array? What happens? Uh-oh, we get an error. We want to start thinking about how errors might arise. We want to make these functions as error-free as possible. And during an interview, you usually won't have time to do all the checks that you want, but you might want to tell the interviewer possible solutions or possible ways to go around this, such as, can we assume always 2 parameters in the function? Is what happens if in the second parameter I pass 0? Okay, I still get false. What if I pass null? Oh, I get an error that says I can't read length of null. So you want to start thinking about and maybe discussing with the interviewer how you may break this function and how you may improve it, such as doing checks, such as if statements, to make sure that what the inputs you are getting are what you are expecting. Now, this is when testing comes in and testing your code comes in. During most interview, that's usually beyond the scope of the interview and you have limited time, so you can't do this, but it's good to tell the interviewer what you would do. This is one of those things that it's simple enough that you can just tell the interviewer this is what you would do versus coding it, and they will essentially give you full marks for it. Let's look at the next step. Don't use bad, confusing names like I and J. Write code that reads well. Now, when I look at this function, it's okay. Now, I say don't use variables like I and J. And although I'm using I and J exactly here, this is being used for loops. And for loops, using I here is okay because it is a bit of a standard, especially in JavaScript, and these are just simply indexes. But perhaps if these parameters had meanings, such as maybe this was the user array and this was the items array, naming these as more useful, more meaningful variables or parameters might be better. Maybe this map variable can be called tally or something more meaningful, specific for the code. Again, this is one of those things that you can talk to the interviewer about and let them know that you're thinking about these things. And that's very, very important. Again, as long as you're thinking about that and you're telling the interviewer, that you're considering these things, you're getting full marks for it. Let's keep going. Test your code. Check for no params, 0, undefined, null, massive arrays, async code, so on and so forth. And we kind of covered this in the previous step, but you want to just check with the interviewer that we're making some assumptions here, but let them know that you're thinking about that. You're thinking about the fact that this function might not always be run with 2 arrays. How can we test this function, and how would you test this function to make sure that it gives the expected result, that we always return true or false? And this is where you might say that you're going to test your code and run some unit tests. Finally, even though I say finally here, there is another point, but finally, talk to the interviewer where you would improve the code. Does it work? Are there different approaches? Is it readable? What would you do, or what would you Google to improve? How can performance be improved? Well, looking at this code, I can start telling the interviewer that, okay, the downside to this solution is that, well, only numbers and strings and booleans can be used correctly because we're using an object, especially in JavaScript, and adding properties A, B, C, and X to this object. Now, object properties, especially the way we're using a JavaScript object right now, might not work if we're using non-literal values. Maybe not strings, maybe a JavaScript expression. And you might also argue that this code could be a little bit more readable. For example, although this code is better in terms of time complexity, when it comes to JavaScript, there's actually a more readable, cleaner way of doing this. Let me show you. This is something that is language specific. That means depending on how much you know about the language that you're working with, you might be able to use methods to simplify this process. So you can tell the interviewer, I would Google specific methods on, let's say, arrays to see if I can just clean up this code and make it readable. For example, I can do this exact same function, and we'll call it contains common item 3, that takes in array 1, array 2, and in one line, I can just return array1 dot sum, which is a new feature, I think ES6 with JavaScript. And I can say item using arrow functions, which come with ES6. And I can say loop through array2 dot includes and check if it includes the item. Whoops, not that item. Now, what do we just do here? Well, we're using some built-in JavaScript methods to do essentially what we've done above, which is check the first array, iterate through each item in the array, and if some of them include the items in our array 2, just return true or false. If we actually check this with our array, and I run this, and let's comment out the first one. If I hit play here, oh, I got to make sure that this is includes, not include. I get false because our array doesn't have any matches. If it does have A and A matched, I get true. Look at that. I just created a nice little function using JavaScript here. How cool is that? This is what we talk about when we say there's different solutions to a problem. We now have a way to measure different solutions to a problem. We can say that there's actually another solution using some of the built-in methods that comes with JavaScript that is, some would say, more readable, more concise. If you're working on a team that really knows their JavaScript, this is a lot easier to read than this, right? So maybe readability is more important. You might say that this is a better solution. Another thing you may have noticed is that we've talked about time complexity here. And we haven't really talked about space complexity. And this goes into a final point. If your interviewer is happy with your solution, the interviewer usually ends here. It is also common, though, that the interviewer asks you extending questions, such as how would you handle a problem if the whole input is too large to fit into memory? Well, if we talk about space complexity here, we can see that in the first solution that we had, let me comment this out, we have space complexity of O1. Because we're not creating any new variables, we're just using the inputs arrays. Technically, additional space complexity for our function is O1. It's constant. But if we scroll down to this one, well, we're creating a new object here. And we're adding the first array into an object, which takes up memory. So this solution actually has space complexity of OA, which is the first array, space complexity. So if an interviewer says if there's limited memory or memory is expensive, you can just tell him or her, well, this solution, although faster in terms of time complexity, is more heavy in terms of space complexity. Now, this point here that we forgot to mention is something that, again, is really good to mention during your interview. Modularize your code from the very beginning. Break up your code into beautiful small pieces and add just comments if you need to. What does that mean? Well, we have the solution over here that we've worked on, and we've commented it out. We've modularized, saying that this first block of code is going to do something, then this block of code is going to do something else. But as code gets more and more complex, it becomes increasingly important to write in a modular way. That is, small bits and pieces that read like English. You see, long, really hard to read code costs companies a lot of money because it's not just you working on a code base. It's most likely tens, hundreds, if not thousands of developers and engineers. So companies want to hire somebody that is able to write clean code that is readable, that is easy for anyone to pick up and code along with. For example, here, what we might want to do is actually separate these out into different functions. Maybe creating a function in here that perhaps says map array to object that receives the first array item. And then maybe here another function to the outside world that says compare array to object. Now, you don't really have to do this during an interview, but it's good to mention it and talk about the idea of modularizing your code. If a function is doing too many things, that's not ideal. When we say modular, we want to build small pieces of code that do one thing and one thing really well. Ideally, a function takes an input and returns an output, and inside of that block does just one thing. If it has to do any extra actions, well, perhaps you have another function that lives on the outside world, and this function also does one thing really well. And this creates really testable, clean code that is modular. Again, something that is really good to mention and talk about in your interview. Whew. All right. I know this is a lot, and it's a lot to think about because now you start thinking, am I going to have to worry about each code that I write and analyze it this deeply? No. In your day-to-day life, you're not going to do that. But I wanted to demonstrate to you that this is the kind of thought process that really good developers have and what companies are interviewing for. If you're able to think clearly through these steps, like I have outlined for you, and you're able to solve problems this way, you see how much more impressive it is than if I just wrote down this solution without any explanation. Even if you don't get to this part and time runs out during your interview, you've demonstrated to your interviewer that you're able to think clearly. You have the fundamentals to think like an engineer. And these are great qualities that companies love to hire for and skills that are very rare. I hope you had fun with this exercise. You might have to come back to these videos later on. But for now, I'll see you in the next one. Bye-bye. Hello! I know. The last two videos were kind of long, very technical. If you weren't familiar with JavaScript, maybe they were a little bit tougher. But the point was the process of solving a problem in a coding interview. And over here, I've created a little playground for you. You remember the Google interview video that I made you watch? Well, I've implemented the solution that the interviewee created in here. We have the naive solution, which is the nested for loops, and then a better solution that uses just one for loop at the expense of creating something in JavaScript called new set. I left this here for you to play around with, and if you want, code it in your own language. But I wanted to challenge you to see if you can implement this on your own, just like the person in the Google interview did in your own language. The naive approach and then the better approach. And try to follow these steps as you code along. Even though you already know the answer, even though you have watched the interview video, by practicing the steps and how you go from the naive to the better solution, by following these steps, you're going to improve that interviewing muscle. All right, I'll see you in the next video. Bye-bye. All right, another section done. And in this section, we talked about the technical interviews and how to solve problems specifically. One big misconception is that you're either a good problem solver or you aren't. But as with anything, it's a muscle that you can train, that you can practice. So with enough practice and knowing the tips and tricks that we covered in this section, you can solve problems a lot better. That shows the interviewer you know what you're talking about. The key in this section was this cheat sheet and the step-by-step walkthrough of a problem. We looked at how a Google interview might look like, and then we mimicked some of the techniques used there to solve our own problem. The idea was to show how you work. Think out loud and try to comment the steps as you go along to solve a problem. Communicating throughout the process as much as possible and not worrying about finishing a problem fast is the key to interviewing and solving problems in an interview. Now, we should have also gotten the idea that we don't want to memorize problems. Because if you do 100 problems and try to memorize them, well, it won't really help you long term. But you're also taking a gamble, right? You're hoping the interviewer asks you a question that you've seen before. Instead, we want to take control of our destiny and practice and be ready for anything by building the fundamentals. We talked about how by using the big O and the lessons we learned here, we can now move on to data structures and algorithms and use them during our code interviews. We also talked about some of the skills that interviewers are looking for and demonstrated how it wasn't necessarily just coding skills. There's a lot of other aspects that interviewers are looking for. And we covered these items and how to show them during our practice interview question. Finally, we're now ready to dive into the exciting part of data structures and algorithms. We have a nice foundation, and we know that all we need is to learn these data structures and algorithms to really be interview ready. And we're also going to be using the cheat sheet that I gave you in this section throughout the rest of the course. And at the foundation of this cheat sheet is the idea of readability of code, space complexity of code, and time complexity of code. And although we didn't cover everything in the cheat sheet, we have a few items here at the end. You'll see that as we go through the data structure and algorithm questions, certain type of patterns will emerge. That although questions may be different in an interview, usually the way to optimize things or tricks to make your answers better can be narrowed down to specific steps. So don't get overwhelmed. There's an easy, clear checklist and heuristics that we're going to go over later on. But by this point, I think we're ready to move on to data structures and algorithms. How do we write good code, create good programs, create value for the companies that we're interviewing for? See you in the next section. Bye-bye. What is a data structure? A data structure is a collection of values. Algorithms are the steps or processes we put into place to manipulate these collection of values. It's what allows us to write programs. A person who knows how data structures and algorithms work and how to use them can write programs, great programs. The beauty is that these are timeless. No matter what programming language you use, whether you prefer one library over the other, whether you write code in Angular or React in the front-end development world, or you're a game developer, underneath it all, it's all data structures and algorithms. If you understand these, then you can really easily adapt and tackle all sorts of technical problems. It is why companies like Facebook, Amazon, Netflix, Google ask questions specific to data structures and algorithms. Because although it may be important to know the latest and greatest JavaScript syntax, or maybe the latest and greatest library, those things change. If you know the fundamentals though, then they can throw you any problem, any situation, and you're able to make the right decision. This knowledge is extremely valuable. The longer you are in the field, the more and more you realize that you need these fundamental principles of data structures and algorithms in order to be a great developer or engineer. So let's get started with that. Over the next few sections, we have a long way to go to get familiar with data structures and algorithms so we can write great programs. Let's get started. Welcome back. What is a data structure? A data structure is a collection of values. The values can have relationships among them and they can have functions applied to them. Each one is different in what it can do and what it is best used for. Most important thing to take away is that each data structure is good and is specialized for its own thing. All right, Andre, you just said a bunch of words and I don't really understand. Well, let's show you a couple of images to simplify this. You see, you can think of data structures as any sort of compartment or container. A data structure is simply a file cabinet of different types. You have a backpack, a place where you put maybe your school books. You have drawers where you put your clothes, a fridge where you put your food, a folder for your files, and a packing box maybe for your toys. Each one of these containers are useful for its own thing. For example, I'm not going to put my food in a drawer over here because that yogurt is going to go bad here. Likewise, I'm not going to put all my papers and files in my backpack or perhaps a toy box because it's just going to get crumpled up. Each one of these containers are specific for its own thing. And that's what data structure really is. It's a way for us to organize data so that we can go into the backpack and retrieve that data really easily. We can go into the fridge and grab that popsicle or ice cream really fast. We can put things in data structures and we can take things from data structures. And that's all it really is. And there are a ton of data structures. Just like in our real life, how we have all these containers, all these places to put things in programming, we have a ton of them. If we go to Wikipedia, for example, well, if we scroll through here, we see a ton of data structures. And this is going to look overwhelming, but don't worry. Most of these, well, I've never encountered myself, and they're very, very specific. You probably only have about 5 or 6 data structures that are really, really important that we're going to go over. And you may have even heard of Bitcoin. and how it uses blockchain technology, this magical word. Well, blockchain at the end of the day is simply a data structure, a way to hold information. So in our programming world, data structures, we can store things like numbers, strings, Boolean types. Just like we saw when we coded in JavaScript with arrays and objects. Arrays and objects in JavaScript are each a form of a data structure that allows us to store information. You see, as humans, this is what we do on Earth, right? We take the chaos and the disorder and make order out of it. At least we try to. We organize our farms to produce food. We package the food and we deliver them to the grocery stores and organize them in the grocery store so that humans can grab those and can then purchase these groceries and give money to put in a compartment and a bank. That's what programs are. We're modeling real life scenarios. And the more advanced a developer you become, the more time you'll start thinking and spending time talking about data structures. This is why interviewers love to talk about data structures. Now, as I always like to mention, there are always trade-offs. Every programming question has a trade-off. Remember our 3 pillars of readability, memory, and speed? When we talked about what code is best? Well, we have the same thing with data structures. One is better than the other in some aspects and the other better than the other. That's why they exist, each one for its own specific case. And there are 2 parts to understanding data structures. One is how to actually build one. How can we build with code some of these data structures? And 2 is how to use them, how to use these data structures. We're going to do both of these in this course. But the second point is the most important, right? Because data structures are usually just tools. And most of the time, they're already pre-built for us. The most important part is how to use them, when to use one over the other. And we kind of saw a little bit of that in the previous section when we talked about how to solve problems, where we used an object versus an array to make our code more efficient. The goal in this course is to understand data structures so that you can pick the right data structure for your problem. Based on different scenarios, data needs to be stored in a specific format. We have a handful of data structures that cover our need to store data in different formats. So let's get a little bit deeper into this topic. In order to truly understand the value of data structures, we have to go deep down into the way a computer works at the fundamental level. In order for a computer to run code, it needs to keep track of things like variables, like numbers, strings, array. These variables are stored in what we call random access memory, or RAM for short. That's how programs run. We remember this from space complexity video, right? On top of that, we also have storage, where we store things like our video files, music files, documents. And the storage can be a disk drive, a flash drive, or a solid state drive. Data on storage is permanent, or what we call persistent. So when you turn off your laptop or computer, it's still going to be there when you turn it back on. In RAM, you lose the memory when the computer turns off. So why wouldn't we just always use storage so we don't lose any data? Well, the problem is that persistent storage is slow. Because you see, a computer is run by its CPU. You can think of the CPU as the little worker that does all the calculations that we need. It does the actual work inside our computer. And this CPU needs access to the RAM and the storage. But it can access the RAM and the information in the RAM a lot faster. But let me give you an example as if we're using Google. when we run Google Chrome, for example, a browser, that Google Chrome browser has a piece of code. Now here I've simplified it, and we just have a variable a equals 1. We're just assigning this variable 1. But we can imagine how we have hundreds, thousands of lines of code of Google Chrome. Now, in order for our computer to run Google Chrome, we run the CPU for it to do so. Now, when a variable is declared in, let's say, a script to run Google Chrome, it's going to hold that in memory, in our random access memory. But once we turn off or close Google Chrome, we want to be able to reopen it, right? Well, that's what we do when we save an application on our computer. We save it to storage so that next time we open up Google Chrome, the CPU is going to grab the program from the storage so that it can use it again. And for Google Chrome to run fast and run smaller scripts, it's going to keep that information in random access memory. We can see this on our computers as well. If I go to About this Mac, my computer, we can see here that we have the processor, which is my CPU. We have my memory, which is my RAM. And if I go to storage, this is my flash storage, my persistent storage on my computer. So you can think of RAM in the computer as a massive storage area, kind of like a data structure, right? Well, this massive storage area has shelves that are numbered. We call these address or addresses. And it's a really, really big shelf that holds a lot of information. And it allows us to run programs on our computer. Now, each of these shelves holds what we call 8 bits or numbers. If you see here, 1, 2, 3, 4, 5, 6, 7, 8. Each one of these numbers is a bit. And a bit is a tiny electrical switch that can be turned on or off. But instead of calling it on or off, we call it 1 or 0. And 8 bits is called a byte. Each shelf has 1 byte of storage. And the CPU is connected to something called a memory controller. And a memory controller does the actual reading of this memory as well as writing this memory. Because sometimes this shelf might be blank and doesn't have anything. Now, this direct connection to the CPU is important because the CPU asks the RAM, hey, what's in shelf number 0? And the memory controller actually has connections individually to all of these shelves. Again, that's really important because it means that we can access the 0 shelf and immediately access the 7th shelf or 10,781 shelf without having to climb down or step down. That's what the name random access memory means. We can access memory really fast because we have these connections any shelf we want. We just need to know which shelf we're looking for. We can access the bits at any random address in memory right away. Even though this memory controller can jump between far apart memory addresses really fast, programs tend to access memory that is nearby. The closer the information is to the CPU and the less it has to travel, the faster a program can run. So computers are actually tuned to get extra speed boosts when reading memory addresses that are close to each other. For a computer to access 0 and 1 is a lot faster than a computer for it to access 0 and 1,000. Because these are a lot closer together. And to further optimize this, our computers also have what we call a CPU cache, where the CPU has a tiny, tiny memory where it stores a copy of stuff that is really, really recent. And this is called a cache. A common one that you might hear is something called LRU cache. So again, if we use Google Chrome as an example, we turn on Google Chrome with, let's say we have the application downloaded on our storage. The CPU loads it up. And because we've visited hackernews.com, it's going to load up the information for that Hacker News and put it into memory, or maybe even cache if it can hold it. So, why is this important for data structures? Well, data structures are, remember, ways for us to store information. For example, if we want to store variable a equals 1, well, in our modern computers, usually we represent integers, that is the number 1, in 32 bits. That is this block size of RAM. And by the way, this is now can be 64 bits with more and more recent upgrades. But this way, we can store the number 1 within this blocks of 32 bits. Why 32 bits? Because 8 bits, which is 1 byte, times 1, 2, 3, 4. So 8 times 4 is 32 bits. We can store 32 bits of information. And this bit of 1, you can see here, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 1 is stored now in memory 0, 1, 2, 3, or the address 0, 1, 2, 3. If we have another variable, b equals to 7, we would store it in the next block over here in our RAM. In doing this, you can now think about how systems that are 8-bit can hold 255 bits of information. Things that are 16-bit, well, they can hold a lot more information. And now we have systems that are 32 bits. You can see here that we can hold a ton of information. And then if we had 64 bits, that is, instead of having 4 little shelves over here, we have 8 shelves. Shelves times 8 bits. Well, that's a lot of information that we can store. And the bigger this is, the more diverse that information is. If we had an 8-bit system, well, the number 256, we can't really store that. That's really hard to do. And I can demonstrate this to you with JavaScript. You see, there's something called integer overflow. Now, JavaScript technically doesn't have integers. It only has what we call a 64-bit floats. But the idea is that a computer can only store a certain number of information. So using this syntax in JavaScript, we have math.pow, which is a function that returns the base to the exponent power. That is, the first parameter is the base to the power of the second parameter. So we can create really large numbers like math.pow, so 5 to the power of 100. If I run this, we see the number over here. If I increase this to, let's say, 6, again, another large number. Now, what if I keep going and change this to 6 to the power of 1,000? We get infinity. What is that? Well, as the number becomes too large to store in our RAM, then we need to represent this number that we cannot store into something that is tangible. In JavaScript's case, it is infinity. We can only store this much information, and no matter how big I make this, any number above a certain threshold is going to just say infinity. How cool is that? Now let's go back to the slides. I showed you all of this because other data types other than numbers work the same way. Each data type has a number of bits associated with it, and that needs to get stored in the system. And the system allocates that storage, and then the CPU reads from that storage. Now, I'll leave a link for you after this video so that you can get more information if you want. We don't want to get too deep in this. But a data structure is this. A data structure is an arrangement of data. You can define the way you interact with this data and how it is arranged in RAM. So some data structures in RAM are organized right next to each other, some are organized apart from each other, and they have different pros and cons on access and write. Our goal is to minimize the operation that we need to do for the CPU to get the information, for the CPU to write information. And that is why data structures are so powerful. We're thinking about the low level. And I don't know about you, but this to me, when I learned about this, was really, really exciting. Because we have a way now to think how data structures actually affect the process of our computers, and how we can use what we know about computers now to write great code. I'll see you in the next video. Bye-bye. Welcome back. There are quite a few data structures that you may be asked in an interview, and we saw how many of them there are on that Wikipedia page. But luckily for you, the list isn't actually that intimidating. All you need to learn are these ones over here. These are used, I would say, 90% of the time. And this is what we're going to talk about in our course. Now, there may be specific ones within these groups, and each one of them has trade-offs. But as long as you learn these and you learn when and why you should use them, then you're going to be miles ahead of most people. It's going to be a lot of fun. Now, before we get going, I want to note one last thing. You see, each language has their own data types, or built-in data types. JavaScript, for example, has numbers, strings, has booleans, which are true, false, and then some strange ones like undefined. And each language has data structures to organize these data types. So for example, in JavaScript, we have arrays and objects that we use. And they are data types. It allows us to structure and organize information such as our primitive data types, or even hold more complex ones like having an array that contains multiple objects. And we're going to talk about this in more detail, but I want to show you that we do have different languages that have different access to some data structures. You can see over here some of the other languages that we can use in this course and whether they have them available. We see that Java has arrays, has linked lists, stacks. We have priority queues and many other types. Now, does that mean that if we're using JavaScript, we can only use arrays and objects? Well, no, not really. Although these languages come with data structures built in, we can also build our own. And most languages have enough data structures and data types for us to build and create our own data structures. So if JavaScript doesn't have stacks, well, we can build one. Now, to finish this section and finally dive into our first data structure, I wanted to just remind you that we have a little map over here of what we need to know for the coding interview. Now, in this map, I have a little present emoji next to each one of the data structures that we're going to talk about. As you can see, there aren't that many of them, and many of them are quite related or are children of the other. But use this as a reference for you to just draw a map of how things are connected and what the data structures are that we're going to talk about. But let's get our hands dirty with our first data structure. I'll see you in the next one. Bye-bye. What are the various operations that can be performed on different data structures? Because as we learned in our previous lectures, data structures are simply ways to organize our data on our computers. And the data structures we'll see throughout this course are simply variations of how we store this data on our computers, this information. And each data structure has their trade-offs. Some are good at certain operations, others are good at other operations. One type of action that we're going to perform with data structures, well, is insertion. Add a new data item in a given collection of items, such as us adding the Apple item in memory here. Another one? Well, deletion. We want to sometimes delete data, such as remove mango from our list. Another type of action might be traversal. And we're going to see this a lot. Traversal simply means access each data item exactly once so that it can be processed. Another useful one is searching. We want to find out the location of the data item if it exists in a given collection. And then we also have things like sorting. That is, having data that is sorted, kind of like it is on the left-hand side over here, versus the right-hand side where there's not much sorting going on, at least from what we can see. And obviously, the main one, and probably the most important, is access. How do we access this data that we have on our computer? Now, each data structure that we're going to go through in this course will have different pros and cons for each one of these. And if we take a look at our Big O cheat sheet, well, we're very familiar with this diagram over here, or this graph. And if we scroll down, we have all these data structures that it lists. And don't get too overwhelmed. We're going to go over most of these data structures, and you see that half of them are mainly trees and variation of trees. And within here, we see that each one of them has access, search, insertion, deletion, average, and worst case. And because we understand Big O, we can see that, all right, we're seeing which one's good for what and what is bad for what. And as we go through our data structures, we're going to go over these pros and cons so that you build the foundation to be able to decide which data structure should I use on your next problem. We're going to get started with our very first data structure in the next lesson. I'll see you in that one. Bye-bye. Woohoo! It's finally time to learn our very first data structure, and one that most likely you're very familiar with. Arrays. Arrays, which are sometimes called lists, organizes items sequentially. That means one after another in memory, kind of like we have here. We have some sort of data at index 0, let's say juice, and then right after at index 1, we have something else, maybe apple. Maybe this is a grocery list. In our computer's memory, it'll be one after another. Because remember, our RAM is a lot bigger than just 7 slots. And the arrays are probably the simplest and most widely used data structures. And luckily for us, we're starting with this because arrays have the least amount of rules. And because they're stored in contiguous memory, that is, in order, they also have the smallest footprint of any data structure. So if all you need is to store some data and iterate over it, that is, go one by one, step by step, arrays are the best choice. Especially if you know the indices, that is, here on the left, of the items you're storing. And just as a quick glance, and we'll go over this in more detail in later videos, but lookup or access with arrays are constant time of 1. It's super, super fast. Other actions or methods that we're going to go over, such as push, are also fast, but then inserts and deletes are O of n, or linear time. But in order to demonstrate arrays, let's actually use code to show you an example. We have our little playground over here. And again, you can use whichever language you prefer. I'm just going to demonstrate this in JavaScript. We can create a simple array. Let's call it strings. And this array, again, using the square bracket notation, will have A, then B, then C, and D. And we've just created an array in JavaScript. Now, looking at this, and based on what we've learned so far, we can make a couple of assumptions. For example, to store the letter A, letter B, letter C, letter D, that's 1, 2, 3, 4, 4 items. If we were on a 32-bit system, that is, we have 1, 2, 3, 4 shelves to store the letter A in zeros and ones. Well, if that's the case, we just multiply 4 times 4. So 4 items, and each item taking up 4 shelves in our memory. That means we're using up 20 or 16 bytes of storage. If we remember in our little example here that with a 32-bit system, we have 1, 2, 3, 4 shelves to store this number. Again, this is a bit of a simplified version of looking at it, but I hope you see what we're doing here. We're simply storing A, B, C, D in sequential order in our RAM, our random access memory. So the computer now knows where to find these items. Therefore, when I do strings 2, I'm telling the computer, hey, go to the array called strings. You should know where that is because underneath the hood, you stored it for me. And grab the third item. Remember, the indexes are 0, 1, 2. So grab the third item from where the array is stored on your memory. And if I run this, I'll get C. The computer is going to grab that information for me because here it stored it for me and here it's grabbing it for me. All right, so let's do a few more operations with arrays and see what the pros and cons are. Well, in JavaScript, we have a few methods that we can use with arrays. One is push, which simply allows us to add something at the end of the array. So strings dot push E. And if we just remove this, and let's have a console.log of strings. If I run this, I get A, B, C, D, E. This string push operation, because it just adds it at the end of the array, is an O1 operation. All we're doing is adding whatever item we want at the end. We're not looping through anything. So hopefully that makes sense why that would be O1. That's very convenient. What's another method that we get? We can also use pop. And pop is the opposite of push. Pop will simply mean to remove the last item from the strings, from the array. If I click run here, you see that the E was moved. If I do strings.pop again and hit run, we see that this time around we've added E, then we removed E, and then finally D to be left with A, B, and C. What do you think the time complexity of this operation is? Once again, it's O of 1 because we're not looping through anything. We're just removing the last item. And remember, our computer knows where last item is stored. We're simply saying, go to index of, let's say, 7, the very last item, and remove the bread. But let's do something interesting here now. What if we want to add an item at the beginning of the array? Maybe in here we want to add the letter X. Well, we have something called onShift in JavaScript. And depending on your language, you'll have perhaps something different. But the idea here is we simply do strings.onShift. And by the way, you see here how REPL.it actually gives you the parameters that you can enter. In this case, it just says what items, which is a string, should I enter. In our case, I'll say I want to unshift X, which is saying just add X at the beginning of the array. If I click run here, we see that x has been added at the beginning of our array. What do you think the time complexity of this operation is? And by the way, as we go through data structures and because we know big O notation, isn't it pretty cool that we're able to think about code beyond just, oh, I'm just doing this. We can think deeply about what's happening underneath the hood. Why might this operation be longer than this operation? I find that fascinating, and when I first understood this point, it really made me a better engineer. And I hope you're starting to get this aha moment for you as well, especially if this is your first time with data structures. Now, on shift, what are we doing here? Well, remember, strings are essentially stored. If I move this to a new line, the computer knows that this is at 0, this is at index of 1, this is at index of 2, and this is at index of 3. When I add x with the unshift, I'm all of a sudden adding x into our array, but we now have to shift these numbers because the indexes are still like this. But this time around, we have to say, okay, 0 is now at x, A is now 1, B is now 2, and C is at index 3, and D is at index 4. And just by me doing this, you might have seen something. We just iterated, looped through everything, and reassigned the indexes. And I did 1, 2, 3, 4, 5 moves, or 5 operations to realign the indexes. And this should give you a hint. That is, this operation is O of n. Depending on the size of the array, that's how long it's going to take to do that operation. We're looping. So right away, we know that, with arrays, maybe it's not the best data structure for adding items at the beginning of the array. What if we wanted to add something in the middle of the array? So we can use the method splice here. Let me scroll down a bit. And with splice, I can say strings.splice. And again, I get a hint of what I can do. The first is the start number. So I want to start at index of 2. And remember, we have this array here, x, a, b, c. So we're starting at b. And the second parameter is the delete count. What do we want to delete, or how many things from this index do we want to delete? In our case, we don't want to delete anything, we just want to add. So I'll say 0, and then the items that we want to add. So let's just add a string that says alien. Oh, and let's remove this x from our original array. That's better. Let's hit run, and there we go. We have x because we've unshifted, a, then alien, b, c. So splice told us go to index of 2, 0, 1, 2, where b was initially, and add alien instead of b and just shift things over. So what we've done here is, if we go back to our example, we have the x in our array, and we shifted these indexes of x and a are still the same, but we shifted b over and said, in here, I want you to add alien. And we now had to go over everything and say 2 for alien, we want 3 for b, 4 for c, and 5 for d. So what's our big O here? We don't need this comma. Well, our big O in this case, we did half of the operations because we changed half the array. We looped through half the array. So it would be O of n divided by 2. But remember, our rules when it comes to big O, we remove constants and simplify to just O of n. Worst case, it's going to be O of n operation. All right. I'm going to leave this for you so you can play around and try different methods on arrays. But I hope you understand how they work and how there's some good things that we can do, such as accessing the array that is O of 1 because it's, well, extremely fast. We know exactly where it is in memory. We can push and pop, but when it comes to unshifting or splicing or even deleting, because with splice we can even do deletes, that's going to be O of n. And if we go back to our chart, we should now have a better understanding of why arrays lookups are extremely fast. We know where they are. We know why push, adding at the end of the array, is extremely fast. But why inserting and deleting might not be the best or the fastest when it comes to arrays. But here's the thing. There's actually two types of arrays. And in the next video, we're going to talk about these two types. I'll see you in that one. Bye-bye. Welcome back. As I mentioned in the previous video, there are actually two types of arrays. One is called static, and the other, dynamic arrays. Now, what is the difference between the two? Well, the one limitation of static arrays is that they're fixed in size, meaning you need to specify the number of elements your array will hold ahead of time. So in this case, if this was a static array, I would say create an array of 7 items, knowing beforehand that in my grocery list, I'm only going to have max 7 items. Because arrays are allocated in adjacent blocks of memory when they're created, there's no guarantee that after we've allocated 7 shelves of memory that you can keep adding things on, especially in order. We solve this problem with static arrays that require us to say ahead of time, hey, I only want 7 shelves of memory, with dynamic arrays. And dynamic arrays allow us to copy and rebuild an array at a new location, which with more memory if we wanted more memory. So for example, with our static array, if we realize that we forgot another item on our list and we need 8 items, what happens is we copy this entire array, we allocate 14 blocks of memory, and paste this list plus the 8th item into that new location. Let me show you how this works with code. You see, in languages like C++, let me scroll down over here. In C++, which has static arrays, to create an array, you do something like this. You would say int a 20. And this says, I want an array that has space of 20 items. Or you can do something like int b5 and then fill up the array of 5 items with 1, 2, 3, 4, 5 integers. That's what int stands for, numbers. And because of this, and because this is a static array, in order for us to add a 6th item on here, well, we would need to copy this entire array and move it over to a completely different area of memory in order to create the space for it. Now, luckily for us, when I showed you with JavaScript how to do this, well, we never had to worry about it, did we? In our JavaScript example, we never really allocated memory. And that's because in JavaScript and other languages like Python, where you have lists and array list in Java, they work like dynamic arrays. They automatically allocate memory according to the increase in size of the array. So right off the bat, you're thinking, dynamic arrays are way better, easier. I don't have to think about memory because of automatic resizing. And that gets into a discussion of managing memory, which low-level languages like C++ allow, while higher-level languages like JavaScript allow us to not think about memory and let the machine take care of it for you. There's times where maybe you do want to manage your memory and times where you don't need to, based on your needs. Obviously, having more control over memory allows you to really tweak things and make things faster. And that's why languages like C++ can be much faster than higher level languages like JavaScript. But we don't need to get into that. What we want to get out of this lesson is that dynamic array expands as you add more elements. So you don't need to determine the size ahead of time. But you may have noticed something with dynamic arrays. You see over here how I have append at O of 1. That is the same as the push command that we did in the previous lesson. But I have a star here that says it can be O of n. Why is that? Well, if we remember our array, and let's remove the extra items here that we don't need. So just say A, B, C, D. If underneath the hood, JavaScript and our machine only created 4 blocks of memory for this array, and we add another letter underneath the hood, because this is a dynamic array, it's going to loop over these items, copy them, and move it to a different location with now 8 blocks of space, so that we can keep adding onto here. And you see here, because we did this looping, the operation becomes O of n. So that's something to keep in mind. Although it's a minor detail, it's good to know how things work underneath the hood. And most of the time, with the languages that you're working and during interviews, you will be talking about dynamic arrays, and you won't have to worry about allocating memory and thinking about the possibility that you might have to copy the array. That's really low level. But I wanted to show you how they work so that you have those fundamentals going forward. And understand that when it comes to arrays, just because you're adding at the end using the push command, you can assume that it's O of 1 most of the times or constant time. But every once in a while, you might encounter a situation where it's O of n, linear time. I'll see you in the next video. Bye-bye. Welcome back. We're going to talk about some advanced objects concepts. Now, as I said, with both arrays and functions, these are advanced concepts. You're probably not going to just get it 100% the first time around, but use these videos as a reference to come back as you progress through your career. Now, in this video, I'm going to talk about 3 things that are important with objects. We're going to talk about reference type. We're going to talk about context. And finally, we're going to talk about instantiation. So let's get started with the first one, reference type. What do I mean when I say reference type? Well, I want you to see if you can guess what's going to happen when I do array equals array. What do you think the answer is going to be? Let's see. Interesting. Okay, what if I do array 1 equals array 1? Interesting. Okay, one more question. What about something like this? Object 1 equals a value of 10. And we'll say object 2 equals object 1. And we'll finally say variable object 3 equals value 10. So looking at these, and I'm actually going to copy it on here so you can see it as well. Looking at this, what happens if I do object1 equals object2? What do you think will happen? True. Okay, that makes sense. I mean, object2 is object1. But what if I do object1 equals object3? Here I get false. But why is that? We have value 10, value 10. They're both the same thing, right? Let's check something else. What if I do object1.value equals 15? Okay, and now I do object2.value. It equals 15, but if I do object3.value, I get 10. Well, that was confusing, right? Let's look at what's actually going on. And this is the first topic we're talking about, which is reference type. Let's look at a diagram. Objects are what's called the reference types in JavaScript. Up until this point, all the other JavaScript types that we've learned, including numbers, null, we have undefined, booleans, strings, even symbols, they're all defined by the programming language. So JavaScript, the person who wrote JavaScript, and ECMAScript, the standard, says these are primitive types. We tell you what they are. Now, a reference type, which is a non-primitive type, are not defined by the programming languages. What that means is that they're created by the programmer. So let's look over here as an example. When I say variable number1 equals 1, JavaScript knows what 1 is. It's a number, and it's a primitive type. It's always the same thing. It's immutable. Every time it uses a 1, that's the same one that JavaScript knows about. When I do variable number2, yep, it's using the same number1 that JavaScript knows about. However, when we created object1 equals value 10, and object2 equals object1, and object3 equals value 10, well, those were created by the programmer. They're reference types. So what we said was, I want object1, create a new object. We'll say this box over here, this filing cabinet, and in it, put value 10 into this box. Object2 says, I want you to just reference, and that's where the word comes from, reference object1, saying, hey, I want whatever's inside this box. When object3 gets created, it's a new object because we have the new brackets, and it's saying put value 10 in this box. Essentially what we're doing is saying, when we create variable object1, we're storing just a reference, an address to where we're storing the value 10, which is box 1. So we're saying object1, I'm just letting you know that this is the address of all the contents that you want. And that's in box 1. Object2 is saying, I want whatever is in object 1, and we look in object 1, and object 1 just has the information of box 1. So it references that. And object 3 creates a new object, so it's saying, I'm going to put my contents in box 3, and I'm just going to have the address of the box saying box 3. That's right over here. So going back to our example, this makes sense. When we changed object1 value to 15, we changed the contents of box 1. So when we do object2.value, which is referencing the same box as object1, that's 15. But object3.value doesn't change because that's interested in a completely different box. It's box 3. And going back to the first example, arrays, well, as I mentioned in previous videos, arrays are just objects at the end of the day. So when you create an array, it's the same thing, creating a box, a data structure, and this is creating a second data structure. All right, so that is reference type. A very important concept, but I think you get it, right? Let's get to the next one. This gets a little trickier. This one's called context. And context gets confused a lot with scope. If you remember, we said that scope is created when it sees curly brackets, right? We said that if we create a function, as soon as we create that function, there's a new scope that's created. So we can have let A equals A, and that lives within this universe. It doesn't know anything about the root scope, which is over here. So if I do console.log A, well, it's not going to work. Oh, and we need to actually assign something, and we need to name it. So let's just say B. So if I do this, well, console.log A will just return reference error because it doesn't exist. So that's scope. Now, how is context different? Context tells you where we are within the object. Let me explain. If we say console.log this, well, you see, I get some highlighting. And this is the first time we're seeing this. And it's a special word in JavaScript, probably the most confusing word that a lot of people have trouble in. Even people that have been in the industry for years still have a difficult time with this. But let's see what it is. This is, as you can see, the window object. So just to double check, if I do console.log this equals window, I get true. And I can access this dot alert hello. So what this means is, what is the object environment that we're in right now? The best way to think about it is, what is to the left of the dot? So right now I'm able to do alert because I'm inside the window object. So doing window or doing this is the same thing. Now, why is that important? Well, when we get to instantiation, I'll show you why it is. But it's a very important concept that you'll see again and again. But remember, this just refers to what object it's inside of. Two more examples to demonstrate this. One is if I do function A, within function A, we'll say console.log this. So if I call A, what do you think happens? Let's see. Still the window object. This still refers to the function. And if you remember, that's because I said it has to be what object we're inside of right now. Technically, function A, I can go window.a and run the function. So to the left of the dot, well, that's the window. In order to create a new value for this, you have to do something like this. Object A, function A. Now if I do function, and within here I do console.log this, well, in that case, if I copy this and run object for.a, well, now this is the object, which is object 4. So why is that important to us? Well, first of all, you'll see it in other code bases, so it's good to know. But it's really important when we do instantiation. Instantiation is when you make a copy of an object and reuse the code. Imagine you're building a big multiplayer game online. And this game's going to have many players. You can have wizards, you can have trolls, warlocks, elves. Now, if you had to create an object for every single player, that's a lot of repeated code, that's a lot of hassle, and well, that's a lot of your time, and it's not very efficient. To solve that, you can do something called instantiation. You're making instances or multiple copies of an object. So let me show you how we do instantiation in JavaScript. Again, this is going to look a little bit weird at first, just like for loops did, just like functions did at the beginning, but it's just the syntax and you'll get used to it. So let's say we have a player class. Now you see the new syntax already, and I capitalize a class. Now think of a class as something that I want to make a copy of. If I ever want to make a copy of an object, it's a good idea to do something like this so that, well, you'll see how easy it is to copy this now. So we do class player, and within here, we'll say constructor. And I know this looks weird, but again, it's just syntax. Let's give it, this player can have a name and a type. And within the constructor, this.name equals name. And this.type equals type. Oh boy, what just happened here? Constructor, when you create a class, a player class, says every time I'm making a copy of a player, the first thing that gets run is the constructor function. And this constructor function is going to create these properties on the player object. So a name and a type. And now I can create anything that I want for the player. Let's say we want to create a method such as introduce that console.logs with backticks. Hi, I am. And again, we remember the syntax template strings. This.name, I'm a this.type. Awesome. So now I'm saying this player class, any player that I create will always be able to introduce themselves. And they'll also have this name and this.type. And the reason we use this here is that when we create a player, we can access the name and type property. I'll show you later on how that works, but this is just a syntax you're going to get used to. In order to access the player and make copies of it, you'll have to run a constructor, which is all the properties and methods that you want the player to have. You can also create methods that players can have. And anytime you want to access a property within the constructor, we'll use this.name. If I want to use introduce, I'll have to do this.introduce. Okay, so we have a player, but when we're building our multiplayer game, we want to now copy this, but add on to it. Let's say we want to create a wizard player, a player that's a wizard. In that case, we would do class wizard, again, capital letter, extends, and again, it's just the JavaScript keyword player. So what is this saying? I'm saying I want wizard to extend whatever player has. So I want to add on top of whatever player has. Again, because it's a class, we'll have to do a constructor. And this wizard is going to accept name and type. And within here, this is the tricky part. Anytime we extend something, we need to also call the constructor function of the player. We have to do something called super with the properties that we want to pass to the constructor. In this case, name and type. I know this is confusing. is just something you have to do. Whenever you extend a class, you want to use super so that you essentially have access to these. Okay, so let's say that with the wizard, we also want to have a play function. And the play function will just console.log I'm a this type. And now that we have our wizard, what's the power? What's the reason that we just did this? Now we can do this. Instead of constantly creating players and then saying that they are wizards and they can play, now I can say wizard1 equals new wizard, and we'll call the first wizard, again, we get name and type. So we'll say Shelly, and she'll be a healer. And if I want to create a new wizard, I'll just say wizard2 equals new wizard, Sean, and he is dark magic. Whew, that was a lot of new syntax. So let's go through it and make sure we understand everything. As we've learned, let's use console log to really understand what we're doing. I'm going to add a console log right at the top over here. And we'll say this. What is this? I'm going to save. And actually, I'm going to copy this into the console. Let's copy it and see what the console log gives us. We see that we get wizard. All right, let's go through everything here. I say we have a class player, then a class wizard that extends player, and then we have two variables that we created, wizard1 and wizard2. Now, the program is going to see the new keyword, and anytime it sees the new keyword, it says, oh, we're creating a new wizard. And this wizard is going to have two parameters, Shelly and healer. So it's going to go to the wizard class. Again, because it has this new word, it goes to the wizard class and it says, hey, wizard, I want you to extend player. So it's going to go to the constructor and it's going to see this super. And what this does is it takes us up to the constructor of the player and it runs this. And now it attaches this as the wizard. And then it introduces the new function and then adds the play function. Now, if I go to wizard1 and I say play, I get I'm a healer because Shelly's a healer. But I also have access to wizard1 dot introduce. Hi, I am Shelly. I'm a healer. And we also have access to wizard2. Oh, I have to run this again. Let's run this again. And I don't think I copied the second wizard last time. So now I have wizard2 introduce. Hi, I'm Sean. I'm a dark magic. That sentence doesn't make sense, Sean, but that's okay for now. Let's just try something. If I do console log here, and we'll just say wizard, and here we'll say player just so we can distinguish between them. And I'm only going to copy the first wizard so that we don't get two of these running. Again, because we're creating two wizards, we're going to have this run twice. But just for our sanity, we'll run Shelly. So I'm going to refresh and add here. Oh, I forgot to add a comma. And let's refresh. And I get an error. Reference error, must call superconstructor in derived class before accessing this. What that's saying is that in order for me to access this and get this.type, I have to call super, which runs a construction function in player. So that's what super is doing. It sounds kind of weird, but it's just something that you need. I'm just going to put this at the bottom after we call super. And now it should work. Let's see. I get the first player, wizard. So we call super. As soon as we say new wizard, Shelly healer, I go to the wizard extends player. I run the constructor function, which says super. Hey, run the constructor function in the player. And I run that. And that's why we log console log player first. And then we go to console.log wizard and then run the rest of the class. Very cool. Now, just to show you something, this is actually new syntax that you'll see in React, and it was part of ES6. But back in the day, this is how we used to do it. The exact same code I have up there is right here. It's called classical inheritance, and it doesn't look too bad, but you see that there's prototype, which it's another thing that you'll see in JavaScript, and to be honest with you, you shouldn't really use it. It doesn't look very nice. And you see that we have to attach play to both Wizard 1 and Wizard 2, and it just doesn't look as nice as this. And once you get used to everything, it's not too bad. All we're saying is, as soon as we say class, we say, hey, we're probably going to make a copy of this object. So we want to make copies of player, we want to make copies of wizard, and that's called instantiation. When I do the new keyword, I say, make an instance of wizard. And wizard uses some functionality from the player and adds its own little play function as well. Holy moly, that was a lot. Like I said, this is something that you'll have to come back to, and you won't get it right away. It's really hard to fully understand the topic without actually having to use it in real life. Just keep this in mind. Every time you hear somebody talk about reference type or context or even scope or instantiating something, well, these are the things that they're talking about. Objects are really complicated. They're really hard, but with that, it gives us a lot of power. So with that, good luck with the exercises. I'll see you in the next one. Bye-bye. Now that we know how to use arrays, where they're fast, where they're slow, we're going to get into a part that is not crucial for interviews, but it's good to understand how they work and how to build an array. Most likely in an interview, you won't get asked, hey, build an array from the beginning. But I do want to build those foundations for you so that we understand arrays from a fundamental level. So let's build an array ourselves. Now, in this video, we're going to be using the class syntax in JavaScript. So we're going to create an array class. Even though with JavaScript and many other languages, we can just do this and we've created an array. Let's see if we can build one of our own. Because as you'll find out as we go through this course, data structures are simply things that we can build from scratch. We can create whatever data structure we want. We can create our own data structure. The most common data structures are well known and are already implemented in most languages because they're so useful. But you are able to build any data structure you want from scratch. And as you'll find out, most data structures are built on top of other data structures. Now, to get started, we're going to create an array in JavaScript. But just a heads up, JavaScript is a bit of an interesting case. Arrays in JavaScript are just objects with integer-based keys that act like indexes. And that's what we're going to build. Different languages will have this implementation differently, but what we're going to learn here is still going to be applicable to how arrays work in other languages. So we're going to start off with creating a class. Let's start off with creating a class, And we'll call this my array. And within the my array, we'll have a constructor, which is the initial function that will be run when we create this my array. And this constructor is going to have two data points. One is the length property, because with an array, we're able to determine the length of the array. And the initial length will be 0. That is how many items the array has. And then we'll obviously have the data within the array. And this is going to be an object. Now, what's the most common action that we have in an array? Well, it's the access, to access the data. So let's create a get method. And this get method is going to take an index to actually grab the data from memory. So I'm going to just say return this dot data. And if this keyword is confusing to you, make sure you watch the previous video. This dot data is just referring to this data that we've created in the constructor. And we're just going to return the data at the index that we're requiring. Let's see how this would work in action. To create a new myArray, all we need to do is say const new array. And we use the new keyword in JavaScript to instantiate this, or create a copy of this class, like this. So now if I do console.log new array, and I click run, I get my array that has property length of 0 and data that is empty. If I do new array dot get 0, index of 0, I get undefined. Well, because there's nothing in this object. We have no items. And JavaScript automatically has the type undefined when, well, there's nothing. Let's add our next method. That is the push method, to add something at the end of the array. So I'm going to create a push method, and this method will take in an item that we will give it. And within here, we'll simply add this to the data of our object. It's going to add it to the length of our item. So because we have 0 items and the length is 0, this is going to add the data at this.data 0 index. And the 0 index will simply now contain the item. And because we want to keep adding items if we wanted to, we will say this dot length plus plus, because now our array has a length of 1 instead of 0. So that next time we run the push method, this dot length will be 1 and the new item will be added at index of 1. And let's just return this dot length for now, because the typical push method in JavaScript will usually return the length of the array. Let's run this and see what happens. I'm going to say that down here, we'll have new array dot push, and we're going to push high. If I run this, I see I have my array, length 1. Data is going to have a property 0 of high. Nice. What if we add another thing? Let's do new array dot push, and we'll say u. If I run this, I have length of 2 now with index of 0 at high, or index of 0 has high, and the index of 1 has u. Very cool. What else can we do? Well, let's add the pop command to remove the last item of the array. Once again, we have the pop method that doesn't receive anything. We don't need to pass it a parameter. all we need to do is delete the last item in the array. We can simply have a variable, let's say last item, that grabs the last item in our data object. So this is going to just simply be this.data at index of length minus 1. Remember, we want the index of 1. Even though the length is 2 because we're counting 0, 1, we want the last item in the data. And from here, we can just use the delete keyword in JavaScript and say this.data at this.length minus 1. Just delete that item. And obviously, we need to decrease, so just shorthand here in JavaScript to decrease the length of our data by 1. And then finally, we can just return the item that we deleted. So now if I run another command, and by the way, you might see here that I've missed the semicolons in JavaScript. Most of the time, you can get away with not adding semicolons, and some people don't use semicolons at all in JavaScript. Don't get too distracted by that. Sometimes I forget, and it's not really important, at least for our purposes. Let's add a new item to the array. That's going to be the exclamation point. And I'm going to say my or new array.pop. If I run this, I get an error saying item because this should be last item. There you go. Let's run that again. And we see that it's hi u because the exclamation mark has been deleted. If I run pop again, I see that I have length of 1 and only hi remaining. Very cool. All right, let's add one last one. And to show you why some operations in arrays are O of n, we're going to add the delete method. And the delete method is going to take an index, which item we want to delete. And in here, we will have to do a const item. So we're going to create a reference to this.data index, which is the item we want to delete. And how are we going to delete this? Because remember, in an array, we'll have to delete the item, then shift the index of all the other data types by 1. Well, because we want to follow good coding practices, using the idea of single responsibility principle, let's add another function that does this for us, that does the shifting of data for us. I'm going to create a new method, and we do this in JavaScript using the this syntax, shift items. And this method is going to take the index that we received here in the delete. Now, this shift items, we can create it here and say that shift items method. And by the way, I use the words function and methods interchangeably sometimes. Method simply means it's a function within a class. So this shift items will be a method of my array. But it is a function. So this function, which is a method of my array, will have the index parameter passed into it. And this is where we do some fun things. We're going to have to loop through the items. So that's a for loop, which right away should ring the bell and say, ooh, this is an O of n operation. We're going to have an index of 0, or I of 0. Actually, instead of 0, remember, because we want to shift items, not all of them, just wherever the index starts from, we say index. And now, I will have to be this.length. So I is less than this.length minus 1. And we're going to increment I by 1 each time through the loop. Within this loop, all we're going to do is say this.data, our data, at each index that we loop through is going to equal this dot data at I plus 1. What just happened here? Well, we're saying start at the index that we want to start the delete from and iterate through it all the way until the end. And within this loop, I want you to take each item in the data that we have, and instead of what it had before, I want you to add the data that is right next to it at plus 1. So if we had an array that is 0 and 2, I'm saying from the index of 0 over here, I want you to now instead make 0 equal to 2. So index of I plus 1. So we're shifting the items to the left by 1. So we have shifted here all the items 1 to the left. And because we did that, the index that we gave it for the delete automatically gets replaced because that I is going to get replaced. Now, there's an issue here, right? Because now the very last item in the array, that is this dot data at this dot length minus 1, which is the last item in the array, will still exist. We've shifted everything over by 1, but we've never touched the very last item because we stopped when I is less than this dot length minus 1. So this is still full. So I'm going to comment this out and just show you what happens if we just leave it like this. I'm going to run the new array dot delete, and I'm going to remove the pop commands for now. And in the delete, I'm going to say I want to delete the U item. So that's index of 1. If I run this, I get hi, U is deleted, but then I have exclamation mark at index of 1, so the shifting is working. But at index of 2, I still have the exclamation mark because, well, we never deleted it. We've shifted everything once over, but we never touched index of 2. So all we need to do to get rid of that is the delete keyword to delete the last item, and obviously to decrement our length. Because we've just deleted an item, we can do this dot length minus minus. If we run this now, hey, look at that. Length of 2, hi, exclamation mark. Let's play a little around to make sure everything is working here. If, let's say, I add a couple more push commands here, and we'll say here R, hi, U, R, and then let's say nice. If I run this, I get hi, exclamation mark, R, nice. That doesn't make sense. Let's change this to 0 to remove the hi. If I run this, I get U, exclamation mark, R, nice. That still doesn't make sense. Let's remove the exclamation mark so that we only have U, R, nice. I'm going to run the new array, and we can delete index of 1, which is the exclamation mark, and let's see what we get then. If I run this, I get U, R, nice. Awesome. Now, you might look at this and want to add your own methods. You might want to, let's say, in here, return the last item just as a reference, which is how it works in JavaScript. But I think for now, you have an understanding of how arrays work and how they're implemented underneath the hood. We have simple O of 1 commands, which are really, really nice. But as soon as we have to start shifting indexes and changing things around, we have to loop over things, which makes it O of n, or linear time. I'm going to leave this for you as a playground after this lesson. So you can add your own things, maybe write it in different languages, and explore a little bit more into arrays. But this video is already getting long. I don't want you to get too bored now, so I'll see you in the next video. Bye-bye. Welcome back. I wanted to add a quick video to let you know about a common interview trick. We're going to be doing some array questions after this, but in interviews, you should treat any string questions, like over here, as an array question. You see, strings are simply an array of characters. Most of the time in an interview, when you get a question like reverse a string, what you should be thinking is to convert this into an array, do some sort of a loop on it or an operation using something like a split method in JavaScript, and then returning it as a string after you've finished the operations with them. So that is a very common interview question where you're manipulating strings. Just keep that in mind, and we'll actually demonstrate this in the next video when we do a very common interview question. I'll see you in that one. Bye-bye. Welcome back. Let's get into some fun interview questions. We're going to start off with a very, very common one, and it shouldn't be too complicated to start us off. The interviewer asks you, can you create a function that reverses a string? So if you passed into this function right here, hi, my name is Andre, it should return this gibberish that is, oh, and I forgot M here, this gibberish that is, well, backwards. It's just simply reversing a string. Now, I want you to go ahead and try this in your own REPL.it or whichever text editor you use and see if you can think through the problem, use what you know about arrays to solve this. Now, keep in mind, when it comes to questions like these, there are many ways to do things. As programmers, we know this, right? There are so many ways to solve a problem. And depending on our style, our knowledge, and time, we're going to come up with different solutions. So if your answer is different than mine, well, that's not the worst thing. What you want to be able to do is to think through a problem and understand why you made those decisions. So go ahead, reverse a string, and I'll see you in the solution video. Bye-bye. Welcome back. Now, I'm not going to go over all of our steps that we used in the section where we talked about how to solve problems and how to talk through your problems in front of an interviewer. And we even watched that Google video of all the things you need to do. Because that's going to take way too long of a time, I'm going to speed things up and just talk about the key points of how you would solve this problem. Well, in order to reverse a string, the first thing we want to do is some sort of a check of our input. We can't just assume that we're going to always receive a string. What if somebody calls the reverse function with, well, undefined or with a number? What happens then? And a good thing to always start off with is to check the input. In my case, I'm going to do a simple check. Let's say that if there's no string, so that is undefined, or perhaps that the string.length is less than 2. That means, well, if string.length is less than 2, that means I'm just receiving one letter or no letters, in which case we don't really need to do any operations. It's already kind of reversed. And we can add different input validation here, such as using the type of keyword in JavaScript to check if it's a string type. But that's something you can just do on your own. Actually, let's implement it since we're here anyway, just to show you. So I can say type of string if it doesn't equal string. Type of str, which is the parameter we receive, doesn't equal the string type. Well, in that case, we can just return That's not good. Otherwise, let's do some operation. To reverse the string, well, let's think about this. We want to convert it into an array. So I'm going to create a backwards array. And this is what we're going to return from the function. I'm going to return the array that is reversed, but we want to return a string, right? It reverses a string. This should return a string. Even though we're going to convert whatever we receive into an array, at the end, we want to turn it back into a string. So in JavaScript, we can do the toString method or the join method. And we just say join all the items in the array. Now in here, we're going to grab the length of the array or the string because we're going to be using it a lot and we don't want to have repeated code. So I'm going to say length minus 1 is how many items we have in the string. Or maybe we should name this items number. Or actually, total items. That's a better name. Now, these total items, so we're going to loop through our string. We'll say let I equals to the total items. So I is going to equal however many characters we have in our string. And we're going to keep going until I is equals to 0. And all we're going to do, because we want to go from back to front, we're going to decrement this. So we're going to go from the length of the string all the way back. So we're going to start off with I, E, R, D, and A, and insert those into an array that we've created, the backwards array, one by one. So in this loop, all we're going to do is say backwards dot push each item that we're going to create. So str I. And I know what you're thinking. Whoa. Why didn't we just convert the string into an array? You told me all about converting strings into an array, and we didn't really do that. And JavaScript actually has the str.split, or we can run the split command to split things into an array. But with JavaScript, we can actually just use strings as arrays and access each property like this with bracket notation so that they essentially are arrays. So we don't have to run any split commands. This also works. And all we're doing is we're going backwards one by one and pushing each item of our given string into our array. So if I console log here before we run the join command, the backwards array, and I run reverse, and let's reverse this string. Let's run this. Oh, and you may have noticed that this length didn't really come from anywhere. It should be total items. So this is the total items. This is the problem with live coding. I try to show that everybody makes mistakes, even myself. And it's good because this way you think through the problem. And these total items, remember, we want to keep going as long as I is greater than or equal to 0. So if I now run this, hey, look at that. We have an array with all of our backwards items right in here. And you see here that the return value that we get is the backwards string that we received because we join it at the end. Very cool. I hope you got that answer. Or maybe you have a better answer than me. because what I did here is not necessarily the cleanest way. And depending on which programming language you use, you might have built-in methods that simplify this step. Let me show you what I mean. In JavaScript, for example, we can use some built-in methods that come with arrays to just simplify this whole thing and make our code a lot more readable. Let's create a new function, and I'm going to call this reverse2. And this reverse2 is going to, once again, receive some sort of an input. I won't do any input validation for this one. You can just assume that we can just copy and paste it here. But in here, we can do a simple return statement, grab the string, run the split command, because this time around, we're not going to access the I like we did up here. We're going to convert it into an array so that we can use a built-in method that comes in JavaScript arrays called reverse. And this reverse does what we just did here for us. And now we just join it at the end. So by using a built-in method called reverse, I avoided all this work. How nice is that? Let's see if that works. I'm going to say reverse2, going to run, and look at that. It's still working. What about another solution? Again, many different ways. And let's say the interviewer says, is there a more modern, cleaner way that you can make this function? And because in JavaScript there's the new ES6 syntax, you can even create a one-line function, call it reverse3. That's going to take a string, and it's going to do string.split. And again, do the exact same thing using arrow function this time around. And this should still work the exact same. Look at that. And if you want to get fancy, you can again use a new feature of JavaScript, which is destructuring, or not destructuring, this is the spread operator. If I run this, we no longer need the split. I can run this and I get the same thing. Again, I just want to demonstrate to you that there are many different ways to solve a problem. And an interviewer is not going to reject you for a job just because you implemented it this way versus this way. It depends on how you deliver your solution. And this is something that we talked about in our How to Solve Problems section. How you want to talk through the problem, explain to the interviewer why you did. And as long as you understand the pros and cons of each solution, that's what makes a great engineer. I'll see you in the next one. Bye-bye. Welcome back. It's time to do another fun array interview question. An interviewer asks you, given two arrays that are sorted, can you merge these two arrays into one big one that's still sorted? So if I have a function called merge sorted arrays, and I give it two parameters with two sorted arrays, can you make it so that it returns 0, 3, 4, 4, 6, 30, 31, as you can see, completely sorted? Let's see what you can come up with, and I'll see you in the solution video. Bye-bye. Welcome back. It's time to sort some arrays. Let's grab this function, put it at the very end, because hopefully it will work at the very end, and start writing our code. We'll start off by first defining the function called merge sorted arrays. It's going to take the first parameter, which is the first array, then the second parameter, which is the second array. I'm going to first define some variables that we're going to use throughout the function. The first one will be a constant, which is merged array. which will be our answer. For now, it's going to be an empty array. And we might as well just make sure that we return this merged array at the end. Hopefully it all works and we can populate this with these two arrays. Now in here, I want to grab the array1 item just for reference, and this is going to be our very first array item. So this simply has the 0 item here in our first array. And then we'll do the same thing, array2 item, which is going to grab the number 4 from here. Now, the very first thing I like doing in a function is checking for some sort of an input, making sure that everything works. I'm going to spare you the time of me doing this because you should have an idea of how to check whether it's an array, whether you have two parameters. But the one input that I think is worth checking is, what if we have something like this, where the second array is just an empty array? In our case, we can just return the first array because, well, it's already sorted. We're still merging the two arrays, but the other array doesn't have anything. And that's the same if this first array was just empty as well. So to avoid any extra work, let's check for those conditions so that right away we can give out the answer and make our function more efficient in those cases. So I can just do an if statement. I'll say array1 length. If that is equals to 0, so if first array is empty, just simply return the second array. And we can do the same for the other case. If array2 length is empty, then we can just return the first array. Nice and simple. But now let's get into the harder topic, which is what happens if both of these arrays are full, like they are now. Well, just to change things up, because I've been using the for loops for a while, I'll use the while loop in JavaScript. And this simply says loop through the items while a condition is met. In our case, I'm going to say while there is an array1 item, or there is an array2 item, do something. And remember, these variables are simply, for now, the first item in each one of the arrays. And by the way, if you're wondering why sometimes I use const, sometimes I use let, well, const means that once I assign this variable to this array, I can't modify it. I can't say merged array equals to 2. It's going to give me a warning because it's a constant. I can add things to the array, but I can't change this reference to the array. On the other hand, let allows me to do that. So later on, I can say array1 item equals to something new, like array1 in the index of 1. So that is why we're using this syntax. It's a new ES6 syntax in JavaScript. All right. So while we have things in the arrays, we want to first do a bit of a check. Let's say if array1 item is less than array2 item, that is, if 0 is less than 4, we want to add to the merged array, empty array, we want to say push, and we'll push the first item in the array. So we're going to push 0. And because we've now pushed the 0 item into this array, we don't really need to worry about 0 anymore. So we can just simply say array1 item is now going to equal array1 at index of 1. Right? Because now we want to move to array item that's over here at index of 1, which is 3, so that we can compare 3 with 4. Now we want to increment this every time, and because we are doing a loop here, let's convert this into an index that is I, and increment it I++. And at the top over here, we can just say for the beginning that I is going to equal 1. So that way, as we loop through this, this is going to increment with I++, so that is increment by 1, so that we can go 0, 3, 4, 31. And by the way, I just noticed that I can't spell. This should be array over here. All right. Now that's the case when array 1 item is less than array 2. But let's do the other side. If array 2 item is less than array 1, we now merge into the array 2 item. Because if array 1 item is not less than array 2 item, we don't even need to add a condition here. We know that array 1 item is greater than array 2 items, in which case we can just add the second item. So that is, we add this item instead. And again, we want to do the exact same thing that we did with the first item, or the first array. That is, the array 2 item is now going to equal array 2, and we need a different index of this. We can't use the same one, right? So we can just say this is going to be j, and up here, we simply do the same thing. J is going to equal to 1. So once we figured out the 0 index items, we can then move on to index of 1, then index of 2, index of 3, so on and so forth. Now let's check this code and see if it works. If I run this, you'll see that my browser just crashed. And that's because I have a setting on REPL.it which allows for this to happen. Most likely, if you're using the default settings here, it will give you a warning. But let's go back. Why did that happen? This is why it's always a good idea to go step by step and make sure things work. We did a lot of coding here without actually testing if any of this works. So a good note here is to pause every once in a while and just test your assumptions, log out the answers. In this case, we missed a critical point. That is in this check over here. If we do the while loop as long as array 1 item or array 2 items are populated. And we check here if array 1 item is less than array 2 item. But the problem here is that we could have a case where one of these, because we're using OR, could be undefined or we reach the end of the line. In order to account for that, the critical thing to do here is to always know how your code is running. So let's do a console.log here. Say array 1 item, and then array 2 item. Let's see what we get throughout the loop. If I run this, it's going to crash again and we won't be able to see our logs. So I'm just going to write down the correct version here and then explain why we did what we did. I'm going to just say if array 2 item, if the array 2 item doesn't exist, so if we have undefined, it's going to turn this into true, so we run through this. What is that? Let's have a look. Notice what we just logged here. We've logged array 1 item, then array 2 item. So this is why we're comparing throughout our loops. 0 and 4, then 3 and 4, then 4 and 4, then 4 and 6, then 31 and 6, 31 and 30, and then 31 and undefined. You see here how the second array item becomes undefined. And in order for us to bypass this undefined, which becomes undefined define here, and we use the exclamation mark in JavaScript to turn this into a true statement. So it turns into this so that we can add the 31 in array 1 into the final slot of the array. Now, if this was like this and I run, we get undefined for the first array. However, because we're doing this second check, which is array 1 item less than array 2 item? And in our case, if we do undefined less than 6, which is what we're doing here in this comparison, if I run this, and let's console.log this to see what the answer is, I get false. So even though in this time around, array 1 is undefined because we've gone through it, because this statement is false, we go to the else statement and fill the rest of the array with 6 and 13 or 30, which come from array 2. Now, I wanted to point this out to you because this may not be the cleanest solution, right? I mean, looking at this code, just think about what I had to explain and draw out for you to fully understand how this works. And I did this for a specific reason. During the interview, if you have to explain things in detail like this and write things out, well, perhaps there's a better way of writing it. Because an interviewer is going to get confused as to what this means, then what this means, and it doesn't really read like English, does it? Ideally, these functions are really, really nice to just read. So perhaps I can take this part of the function and convert it into its own function and just name this as should push first array item. And this should be should push array 2 item. And by extracting out these pieces of code into their own little function, you can clean out this answer and make it more readable. And interviewers are going to like that. Now, during an interview, you may not have time to do so, but you can let the interviewer know how you wrote the solution and you understand that this is probably not the most readable solution. And this is what you would do to clean it up. You don't have to actually code it. As long as you tell them and you understand where you would improve things, that in an interviewer's eyes is just as good as you actually coding it that way. All right, looks like this is working. If I do an empty array here, I see that it's still working. Our answer is looking good. Hope you got this far. I'll see you in the next video. Bye-bye. It's time to celebrate because you just finished your first data structure. And they're going to get more and more fun. But you see here that we've started to complete our mental model of data structures. I promised you that by the end of this course, this whole diagram is going to make sense. And we've finished a small part of it. The arrays. We talked about static and dynamic arrays. We talked about the big O complexity and how dynamic arrays can sometimes have O of n appends because, well, sometimes we have to double up or expand our memory. We also talked about how strings and questions regarding strings can be treated very similar to array questions, where you just convert them into an array and then join them back up and return a string answer that you need. And there's a few other points for arrays that we're going to talk about when we get into algorithms. But by now, you should take a look at the Big O cheat sheet and understand why the array data structure has these big O numbers, and understand when an array is a good thing to use. One thing that you'll note when it comes to arrays, especially when we get to algorithms, is that they're really, really good at having sorted data. When it comes to sorting, arrays are awesome because they're in memory in sequential order according to their index. Now, before I go on to the slide, you can pause the video, think about when you would want to use an array, when you wouldn't. Because in about 5 seconds, I'm going to show you the pros and cons. So pause the video and the answer to when you should use an array. Well, here it is. Arrays are great for fast lookups. That is just accessing information where you know which index you want to look up. It's really fast at push and pop. So adding things at the end of an array or taking things out at the end of the array. And of course, because it's ordered. Having something that is ordered and close to each other in memory makes it really fast. However, it has slow inserts and deletes because we have to shift arrays whenever it's not at the very end of the array. And then finally, if using static arrays, it's fixed size. That means sometimes you have to declare the memory ahead of time and how large of an array you want. But that can be avoided if we use some of the more modern languages that have dynamic arrays. Also, I just realized that this smiley face kind of looks like a crazy person, but this is meant to be good. This is good. This scary little icon, that's bad. Okay, I think we get it now. We're going to come back to arrays because a lot of other data structures we're going to talk about later on, like queues and stacks, are related to arrays. But for now, I want to get into other data structures because we still have a few to go through. I'll see you in the next one. Bye-bye. It's time for our next data structure, hash tables. Hash tables, or hash maps, maps, unordered maps, dictionaries, objects, there are many ways to call this data structure. And different languages have different names for it and slight variations on the hash tables. Objects, for example, in JavaScript, are a type of hash table. The reason I'm starting the course with arrays and objects, or hash tables, is because these two are the most common interview questions. You're going to use them in any coding question. Me personally, I have yet to be part of an interview that you didn't have to know these. They are an absolute must. Now, luckily for us, pretty much every language has a built-in hash table, just like arrays. In Python, they're called dictionaries. JavaScript, as we said, are objects. Java has maps, and Ruby has hashes. And hash tables are very important all across computer science. You see them a lot in databases, in caches, and they're extremely useful. So what are they? And also, you may be wondering, what does the name hash table mean? Where did this name come from? Well, let's look at an example. Imagine you're going grocery shopping and you have an object here, basket, and you want to add grapes as the property of the basket object. Again, we're using JavaScript syntax, but this should look familiar to you. So we want to set that basket.grapes is going to equal 10,000. We're buying 10,000 grapes because you can never have too many grapes. Now, first off, thinking about how we would store this with arrays, it would be a little bit more difficult, right? In an array, we have an index that's numbered and a value. With a hash table or an object, we get to set a key, which is grapes, and a value. So we get to set a key value pair. So right away, we see some benefits in here. Now, a way a hash table works is we have the key, which is grapes. And this key is used as the index of where to find the value in memory. Remember, with arrays, we had the index, which was a number. But with hash tables, we use grapes as a way to find it in our memory shelf. This is done this way, with something called a hash function. But for now, we'll just assume this is a black box. We don't know what's going on here. All that's going to happen is we're going to pass grapes into this black box. This black box is going to do some magic, and out of it comes a key into an index where we want to store this value. So now our 1,000 grapes can be stored in this memory address, 711. And technically, it actually stores both grapes, the key, and the value of 10,000. Here, I've just simplified it to 10,000, just so it's a little bit cleaner. But keep in mind that it's going to store both key and value, and I'll show you a diagram showing this later on. So this black box over here gets to decide where to put the data on our memory in our computers. But you might be wondering, what is this thing, and why does it get to decide where to put all this information? For that, I'll see you in the next video. Bye-bye. What is a hash function? It's something that's used all across computer science. A hash function is simply a function that generates a value of fixed length for each input that it gets. All right, what does that mean? Well, I have here a MD5 hash generator. MD5 is the type of hash function, and there's many types. You might have heard of SHA-1, SHA-256, and many others. Using this hash function, let's see what happens if I do hello. You see that right away, MD5 hashes this string and turns it into this gibberish. That's what a hash function does. We give it an input, and the function generates some random pattern. Now, there's some key aspects of hash functions. First is that it's one way, in the sense that if I give somebody this, they have no idea what the input was. And it's practically impossible for me to have any clue as to what the input is. The second is that no matter how many times I put hello in there, it's going to be the same. But as soon as I change one thing, it's going to completely change the output. If I go back to hello and watch me just change to capital H, even a capital letter, so it starts with 5D4. If I do capital H, it's completely different again. And looking at this, we can at least say that, I don't know what this is useful for, but the one thing that I know is that no matter what, if I give it the same input, it's going to give me the same result, but I have no idea how to convert this back into hello. This is what we call idempotent or idempotent. There's different pronunciations. I'm not really sure which one's which, but it is a fancy way of saying that a function, given an input, always outputs the same output. Now, the one benefit and why we would want to use this in a data structure is that we get really fast data access. Because all I have to do to find grapes, or basket.grapes, is to pass grapes into something like an MD5 hash. It generates this number for me, and I immediately know where it is in my memory on our computer. But this doesn't look like an address, does it? Technically, a hash function that we use for hash tables is going to take grapes, generate some sort of gibberish, and then convert it to an index space or an address space that it has based on this number. You see, unlike arrays where we just had ordered indexes, with hash tables, all we need to do is give it a key and we know exactly where that item is in our memory. But you might be wondering, this black box hash function, doesn't it slow things down? Because every time we want to add a property and a value, grapes and 10,000, to a hash table, we have to run it through the hash function so we can decide where to put it in memory. And if you've noticed that, good job. That is a big factor. You don't want this to take a very long time because, well, every time you add a property to memory or retrieve a property to memory, because again, both times we're sending the key grapes into the hash function to find where to get it from. We need this to be really, really fast. And underneath the hood, remember, because hash tables exist in all languages, they're implemented with an optimum hashing function that's really, really fast. As a side note, hash functions like SHA-256 take a really long time to generate a hash. And it is an overly complex hashing function that is used a lot in places like cryptography, where you want this to take longer, but that is outside the scope of this course. If you're interested, I do recommend that you check out the differences between these two. To review, we have a key that is grapes. We send it through a hash function that is going to hash something really, really fast and then map whatever the hash came out to be into a memory address where we want to store our data, our grapes 10,000. And when it comes to hashing functions, you typically leave this to whatever framework or language you're using. And we usually assume a time complexity or big O notation of O1 because this happens really fast. All right, now that we understand what this black box does, let's talk a little bit more about hash tables, why they're useful, and why, in some cases, are better than arrays. Looking at hash functions, we can start to think about what actions they perform and how fast it can be done. When it comes to inserting something in our memory space, well, it's going to be O of 1. We hash the key, such as grapes, through the hash function and places it automatically into the address space that it comes up with. Lookup is the exact same. We access the property. That property is going to get hashed and direct us exactly to the address to find the values. What about deletes? Same thing. We simply use the key. Right away, we know where to delete the item from. And because it isn't ordered, we don't have to shift indexes like we did with arrays. Everything is just nice and simple. What about searching? If we want to find something in our basket, like apples, well, that's easy too. We simply use hash functions. If we go to our playground, in JavaScript, I can create an object. Let's say let user, and this user will have property of age 54. Let's say that the name is going to be Kylie. Magic, well, let's say Kylie does have magic skills, so we'll set it to true. And for fun, let's say that the scream is a function that will just console.log a scream. That was not the strongest of screams, but I don't want to scare people around me. When I run this, I've created a user object, and the age 54, name Kylie, magic true, scream, and this function are all going to get placed somewhere in memory at different addresses. But I can access this really, really fast. I can say user.age, which is going to give me 54 at 01 time. Perhaps adding a new property, I can just simply say user.spell is going to equal abracadabra. And if I run this, and let's just check out what the user object gives us, we see that we now have the spell abracadabra added. This again is access of 01, is O of 1 because we take it through the hash functions and the computer decides where to put both spell and abracadabra in memory. And if I run user.scream, same thing. Oh, I cannot spell scream. Same thing. I get to access this function in memory really, really fast at O of 1. How amazing is that? And I know what you're thinking. Hash tables are amazing. We should be using them all the time. And you're right, we should be using them in a lot of cases. But as we know, there's always pros and cons. Now, let me talk to you about one of the main problems with hash tables. And I have a nice visual to demonstrate this for you. I'll link to this in this video so you can play around with it later. I have a little animation here where we have 12 memory spaces. Remember, our computer has limited space. And when we create an object or a hash table, the computer decides how much space to allocate. It's not going to allocate all the space to the hash table. It's going to allocate a bit of it. And I'll show you later on when we implement our own hash table how we can adjust the size. But seeing that there's only 12 spaces, you can imagine if I insert here, let's say 1. Let's see if I can make this bigger so you can see it. Yeah, there you go. I'm going to insert, let's say the number 3 gets inserted here. Let's do 55. Insert it. Ooh, what happened there? Did you see that? The hash function randomly assigned a space in memory and put it in 3. Uh-oh. Remember, there's nothing telling the hash function to evenly distribute until everything is full. Although hash functions are optimized to try to distribute this data all over, it also matters what we put into it. So when 55 gets hashed, well, this hash function generates the address location of 3 to put it in. And because we already have 3 there, it does something funny here. Let's keep adding here and see what happens. I'll add 2, maybe add 12, and finally add 14. Uh-oh, it did the same thing again. And what we just noticed here is something called collision. And a collision looks something like this. We have the keys. Let's say we're inserting the name and the phone number of a user. And we initially place John Smith. This key gets hashed, gets placed in the address space of 152, and gets stored. Remember how I said it actually stores both keys and values? It stores in something called buckets John Smith with the value, that is its phone number, right here. And then we keep going with Lisa Smith, then Sam Doe, then Sandra. Oh no, as soon as we hash Sandra D, it becomes the same address space as John Smith, and we have a collision. And because of this collision, we need a way to store both users somehow in this address space. And something funky is going on here with this little circle and then a point and Sandra D. And just a hint here, this is actually a new data structure that we're going to learn about called linked lists coming up. You see, with hash tables, we can't avoid these collisions. With enough data, with limited memory, we're always going to have this collision. So there is a possibility, if we go back to our example, and I refresh here to start from scratch, that we constantly just add, despite our hash table that's really, really fast, constantly just keep adding to the same memory space, which slows down our ability to access or insert information. Because now, if I want to check what's in this address space, I have to go 1, 2, 3, 4, 5, and so on and so forth. Theoretically, when you have a collision, it slows down reading and writing with a hash table with O n divided by k, where k is the size of your hash table. And remember, because we remove constants and simplify things, it becomes an O(n) operation. Now, collision will likely happen in any hash table implementation. And luckily for you, you're never going to have to really implement it yourself. And it's not a very common interview question, but you do want to know about it so you can talk about it. There's two common ways to deal with these collisions. I showed you one of them with something called linked list, which we'll talk about later on. But if we go to the hash table Wikipedia page and look at collision resolution, you can see that there's a ton of different ways to solve collisions. The way that I showed you is called separate chaining, but there's different methods like open addressing and Robinhood hashing that you can read about if you're really interested in the topic. The point I wanted to make is that there is a bit of a downside. When we talk about fast lookups in hash tables, occasionally, depending on the hash function, it might take O of n. All right, let's keep going and expand our knowledge of hash tables in the next video. Welcome back. Now, hash tables are implemented differently in different languages, but most of the time, the key and the value can be any type of data structure. We saw here that we can have a function as a value. We can have another object if we want as a value. We can have an array as a value if we want. And I mean, you can do this in arrays as well. We don't just have numbers and strings in arrays. We can have arrays of objects. But you can also sometimes have keys that are more than just strings. You could potentially have functions as keys and a value that is also a function, or perhaps a number or an array, whatever you want. Now, in JavaScript, in an object like this, if you pass a key that is a number or a function, it actually gets stringified and it only allows string keys. But with the new version of JavaScript and ES6, you actually have something called map and sets, which also may be familiar in other languages. A map is created like this. And the difference between a map and an object is the fact that a map allows you to save any data type as the key. Remember, with an object, you can only save the key as a string. With a map, it allows us, if we want, to even have functions as keys or arrays as keys. And another benefit of map is that it maintains insertion order. What does that mean? Well, with an object, there is no order, is there? If we go back to our diagram, our data is inserted randomly in different places. If we go back to our user's example, we see that there is definitely no order. When we grab all the values of an object, we start with, let's say, Lisa Smith, which was entered second, then John Smith, then perhaps Sandra D. Sam Doe gets selected last. There is no order like there was with arrays. But there are some versions of hash tables, like maps in JavaScript, that maintains this order of insertion, so that when we loop through items in an object, we have this maintained order. Sets is another feature, very similar to map. The only difference is that it only stores the keys, no values. So you see here, Each language, as we mentioned, comes with its own pre-built versions of data structures. But at the end of the day, all of them are hash tables. But in order to truly understand how hash tables work, I think we should build one. In the next video, we're going to do just that. Welcome back. It's time for us to implement our own hash table. But let's do a bit of an exercise. And this may be difficult, so don't get upset if you are not able to finish it. After this, I'll provide a solution video and we'll walk through it. But as an extra challenge, I have created a template for you. A new hash table that we're going to create. Yes, I know JavaScript already has objects and we can just simply create one like we've seen before, but what's the fun in that? Let's create our own. Now, this hash table has a constructor that will receive a size. So when we create this hash table, we're going to give it a memory space size of 50. Let's say that we only want 50 shelves of memory. We're going to create this .data where our data will live. And within it, it's going to create a new array. And this array is going to hold our information for us. So we would have something like grapes and 10,000 as our bucket. So the first item in the array will be an array that is grapes 10,000. Remember, if we looked at the diagram, we have these buckets that our data lives in. And because right now we're implementing our own hash tables, we're using array instead of objects. But the idea is that using a new method that you'll have to create, which will be called set, you're going to be able to set grapes as the first index in the array and the number of grapes as the second index in the array. And from there, we can have another method, get, which retrieves the grapes and returns 10,000. Now, you're probably wondering, oh boy, what is this gibberish? And I wrote this ahead of time for you because it's not really important as part of the course. But remember, we need a hash function in order to create a hash table. And I've created here the smallest, tiniest hash function you can think of. We're going to talk about what this actually does in the solution video. For now, all you have to know is that it's going to just generate a hash for us. For example, if I do underscore hash here and give it a key, so let's say that I want to insert grapes and I click run, I get 23. If I click run again, I always get 23. If I change grapes to 2 S's, I get a different memory space. If I just type in randomly here, again, I get different memory spaces, all from 0 to 50. So your challenge here is to create these two new methods, set and get, that adds to this .data and retrieves from this .data. Again, if you're not super familiar with JavaScript, this may be hard, but give it a try. And in the next video, we'll walk through step by step. I'll see you in that one. Bye-bye. Welcome back. It's time to walk through our own implementation of hash table. Now, before we get started, I do want to mention something that you may be wondering about. That is this underscore over here. What does that mean? In most other languages, like Java, when you create a class, you can have private properties. That is, properties that I can't access outside of this class. So I wouldn't be able to do my hash table underscore hash and access this property or method. Now, with JavaScript ES6, that's not really possible. And there is a common standard, which is to put underscore here in the JavaScript world, which says this is a private property. Now, this is just meaningless, really. I can still access the hash method, but it is a developer standard in the JavaScript community to let other developers know that, hey, you shouldn't be accessing this, even though you technically can. And there are ways to make it work and have private properties, but it requires things like closures, symbols, or weak maps, which, again, is beyond the scope of this course, and we don't need to worry about. So that's where the underscore is coming from. We're not usually going to access hash function like this. All right, now that we got that out of the way, let's talk a little bit about what this does. If I enter in here grapes, we first create a new variable that is hash, that is equal to 0. And then this key, we're going to grab the length of grapes. So that is 1, 2, 3, 4, 5, 6. And we're going to add 0, which comes from the hash, plus key character code at. And character code at in JavaScript simply gives us an integer between 0 and this number, representing the UTF-16 code. So that's just an encoding. It's pretty much saying, give me a character code, because remember, in memory, a string or a letter is represented as a number. So this method allows us to say at index whatever we put in the parameter. So let's say we're looking at index of I, the very first one will be G. We're going to get the character code for G, that is a number. We multiply that by the index again, just to make sure it makes it unique. And then we use what's called the modulo operator to make sure that this stays within the length of 50, the size of our data. And then we return the hash. An easy way to see what's happening here is to simply console.log hash. If I run this, we see that it's going to loop through our grapes character by character. It's going to generate some sort of a hash. And because this hash gets constantly looped over, we include whatever the generated, let's see, the first one is 0. It's going to say 0 plus whatever this is. Then the next iteration, hash is going to equal 14 and generate something else, which is 8, and keeps going until we get 23. You can take your time and go through this code if you really want to. Again, this is not the focus of this video, so let's move on. Using our hash function, let's do our very first method. Let's create the set method. This set method is going to receive a key and a value. And just so we can see this and what's going to happen, we'll run this method here saying we want grapes to equal 10,000. Lots of grapes because they are delicious. If I run this, I get undefined because, well, this isn't really doing anything. The first thing we want to do is to create a variable called let address, which will represent where we want to store this information. And we'll say this dot hash key. So all we're saying is store this data that we're going to insert, the key and value, in this address space that is created by our hash function. And we give it the key of grapes. Remember our little animation. We're sending the grapes into that magic little blocks. That is the hash function. From there, we simply say if this dot data address, if it doesn't exist and there's nothing there, because remember, in a hash table, we can have collisions. And because we only have 50 spaces, 50 shelves here, we might have these collisions with enough data. So we're going to check if there is nothing there. In that case, well, just simply add that data. We're going to say this dot data address is going to be an array. And in this new space, new address space, we're simply going to add by doing push key value. So let's run this and see what happens. Oh, and I have a misspelled address here. Let's run that again. I get undefined. But let's see what happens if I just console.log this dot data here. Whoa, check that out. We have 23 empty items. On the 24th item, we have grapes, 10,000, an array here, and then 26 empty items after that. Remember, we have 50 shelves in our memory, and we have 23, 24, plus 26, that's 50. Except our grapes was inserted somewhere in 50, it looks like the 24 spot. Very cool. But what happens if this already exists? If I change the hash table to just have, let's say, 2 memory spaces, and I click run here, I get 1 empty and grapes. And if I change this around, do you see that? If I click again, and let's say go back to just grapes, check out what happens to my hash table. I click run, and it just deleted my previous entry. We have a collision, but we're not doing anything about it, and we've just deleted our data. That could have been really important user data. We definitely don't want that. So in order to solve that, we simply say if, because we're checking here if there is nothing in that address space, do this. Otherwise, simply add on to that array. So we can actually just run the same command here. A nicer and cleaner way of doing this is to actually just take out the else, because regardless, we're always going to be pushing key and value. We're always going to be adding the key and value that we add to the data. So all we do is just remove this, so that when I run this, and just so we know what's happening, let's return this dot data here. I'm going to hit run. And if we add here, let's say another item, this time we'll say apples, and just 54 apples. If I run this, did you see what happened here? If you look closely, we have one empty item, and then an array that contains inside of it the first index that is an array and a second index that is another array, because we've just pushed onto our existing array because our memory space is only 2. Very cool. That wasn't too bad. Let's keep going. The next one is, well, I want to be able to grab grapes and apples. We can use the get method here, which will receive a key. And this get method is going to work very nicely by just saying get, and then what we want to grab, which will be grapes. We're going to do the exact same thing in that we run it through that black box where we're going to use the hash function to get the address of where we want to go. And now we have the address to where we want to grab our information from. However, remember that we store this information in a bucket. So we have grapes and 10,000. How do we grab that? We know where to get it from now. We have the address, but we now need to loop over and grab grapes and then 10,000, or apples and then 54. Let me show you what I mean. We'll first create a variable saying current bucket. That will just be this.data or address, just so we don't repeat ourselves and we have a reference to this address or to the address and the data value. So this means if we console.log current bucket and I run this, you see that I have the current bucket. Even though this has 2 items, remember that it is technically just within its own bucket within one array. If we increase this memory space to, let's say, 50, we see that this bucket contains grapes. So we're grabbing this information, but all we want to do is have 10,000 being returned. That's how hash tables work, or the get in the hash function works. Well, all we need to do is to say if current bucket, and we'll say dot length. That is, if this current bucket has something in it, in that case, we are going to do something. Otherwise, we're going to just return undefined because there's nothing in the bucket. We're checking if this actually exists. So if there's nothing in the array, if the length is 0 and the array is empty, well then, we're not interested in it. As a matter of fact, we actually don't even need the length here because remember, initially, it's just going to be an empty array with undefined, and we add an array to each slot whenever we set something, and it's an empty address. So we can just leave it like that because if it's undefined, it'll skip over and return undefined. Now in here, we will do a for loop because remember, we might have multiple items in this bucket, like we saw when we had 2 memory spaces. In which case, let me actually demonstrate that. So we can see it. Say run. Oh, and current bucket. I can't spell. Let's run that again. All right. If we console.log current bucket and run this, we see that we have 2 items in that bucket. So we will need to loop over using our favorite for loop, which we've done a ton by now. We're going to say as long as I is less than the current bucket dot length, just increment I. And within here, this is a little bit tricky, so hopefully you follow. I'm going to say if current bucket I, which is the index, so remember it's going to say 0, which is going to grab this, then 1, which is going to grab this. If current bucket, the grapes, so if I do 0 here, that means grab the first, in our case the I, so it's going to be 0 first, grab this first array, then grab the 0 index within this array, which will be grapes. And then once it loops the next time around and I is 1, it's going to be apples. Check that against the key. Remember the key that we receive here that we are looking for. So if grapes, which is the key, matches with this item, in that case, just return the current bucket, the I, and 1 because we want to return 10,000. Hopefully you follow here because if I run this, I get 10,000. The get grapes is 10,000. If I do apples here, it is 54. How cool is that? And looking at this, I hope you understand on a deeper level the time complexity implications of hash tables. Even though we're doing a loop here within the hash function, remember that hash functions are really, really fast. We're just looping over the key. So we don't consider this to be O of n. This is very, very fast. It's O of 1. When we set something, there's no loops here. We're just adding it to our data. We're just pushing it. So that is O of 1. And if we go to get, most of the time, if there's no collisions, it's going to be O of 1. And in real life, most of the time, you can consider that it is O of 1. But in our really bad example with just 2 memory spaces and not a very good hash function, well, this can become O of n. But for now, because we're good programmers, that won't happen, right? Everything will be good. We have O of 1 get. We have the for loop here that might create that list we saw in our example. See this list that we have here? This is what we created. And it would be O of n if this list just kept growing and kept growing and kept growing. But there is one other method that I want us to build and to showcase to you one other downside of hash tables. What if we wanted to go through all the keys of the hash table? How would we do that? We're going to try and implement that in the next video. Bye-bye. Welcome back. Let's implement one last feature in our hash table over here. I want to create something called keys. And keys allows us to iterate or loop through all the keys of our hash table. In this case, grapes and apples. And let's add a few more just for fun so we see what's going on. We'll add oranges, and we don't like them too much, so we're only going to add 2 of them. Now, if we run keys, ideally it's going to iterate and spit out grapes, apples, and oranges for us to see what we need to go shopping for. How would we go about building this? Well, because we're going to do some sort of looping, I'm going to start off by creating a constant. Let's call it keys array. And this is going to be an empty array. Within here, we're going to loop. So for let I equals 0. And as long as I is going to be less than this dot data dot length, we're going to increment I. In here, we're saying we want to loop through all 50 item spaces. All the shelves one by one, we're going to loop through them. Yep, that's a lot of iterations. And if in the shelf there is some sort of data, if it's not undefined, completely empty, and there is something valuable for us that we want to look, because remember, we allocate 50 spaces on the shelf, but we've only placed 3 items or 3 data points on that. So if there is something in that memory space, in that case, we can just say keys array dot push this dot data, and we grab the index, so the first array or the array that we're at right here, and then we want to grab apples, right? Well, if I do 0 here and now hit run, well, we have to return something. Let's return here the keys array at the end of all of this. So after all the loops, we're going to simply say return keys array. If I run this, I get grapes, apples, and oranges. That's fantastic, but I just wanted grapes, apples, and oranges. To see what's going on here, let's console.log this.data I, which is what we're doing here, what we're pushing. And if I run this, we see that we get arrays within the array. Because remember, we have one massive array, and each time we create a new shelf space, we have to have a new array that we create and we push into that. So a little bit of a gotcha here. We have to say 0, which removes the outer array, and now another 0 to grab the first index of this array. Just like that. So if we add another 0 in there to access the first index of the array, we click run, look at that. We get grapes, apples, and oranges. Well done. We've just implemented a hash table. And you may have noticed something, a downside of hash tables. We had to loop here, right? We had a for loop, looping through the entire memory space in order to find our keys. That was so much easier with arrays. With arrays, we would have had just 3 items and we would have looped over 3 times. Instead, here, we looped over 50 times. Imagine if we had 500. That's even more. How exciting is this? We're starting to learn how things work underneath the hood so that now we have an idea of, maybe if we're using this type of method, objects might not be the best idea. And that's one drawback of objects or hash tables. In JavaScript, we can use something like for in loops to loop over items in an object, which again is very, very slow. And as you might realize, there's no guaranteed order. Every time we're just adding something to our address, but when we grab items from the address, we just go from 0 to 50, even though the items are just randomly placed in different shelves. But I hope now you actually get to see how it works. We're putting items randomly in a shelf, but when we retrieve them, they're all unordered. And that's why coding things out, even though you most likely won't get this asked in an interview, knowing how things work allows you to talk about them intelligently. And I hope this exercise has done that for you. I'll leave this for you to play around with and perhaps add different methods like values that grabs the values instead of the keys. But for now, let's finalize our talk of hash tables by comparing them to arrays. Welcome back. Why hash tables? Hash tables are great when you want quick access to certain values. We remember that searching through an array for an item takes a really long time. We have to loop through every item and see if a certain string or a certain number is in an array. With hash tables, that's really, really fast. And this is why you see hash tables in places like databases, right? We want to search for something in a database and it gives it back to us right away. Similarly, inserting items in a hash table, unlike an array that might shift indexes, is typically O of 1. You just simply have to hash and create the key. Although we have those cases of collision, most of the time that's something that we don't need to worry about too much and we can assume an insert of O of 1. Then there's other aspects that are quite similar between the two. Arrays let you quickly look up the value for a given key. Keys are called indexes in an array, and we don't get to pick them. It's always 0, 1, 2, 3. In hash tables, we can pick them. So hash tables is kind of like a hack on top of an array to let us use flexible keys instead of being stuck with 0, 1, 2, 3. A problem of hash tables that we discussed was the idea of no concept of order. In arrays, each item was placed next to each other on a shelf in memory. Hash tables are kind of placed all over the place. Now that we have an idea of the differences between the two, I think it's time for us to actually work on some exercises and interview questions that will use hash tables in their answers. I'll see you in that one. Bye-bye. Welcome back. it's time for an exciting interview question. And this question comes straight from Google. Given an array, let's say that looks like this, tell me the first recurring character. What does that mean? Well, if we look at this array over here, I want a function that I can enter this array, this input, is going to look through all the numbers and tell me which one gets repeated first. So we look at 2, 5, 1, and 2, and we say, 2 has already been seen. 2 is the recurring number. If we look at another example, we see 2, 1, 1, and we stop here because 1 we've already seen before. We can say the first recurring character is 1. If we get an array that has all unique items, we just return undefined. So, how would you go about solving this? Give it a go. See what you come up with. If you need help, perhaps go on Discord and chat with some of the community members, and I'll see you in the solution video. Welcome back. How was it? Did you get it? Was it a tough question? Don't get too disappointed if you weren't able to get the answer. These questions are meant to be tough, to stretch your mind. If they were too simple, then you wouldn't be learning anything. Let's start off with the naive approach. That is, the approach that first comes to mind. For me, the very first one is going to be a nested for loop. Let's have a function. I'm going to call it first recurring character. It's going to receive an input. And because we've already talked about it, I'm not going to do any input validation. We can just assume that we're always going to get some sort of a numbered array. In here, I'm going to loop again. And oh boy, I've done this so many times by now. I hope you're getting sick and tired of just looping through arrays. But hey, now at least we are masters of loops. I plus plus. So in here, in the first loop, we're going to grab the first item in the array. And let's just call this function so we have it here nice and easy and gives us a nice visual. So I'm going to loop through the first item, then the fifth, or the second, the third, the fourth, and keeps going. I want to grab this item and then do another loop and check 2 versus 5, 2 versus 1, 2 versus 2, and then say, that's the one. If it doesn't find anything, it's going to go to the next 5 and then compare 5 to 1, 1 to 2, 2 to 3, and so on. So once again, I'm just going to copy and paste this time because we have done a lot of for loops. And simply change the variable to be j. We're going to start at 1 because we don't want to compare 2 to 2. We want to compare 2 to 5 to start off. So we're just skipping a loop, which will help us out. I'm going to say j here and j++. Now, some of you may have been caught here because if we have it the way it is right now and you console log this loop, you'll see that it won't work properly. Because every time this shifts, the outer for loop shifts from, let's say, 0 to next one, the 1 index, j is going to be reset to 1. So 5 is going to get compared to 5, and the function is going to assume, 5's the reoccurring character. So a little trick here is to do I plus 1. That is, we always go 1 to the right of where I is, the first index is. So if we're looping, and we're at here, the subloop, the nested loop, is going to look at I plus 1. So it's going to compare 2 to 3, 2 to 5, 2 to I, because, well, we've already compared 2 to 2, 5 to 1, 5 to 2, 1 to 2 in previous loops. All right, we've done that. In here, we can simply do an if statement saying input I, does that equal input j? Does 2 equals to 5? Does 2 equal to 1? Does 2 equal to 2? If that equals, then just simply return input I. Otherwise, if we do all this work and nothing happens, we can just return undefined. Let's see if that works. I'm going to run it, and I get 2. Awesome. What if I change this to 1? If I run this, I get 1. Perfect. What if I do just a single item in an array? I get undefined. If I do an empty array, I get undefined. That's good. What if I do 1, 1 or 1, 1? I get 1. That's great. If I do 1, 2, I get undefined. Awesome. This looks to be working. Nice and simple. But as you can see here, we're not being very efficient. We have nested loops, which should trigger, this is O of n squared. And although technically we're actually always looping a little bit more efficient because of I plus I, we're not looping twice over the entire array. In the end, when you remove the constants and simplify things, it's still going to be O of n squared. So how can we solve this using hash tables? Well, let's create a new function. We'll call this function by the same name, this time number 2, version 2. It's going to receive an input. And let's change our test case to have the same thing like we did previously. What can we do here? Well, let's use a hash table or an object to do something interesting. That is to add all of these as we iterate one by one, so loop through all the items, add them to a hash table, and while we're doing that, we can check to see if the property already exists or the key already exists. We add 2 to the hash table, then 5 to the hash table, then 1 to the hash table, and when we try to add 2, we can trigger a warning saying, we already have 2 as the key. So using that logic, let's see how we can implement it. I'm going to create a map. We'll just call it a hash map for now, because the keys are going to be unique. It's not going to let any duplicate keys. And we can simply do our loops. And in this loop, all we're going to do is say if map, and we can check in this map if it's empty. Now the first check in here, I want to say if the property or if the key already exists, I want to just return the item because we don't need to do any more work. As soon as we find a key that already exists in our hash table, stop all the looping and just return. In this case, we want to return 2. So at index 0, 1, 2, 3, it's going to return and say 2 because, well, this key already exists. So the way we do that in the if check is to simply say if input I, because remember, this is going to equal to 2 when we loop through it. If that exists, then return. Otherwise, we will just add it to our map. So input I is going to equal And the value can be anything. We'll just leave it at I, which is the index. So 2 is going to equal 0, 5 is going to equal 1, 1 is going to have 2. Let's just console log here to see what is happening. But I want to also return undefined at the end in case none of this happens, in case there is no match. So at the end of the for loop, we'll just console.log map and see what we have. I'm going to run and I get 5. And there's no log. What just happened here? Well, if we console log up here instead and take a look at what this is giving us and run, I get undefined, undefined, undefined 0, undefined 1. What does that mean? Well, remember, we're looping through here and we're saying, hey, does 2 exist? Does input 0, which is 2, exist as a key? So it's simply saying map.2. Does it exist? And because that doesn't exist, we get undefined. And it's going to go to next. Hey, does 5 exist? No, it doesn't. Hey, does 1 exist? No, it doesn't. Hey, does 2 exist? And as soon as it checks 2 again, map 2, it's going to say, I already have it. It's at index of 0. So this is working. However, because when this gets to 0, the way JavaScript works, it puts 0 here, but in an if statement, 0 is what we call falsy in JavaScript. And that has to do with type coercion in JavaScript, something that a lot of people get annoyed about with the language. So what we would need to do is to make sure that we specify that we want this to not equal undefined. So as soon as it doesn't equal undefined, I want you to return this item. Now, if we run this, we get 2, which is great. If we console.log the map and run this, and let's add it at the bottom here so we see the actual iteration that's happening. We see that it adds 2 at index of 0, then 2 at index of 0 and 5 index of 1, so on and so forth until it stops after the third loop because it encounters 2 again. It's going to check and say, 2 already exists, just return it. How cool is that? We just made this entire thing with just one loop that is way faster than our first version using hash tables. How cool is that? For me, doing things like this and seeing the power of how learning about Big O and hash tables has improved our coding ability just gets me really, really excited. And I hope this gets you excited as well. We made this function have a time complexity of O of n. We've improved it with one downside. We've increased the memory, the space complexity by O of n because we're creating a new object in this function that needs to keep track of all the items in the array. And in the worst case, when there is no match, it's going to go through the entire item list of the array and hold that information in the map. So we're also going to have, unlike this version where we didn't create any space complexity, we just had space complexity of 1, we now have a little bit more. But in turn, we have a faster function. Very, very cool. Now to finish off, I want to give you one last challenge. You see, looking at these two implementations, what happens if we have something like this? What do you think the first recurring character is. If I run this, I get 5 because, 5 occurs sooner than 2 because of the way we implemented the second function. However, if I go to the first version of our function and run this, I get 2. Why is that? Well, if we go to the very first part of our function, we see that the way we are doing things is we are going one by one in a different way. We're saying grab 2 and then compare 2 with 5, then 2, then 3, then 5, then 1, and 2, 4. And then move over to 5, then 5, and 5, and 2. And so on and so forth. And because of the way we have that implemented, it's going to detect 2 and 2 because the outer loop has an index of 0 and has 2 as it's going through the loop before it compares 5 with 5. Versus our second version with a hash table where we had all these items and we were able to compare them once we grabbed all of them. And that's another powerful thing when you think about arrays and hash tables and how you're able to compare things. And based on what the interviewer asked, you might have a wrong answer. Maybe they want you to detect 5 and 5 before you detect 2 and 2. So my bonus question to you, if you have time and a bit of a challenge, is to convert this function, if you want, into something that matches the answer to this, that is to detect 5 and 5. How would you go about doing that? You're most likely going to have to do something interesting here. So good luck with that. Talk to other people on Discord in our community and see if you can figure it out. And I'll post some creative solutions to that problem as students submit them to see how other people have implemented this. But for now, I think we deserve a break. I'll see you in the next one. Bye-bye. Another data structure down, hash tables. By now, you should absolutely love them because, they're very useful. They're used everywhere. And the funny thing is that it's probably the most common interview question where you use a hash table to optimize something, kind of like we saw in our interview question. By using hash tables, we optimize those nested loops that are O(n) squared to O of n, linear time. This is a question that comes up again and again that I promise you, if you notice this pattern, it will be extremely useful for you in an interview. And undoubtedly, you'll have an instance where you have to use it and follow this exact same step. In this section, we learned that hash tables have really fast lookups, but remember, we need a good collision resolution needed. Usually, we don't need to worry about this because our language and computer underneath the hood take care of that for us. It allows us to do fast inserts, and depending on the type of hash tables, such as maps in JavaScript, we can have flexible keys instead of an array that has 0, 1, 2, 3, just numbered indexes. The downside with hash tables is that it is unordered. It's hard to really go through everything in order, and also it has slow key iteration. That is, if I want to grab all the keys from a hash table, I'll have to go through the entire memory space as we saw when we built our own hash table. Looking at the Big O cheat sheet, we can see that hash tables has a search, insertion, deletion of O of 1, but in worst case, due to collision, there are some O of n operations that could happen. And if we go to our mind map, we can now cross off hash tables off our list. We understand the Big O complexity. We also understand that With collisions, we might want to use something like linked lists, which we'll talk about very shortly. In our exercise, we just simply used arrays. We also learned the idea that hash tables in interviews are usually useful for improving time complexity, especially of nested loops. The trade-off being that we can have fast access, but more memory. Going back to our question that we had a few lessons ago, where we had to find the common item of two arrays. We had array 1 and array 2, and we had to see if any of these arrays contained similar items. We had one that didn't, and the second version, where x and x, both arrays contained x, it would return true. Our first iteration of that exercise, we had to use 2 for loops that were nested. So that created A times B complexity. However, using hash maps, we were able to just do 1 for loop and optimize this function. Like I said before, this is such a common pattern that we'll be talking about it later on in the course as well when we talk about dynamic programming. If we go back to our cheat sheet that I shared with you at the beginning of this course, we can now cross off a few things off the list that we haven't talked about. In the good code checklist, we talked about the good use of data structures, when to use hash tables over perhaps arrays. The idea of code reuse and not repeating yourself is something we've been following and should be familiar to all of us. We also talked about modular code and making code more readable, which allows code to be more maintainable and testable. We talked about how usually in an interview, we want to avoid the O and squared operations. And we saw that we're able to do that with hash tables. But we did see that with a hash table, we had to increase our space complexity to O of n because we created this new variable that keeps track of all the items in the array. So that is the trade-off. And then we can cross off a few heuristics. For those who don't know, heuristics are kind of like rules or simple tricks that are going to come up over and over and over that you can use in an interview. Hash maps or hash tables are usually the answer to improve time complexity. Again, hash tables are some of the best way to optimize your code. And looking at time versus space trade-off, sometimes storing extra state in memory, like we did with hash tables, can help the time or the runtime. And then finally, space-time trade-offs. Hash tables usually solve this a lot of the time. You use more space, but you can get a time optimization to the process. I know we've only talked about 2 data structures, but I think these 2 are the most important. Moving forward, we're going to use them to learn about others. Good job getting this far. Take a nice little break, have some coffee, and I'll see you in the next video. Bye-bye. It's time to talk about our third data structure. And we're going to be talking about 2 types of linked lists in the next coming videos. Singly and doubly linked lists. What problem did we encounter with arrays? Well, with static arrays, we only had a certain amount of data or memory that can be allocated next to each other in memory. But then both dynamic arrays and static arrays can increase their memory once it hits a certain limit and double up that memory in another location. But that operation every once in a while of doubling up the array in order to create more memory had a performance implication, and it cost us O of n. Additionally, arrays also had bad performance for any sort of operations like insert and delete that had to shift indexes over, especially when you inserted or deleted anywhere that wasn't the end of the array. And then came hash tables. They were great. We would pretty much store things wherever we wanted in memory. And hash tables would just take care of it for us and know where to place it in memory. We didn't have to worry about some problems that came with arrays. Life was good. But unfortunately, they weren't really ordered. So how can we solve this problem? Linked lists to the rescue. So does this mean we all should just be using linked lists all the time and disregard arrays and hash tables because linked lists are the best data structures? Nope. As always, there are trade-offs when it comes to data structures. So in the next coming videos, let's learn more about them so we can get a clearer picture. By the way, remember this diagram that I showed you in the hash tables videos? And I said that when we had a collision, one way to solve it was using something like this. And we had no idea what this data structure was. Well, this, John Smith to Sandra D, and this little arrow pointing, that's a linked list. So let's get started and learn what linked lists are. What is a linked list? As the name suggests, it's a list that is linked. All right, Andre, that's not very helpful. Can you actually explain it to us? All right, well, I have a little diagram here for you. A list, or in this case, as we'll find out soon, a singly linked list, contains a set of nodes. And think of nodes as these blocks. Both red and green block together is a node. These nodes have two elements. The value of the data you want to store, in this case, the number 5, and a pointer to the next node in line. So you can see the green block here points to the next node. The first node is called the head, and the last node is called the tail. Now, depending on some people like to call the tail anything that is after the head, so including this block over here. But I prefer the term tail referring to the very last node. Finally, linked lists are what we call null terminated, which signifies that it's the end of the list. So we know that this is the tail node because it points to null. There's nothing coming after it. Now, pointer is a term that you hear a lot in programming and computer science. And we have a video coming up discussing what a pointer actually is. But to focus just on linked lists for now, you can see that it's a very simple data structure. It's simply an element that links to the next element that links to the next element. And it keeps going until the last element that points to null. You can have them sorted, you can have them unsorted, and you can have nodes pretty much contain any sort of data type. But let's take a look at some pseudocode. Up until now, we learned how arrays work. And here I can just create a simple array, let's say a basket that contains our grocery list. We have apples, we have grapes, the most delicious of the fruits, and we have pears. Now, how can we have a basket that's not an array, but a linked list? Well, we can just say that our linked list, and this is not actual code, just pseudocode, I can say that our linked list will contain apples that then points to grapes that then points to pears. And these little arrows are essentially pointers saying apples to grapes to pears. Remember, this isn't actually code. I'm just creating a nice diagram for you. A more accurate diagram might be something like this, where we have apples in memory space of, let's say, A947, and this node points to the next node, which is grapes, that is at this location in memory, and then that node points to pears, that is at this location in memory, and because this is the end of the list, the tail, it points to null. Now, you're thinking to yourself, Andre, how come you're not just coding this in JavaScript? Just show us how linked lists work in JavaScript and stop with this pseudocode gibberish. Well, JavaScript doesn't actually come with linked lists built in. Remember what I said. Different languages have different tools available to them. Languages like Java have linked lists, while JavaScript doesn't come pre-built with linked lists. But luckily for us, we can build one. And this is what you typically do in programming. When you don't have something, you build it. And we have the building blocks to be able to build a linked list. And that's what we're going to do as part of an exercise coming up. But before we code our own linked list and create our own linked list data structure, let's do a fun little exercise. Hey everybody, I want to take a quick break here. Go grab a coffee, grab a tea, just take a break from all the learning that you just did. And I want to talk to you quickly about imposter syndrome. It's this idea that you're not good enough, that things are too complicated for you to ever achieve what you want to achieve. You look at other people, at other industry experts, and you say, I will never get there. But it's just a symptom of learning. This idea of you not being good enough simply means that, well, you're just not there yet. Things take time. If you want to learn a valuable skill, well, it's hard work. That's why it's valuable. Remember how you felt on the first day of going to school, first day on a job. It's the same experience. But over time, with repetition, with practice, you get comfortable, you get experience, and you slowly start to lose that imposter syndrome. Now, this idea of an imposter syndrome is great. It means you're doing something worthwhile. So don't use it as a negative. Use it as an encouragement that you're doing something good, that you're learning and you're stretching your limits. So with this break, I want to propose that we do a quick exercise. I want you to stop the lectures, again, grab a coffee, grab a tea, and head on over to our Discord. Now, in our Discord server, if you've used it up until now, that's great. If you haven't, head on over to this server, and I want you to do something that I think it's super important to learning. And that is using what you've learned up until now to actually teach someone or help someone. So you can go all the way to, let's say, the coding and courses section and pick a topic that you want to help somebody in. So let's say you go to the Python channel. And in here, you'll have other students that are asking Python-related questions. Now, you can scroll through here and see if you're able to help someone. Even though you may not have the experience or the knowledge yet, this idea of practicing and explaining what you've just learned to other people, even if you're not 100% certain, actually is beneficial to your learning. Because if you're never teaching, if you're never explaining and vocalizing and showing what you've learned, you'll always be a beginner. This idea of teaching what you learn is a very important concept. So moving forward, as you go through the lectures, anytime you feel like taking a break, hop on over to Discord and help somebody. Our motto here is that we're always kind. We don't judge anybody. We're all just beginners here. We're all learning. So don't be afraid to answer things because you got to remember, nobody's perfect except for Yoda. Yoda is pretty perfect. All right, I'll see you in the next one. Bye-bye. Welcome back. It's time for a little exercise. Why do you think linked lists may be better than hash tables or arrays, just from what we know right now? I want you to answer this question in your head or write it down before you go into the next video. I also want to show you a nifty little tool that I will link to in this video. And this little visual shows you how a linked list works. So you can play around with it and see where they might shine over arrays or hash tables. You see over here we have a head with a value of 22 and a tail with a value of 89, and then other nodes connecting all of them. And you can use this website to do anything to a linked list. You can create, you can search, you can insert, you can remove. Let's do a insert here. I can either insert to the head if I click here, and if I click go, I enter the value 85. I can insert to the tail at the very end if I hit go. All right. That seems pretty simple, nothing too crazy. What if we insert somewhere in the middle? If I click over here and let's say at index of 2, I want to insert the value of 90. Or let's increase that to 93. I hit go. Keep an eye on what's about to happen. Oh boy, what just happened? Don't worry, it looks a little bit complicated and we're actually going to code this all ourselves and build this in. But I want you to play around with this data structure and in your head come up with why we might want to use something like this. And in the next video, I'm going to tell you all about it so you can test whether your assumptions are correct. I'll see you in the next one. Bye-bye. Welcome back. I hope you are able to think about why linked lists might be good or bad. In this video, let's discuss the answer. One key thing that you may have seen is that linked lists have a sort of loose structure that allows you to insert a value into the middle of the list by simply resetting a few pointers, just like we saw in the animation. I can insert anything that I want, and the only changes that happen is somewhere in the middle here. And this is the same for deleting node in a linked list. And we remember with an array data structure how when we wanted to insert something that wasn't at the end of the array, we had to add the item, let's say in memory space 1, into here and then shift all the items down and index it down, which cost us a lot of time. It cost us O of n. The main difference between arrays and linked lists is that in an array, an element or elements are indexed. So if I wanted to go to item at index 5, I can do that easily. In a linked list, you start at the head and traverse the list until you get to item 5, which is O of n. And this idea of traversal is the same as iteration that we did with arrays, where we go 0, 1, 2, 3, 4, 5. Except we like to call this traversal because you don't really know when the linked list will end. You start from the head and you keep going until you hit null. And as you'll see in our coding example, we're going to have to use something like a while loop when we implement our own linked lists because we don't usually know how long the list is going to be. Another advantage that an array might have is that most computers have caching systems that make reading from sequential memory, that is memory right next to each other, shelves right next to each other, faster than reading scattered addresses. And that's something that we've talked about already. Array items are always located right next to each other in computer memory. Linked lists and nodes instead are actually scattered all over memory, kind of like hash tables. So iterating through a linked list or traversing through a linked list is usually quite a bit slower than iterating through items like an array, even though they're technically both O of n. However, these inserts that we can do in the middle of a linked list is a lot better than an array. What about hash tables? Remember this when we talked about hash tables? Well, just like hash tables, when we insert something into a linked list, we just scatter it all over memory and we can just keep adding it, keep adding it, keep adding it. And we don't have to do any of the unshifting or shifting on the indexes that we did with arrays, which is really, really nice. You can also delete nodes very easily versus with an array. But the one advantage that it has over hash tables is that there is some sort of order to linked list. Each node points to the next node, so you can have sorted data, unlike a hash table. So if we look at our big O of linked lists, we can see that prepend, which is a common language you say to add to the beginning of a linked list, prepend is O of 1, Append, which is at the end of the list to add a new item, is O of 1. Lookup, which we can also call traversal to look for an item, let's say we want to find 10, is O of n because we have to go from the head all the way until we find what we're looking for. Insert is also O of n because we have to go one by one, find the index. We don't know how long our linked list is. We find the index and then insert there, which technically could take O of n. And again, something that we're going to implement in code and have a better understanding of. And delete is also O of n because we have to find the items. Now, you're thinking to yourself, hold on, insert and delete in arrays are also O of n. So how is that better? And that's something that we're going to get into when we actually take a look at the code. Remember, this is the worst case, in which case we insert or delete the very last item. And most of the times, that won't be the case in linked lists. Again, something that we're going to talk about a little bit when we code our own linked list. But looking at a diagram like this, it's really hard to truly understand how they work and what linked lists are. So we're going to code our own. In the next video, we're going to talk about this final piece of the puzzle, what a pointer is, and then finally code our own linked list so we understand the big O implications a little bit better. I'll see you in that one. Bye-bye. Welcome back. Let's quickly talk about pointers, something that you'll hear a lot in computer science topics. A pointer is simply this. It's a reference to another place in memory, or another object, or another node. And in JavaScript, we can demonstrate it with something like this. If I have an object, let's call it object1, that is a simple object that has A as true. And I'm going to comment this out. And now we do something like const object2 equals object1. We've just created a pointer, a reference to an object. And that is what a pointer is. It's simply a reference. Here, I'm not copying the object. I'm not saying object1 equals A equals true and also creating another location in memory that says A equals true. In memory, when we look at our RAM, there is only one entry, A equals to true. And both object1 and object2 point to the same location in memory. To show you that is the case, let's just console log object1 and then console.log object2. And just so we're clear on this, I'm going to say 1 here, and this is going to be 2. So that if I run this, I have both A equals to true. But if I change object A, so accessing property A in object1, and I say that is going to equal booyah, and I run this, look at that. Both object1 and object2 changed because I've created a pointer here saying object2 is going to reference object1 like so. And they both point to the same location in memory. And that's what a pointer is. It's simply saying, hey, this is where it is in memory. And when we look at our linked list example, when we remove, let's say, a node at index of 2, and I hit go, 1, 2, we remove that. And that just disappears from memory. How does that work? Well, if we go back to our example, I can just delete object1, and I'm going to change these into let because we are going to change the values here. If I click run, I get reference error. Object1 is not defined at line 14. That's right over here. Okay, so let's just comment this out because object1 doesn't exist anymore. If I click run, I still have object 2 as booyah, even though we deleted object 1. What's happening here? Well, the way it works in most programming languages is that our computers are going to delete the memory that is unused. And because it sees that object 2 is still referencing this location in memory, this value in memory, it's not going to delete it because there's still a pointer to this location in memory. And this is how things get deleted in languages like JavaScript. This is what you might call garbage collection, where as soon as we say object 2 dot, or object 2 equals hello now, and I click run, now object 2, which referenced the memory space that had a equals to true, is now just simply a string. So because JavaScript is garbage collected, that is, memory is managed automatically, this gets automatically garbage collected and deleted because nothing is pointing to it. However, there's low-level languages where you have to manage your own memory and you have to manually delete this unreferenced item in memory. And this can cause a lot of possible issues where you leave memory that's not being used in memory, which is a valuable resource. But then there's also benefits with non-garbage collected languages where you get to manage your own memory, so you can make things really, really fast and efficient. All right, I think that's enough for pointers. A pointer is simply a reference to something else in memory. And we're going to use this knowledge in our next video to create our very first linked list data structure. I'll see you in the next one. Bye-bye. Welcome back. It's time to create our very first linked list data structure. And let's say I wanted to create a linked list that has 10 pointing to 5 pointing to 16. A nice little simple one. First off, how would we go about visualizing this in a language like JavaScript that doesn't have linked lists? Well, we can simply say that we have a new linked list. Let's just use let here, my linked list. And this is going to equal to an object that has a head property. Remember, because the very first item in a linked list is the head. And we're going to have a node. The point of the node is to say, hey, anything can be in this node. Just put anything you want. And it's a container around this data. So think of node as a bucket of data. And in this case, we can just use an object to put our data in. All this node needs to have in a linked list is a value property of what the value of the node is, plus a next property, which is the pointer to the next node. Now, this value can be anything we want. And the next property has to be a pointer or a reference to the next node, in which case will be an object. So it'll be another object that we're going to reference in memory. This way, the value of the node can always change, but the pointers are always going to be pointing to that. So we can change items and nothing else will change. It will still point to that changed and updated value. Let me show you what I mean. We have the head here, in which case it's 10. So we want to set 10 as our value. And this head is going to point to the next node, which will have a value of 5. Make sure I add the commas in here. And the next value of what do you think? Well, the next node in the list, which is value of 16. And next, referencing what? Well, 16 is the tail of our linked list. So that means it has to point to null. or what we call null terminated. That means it's the end of the list. Perfect. So this is what we want to create, a linked list. Using this as our structure, we're going to create a class called class linked list. And this class, and we should be familiar with the syntax by now, will have a constructor, which is the function that gets run at the very beginning when we create the linked list. That's going to take a value. What does that mean? Well, when we finally say that we're creating a my linked list, remember, we want to create this. When I create my linked list, I'm going to instantiate the class, that is, run the class function here, run the constructor, and create the linked list. I'm going to say linked list, and then give it a value to start off the list because, well, the list can't be empty. It has to have something. It has to start with the head. So in our case, we want to start it with 10. And ideally, by running this command, we've created the first part of our linked list, just the 10. Let me comment this out since we won't need it for now. Now within this constructor, we have, well, the this.head reference because, well, we need to keep track of the head. And this head is going to simply have a value that equals to the value that we passed in, that is the 10 here. And then finally, the next. And what should the next be when we first create this list? Well, since 10 is the only thing that we'll have, or one node, next is going to equal null to begin with. Remember, constructor is all about creating the very first linked list node. What happens when we instantiate a class to start off my linked list? And then finally, we have two other pieces of information that we need to track. One is this.tail. And remember, the word this just refers to the linked list. So it's just referring to the linked list that we create. What is the tail going to be? Well, because we only have one item, the head is also the tail. So we simply say this.head. And by the way, I know this can get a little bit confusing. And as we go through this video series on linked lists, it is a bit hard to wrap your mind around. So I really recommend that you code along here and do the exercises because just watching me talk about linked lists is not going to solidify your information. It is hard to really visualize things. So you may need to build linked lists a couple of times to really get the hang of it. But this will become second nature once you get used to the syntax and also the idea of having this head and tail and referencing them. Anyway, the final piece of the puzzle is, if we want, we can keep track of the length of the linked list. This is optional, but I think it's good to keep track. And because we have one item, when we create this linked list, because we give it a value, we'll give it a length of 1. There we go. If I run this, I get an error because, well, I have this code that's not really JavaScript. So let's comment that out and click run again. I get undefined, well, because we haven't logged anything. But if I console.log my linked list and I run this, look at that. I have a linked list with a head that is value of 10. Next is null because, well, there's only one node. And a tail, which is the exact same thing, pointing to null, and a length of 1. Congratulations, we just built our very first linked list. However, it's time for a little bit of an exercise. Our list is not complete, right? We need to create this linked list. So we need to be able to add 5 and then 16. So my challenge to you is this. We want to create an append method. And this append method is going to take a value. And in here, we want to write a piece of code that allows us to say const or my linked list dot append and give it a value, if we look at our list, of 5 to append to our current list. So I want to be able to say append 5 and then append 16 to create our completed list of 10, 5, and 16. How would you go about doing that? And I'm going to leave this for you to try out. Remember, this may be a little bit hard, and I'll provide the solution video and we'll code along. But I do encourage you to challenge yourself and just think about what's happening and what we've done in the constructor to create this append method. Good luck, and I'll see you in the solution video. Bye-bye. Welcome back. How was the exercise? Were you able to figure out the append method? Let me show you what I would have done. The first thing we would want to do is to create a new node with the value. And we can do that quite easily, saying const new node. That's going to equal, well, an object with the properties that we should be familiar by now. We have value that is going to equal the value that we get as the parameter. And then the next that will be null. So we have our new node here, and we want to attach it now after the 10 node, which is our very first node. Well, we can simply do that by saying this dot tail dot next, which is the, remember, this part over here, next equals null. So that is, what is the tail? That is the last item in our list, because this method doesn't know that we only have one item. We could have 100 items. We just want to add at the end. So it's going to grab the tail and then grab the next value of the tail. So it's going to grab the pointer of the tail and say, hey, instead of pointing it to null, point it to this new node that we just created. All right, we've pointed the tail to now point to the new node, which has next null already set up. And then we also want to say that this, what we had as tail before, which was the value of 10, is no longer the tail. We have a new last item. That is, this dot tail is now going to equal new node. And because we are running this operation after this one, when we run this, the tail.next is still this node. And as soon as we update this node to have a next of the new node, we can now update the tail to be the new node. Because by that point, by the time this line runs, the next has been updated properly for this older tail value. And then finally, we want to make sure that we add the length to equal 2 now. So we're going to do plus plus. And just for fun, because we want to make sure that we do this right, we're going to return this, which is the linked list. Remember, this just references what this class is that gets instantiated. So we're just going to say return this so that we get back our linked list. I'm going to remove the console log for now and see what happens when we just run append 5. I'm going to click run. All right, I get returned our linked list, which has a head of value 10. Next is the new node that we created, the value of 5, and next null. And then the tail is value of 5, next is null, perfect, with a length of 2. Awesome. It looks like it's working. Let's do this one as well. Append. And there we go. We have value of 5. So the head is referencing value of 10, which points to the next node, which has value of 5, which points to next, which is an object, that is the tail. Because of the way logging works, it won't show this nested. It'll just say that this is an object. But this is pointing to tail, which has a value of 16, next null, length of 3. How cool is that? We just created our linked list, our 10, 5, 16 linked list, just like that. I hope you got that right. But if you didn't, don't get discouraged. This takes some time to get used to. Luckily for you, once you write it a couple of times, then it becomes, like I said, second nature. So don't stress out, because I have another challenge for you. Now that you know how to do append, you should be able to do prepend, right? Prepend is adding to the beginning of the list. So let's say that in our list over here, we want to add 1 as our head now, instead of 10. How would we do that with a method called prepend? This prepend is going to take a value, and we're going to be able to run a command like my linked list dot prepend 1 to add the 1 at the beginning of this list. So, code here, good luck. Let's see if you can solve this one, and I'll see you in the next video where I give you the solution. Bye-bye. Welcome back. Were you able to implement prepend? Let's have a look at what the code should look like. The very first thing we do, just like we did with append, is to create the node that we're going to add. So I'm going to say new node, value, and next. Now, next here, I'm going to leave as null. And I'll show you why in the next video that is the case, and we don't just have next equals to this dot head to reference the very first item in our list, which is 10. But for now, just trust me that this we want to leave as null, because we can do that later. Right now, we're just creating an empty node with the value. Next, we want to say that our new node dot next, which is this value over here, is going to equal this dot head. So we've just created a pointer saying that the new node we just created is going to point to this dot head, the very first item in our list. Okay, that should make sense. And then obviously, just like we did with append, we want to update the reference now to say that this dot head is no longer equal to this old value. It's now the new node. And then finally, we want to add this dot length and make sure we increase the length of our list. Finally, if we return this, our linked list, we can say run. And look at that. We've prepended 1 to the very first item on the list, the head, and that is now referencing 10. And the tail of our list is now 16. That wasn't too bad, was it? In the next video, I want to talk quickly about this new node code that we're repeating, both in append and prepend, and what we might want to do with it. I'll see you in that one. Bye-bye. Welcome back. In the previous video, we talked about how new node over here gets repeated, both times in append and prepend. And as we create more methods on our linked list, we're going to have to constantly say new node, value equals value, next null. And usually we want to keep things dry. That is, do not repeat yourself in code. In many implementations of linked list, you'll see something like this, where new node is actually another class. For example, I can create a new class here, and this is how object-oriented programming usually works. We have classes that interact with other classes to create our programs. So you'll see a lot of implementations of linked lists that have class of node, and this node is going to have a constructor that takes a value And this value will have this dot value equals to value. It's going to have this dot next equal to null. Just like that. So that way, instead of us saying constant new node and creating this new node every time, I can just say every time that I want to create a new node, we can say let or const new node equals to new node and then the value. So every time we have a new node, we just instantiate what we call create and run this new node class that creates a node for us with a value property and a next property. So you might prefer using this syntax, but because I find this can get a little bit confusing, especially if you're not used to classes, I'm going to just keep things the way they are because, well, I think it's easier to read. And as you saw, it's fairly easy to implement if you want to do that on your own. Okay, just a quick segue. Let's get back to finishing our linked list in the next video. Bye-bye. Welcome back. We've just implemented prepend and append. And it should be clear to you why that is an O1 operation for both of these. We didn't really have to loop through anything. We just had a reference to the tail and the head, and we reassigned some values. Nice and easy. But now comes the hard part. What about these ones? What about lookups, traversals, inserts, deletes? I think we should code those as well to fully understand how linked lists work. This exercise is going to be a little bit tougher, but I'm going to give you a heads up that there's going to be some looping involved. We want to create an insert method. And this insert method is going to have an index and a value parameter. Because we're going to want to be able to say insert at this location, this value into the list. For example, if I wanted to say my linked list dot insert, and let's say I wanted to insert at index of 2 the value 99, well, that would mean that if we go back to our example, index of 2 would mean 0, 1, 2. Right here, I want to insert 99 and have that point to 5. How would we go about doing that? I want to warn you, this can get a little tricky. And the best way to really think about it is to grab a piece of paper and a pen and draw out the steps that you should do. A good way to practice this and make sure you get it right is to use the Visual Algo website and practice inserting and see what happens when you do index of 2, let's say 99. I hit go. See what happens here. You're going to have to code that action. Did you get that? Play around with this as you try and code the insert function. Like I said, a little hint that there's going to be some looping involved. You saw that in the demonstration or in the animation, there was some sort of traversal. So we're going to have to do some sort of traversal to find the index. And I also just want to code a quick print list function so that instead of using this way of printing our list, which as it gets deeper and deeper, gets harder and harder to understand, I'm going to just create a print list function that you should have access to make sure that your insert method is working. And this print list is simply going to just list our linked list, but instead of having this ugly printout, I'm just going to print it out in an array. So this is just going to be printed out in an array. All we're going to do is say const array. and this is going to be an empty array. We'll have a current node variable that will have this.head, so the first item in the list. And all we're going to do is do a while loop. Remember, this is similar to a for loop. We're looping, but instead we're saying while this is happening, while a condition is happening, run the below commands. So I'm going to say while current node doesn't equal to null, as long as there is a current node and we're not pointing to a null terminator, in that case, just simply add to the array.push, the current node value. That's it. We don't care about the pointers or anything. We just want to push to the array the value. And we want to then update the current node to equal current node.next. So we're going to keep going until the current node is going to be null, at which case we're going to stop. Again, while loops are really, really good if we don't really know the length of our linked list, or we just want to do something while a condition is met. So we can just simply return the array here. Let's see how that would work. If I do, and I'm going to comment out the insert here because we're not going to do that yet, I'm going to just say my linked list dot print list. If I run this, there's our list. So using the print list command to check your work, see if you can create this method. Good luck, and I'll see you in the solution video. Welcome back. Let's see how we can implement the insert method. And this was a tough one, so hopefully you got it. If not, at least you tried so that we can see how we want to implement the insert method properly. The very first thing I want to do is, well, first of all, check my parameters. And this is something that you usually want to do with all methods. I know we simplified things, and when we looked at prepend and append, we never checked whether the value was something that we wanted. But when it comes to inserting something, we want to make sure, especially that the index is a value that we understand, so our program doesn't give any errors. And there's many things that we can do for a check, and I'll leave it up to you to really implement really good checking. But the one important check that I think we should have is if index is greater than or equal to this dot length. So if I give an insert of, let's say, index at 200 and our list is only 3 items long, I want to be able to handle that properly. In this case, I'm saying as long as the index is greater or equal to this dot length, in that case, just add it to the end of the list. So if I say insert 200, value of 99, I'm just going to add the 99 to the end of the list. And you can implement different variations of this. Maybe you can return an error if you want. But to simplify things, I think this is good enough. And we can just say return this dot append, which we already have. We have to say this dot append because we're referencing a method in this class. So let's say this dot append. And we'll just add the value. There we go. So if I do 299 over here, let's add the print list at the bottom here. And if I click run, I get 99 added to the end of the list. But what if index was 2? Well, this now is the hard part. We want to first create the new node. And remember, we can create a new class instance if we wanted to, but in our case, we'll just create a new object that has a value of value and next of null. Nothing new here, we've seen this before. Here comes the tricky part. And I like to comment this out or at least visualize it so we understand what we're doing. We have 2 nodes that are connected. And then we have a new node that comes along and says, hey, I want you to insert me right in between here. What should the steps be? Well, the first thing we need to do is to actually figure out which node the first one is. Because remember, to insert something, we can pick whatever index we want. So if we want to insert an index of 2, we want to grab whatever is at index of 2. So we need to traverse our list and say 0, 1, 2 to find this node and get a reference to it. Otherwise, we don't really have a reference to it. Remember, a linked list only has reference to this head and this tail. So the very first thing we want to do is to actually get to that node. And we're going to call this first node the leader, because that's going to be the first node that we're going to connect this new node to. And this new node is now going to point next to the old node, or the node that was initially connected to the first node. So I'm going to say that this leader node is going to be, well, how can we get that? We need to somehow traverse one by one until we find the index we're looking for. And to keep the code clean, I'm going to create a new method. I'm going to say this dot traverse to index is going to be a new method that's simply going to get the index that is 0, 1, 2, and I want to grab the leader. So if I want to insert the number 99 in here, I have to make sure that 10 points to 99 and 99 points to 5. So that means I need to grab the index, not here, and point it to the leader, that is the 10, the leader that we want of the list. So all I'm going to do is -1. So point to the leader, and this traverse to index, well, we're going to have to create it. And I have the this keyword here because, again, it's a method onto this class. I'm going to say traverse to index. That's going to get an index. And this is where we do our traversal or looping. We might want to check for parameters here and make sure that it's a valid index. And that's something that you can do on your own. It's not very important for this example. We can assume that the index is going to be a valid number, a valid index. And in here, we're going to first have to do something like a counter. That's going to equal to 0. And we're going to say that the current node, and this is something we did similar to the print list. We're going to keep the current node as this dot head. And while the current, or while the counter doesn't equal the index, because we're saying keep traversing, go from the beginning, from the head, all the way until the counter is equal to the index. So keep going through the while loop as long as the counter doesn't equal the index. But as soon as the counter becomes the index, so while we reach the point that we want, in our case, traverse to index -1, that means as soon as we get to 10, then stop. But until then, I want you to traverse through this. So current node is going to equal current node dot next. So we're going to keep moving the current node over to the right, and we're going to increment the counter one by one. That's it. That's our traversal. All we need to do at the end, because we want to return something from this method, is to return the current node. And there we have it. We say traverse to the index. In our case, if we do insert to 99, it's going to receive to 99 here. It's going to create the new node, and it's going to traverse to index. 2 minus 1 is 1, so it's going to say 0 and 1. And counter is going to equal index, so it's going to exit out of this loop, and it's going to return the current node, which is 10. We grabbed a reference to the leader. Congrats. But we're not done yet, right? Once we grab the reference to the leader, what do we do next? Well, the next thing is we want to make sure that we grab the next item in this original list. That is, we want to hold a pointer to number 5. Again, we don't want to break this list. We want to make sure that the connections are working properly and that 99 comes after 10 and after 99 comes 5. So the next step we want to do in our insert method is to what I call hold, or let's just call it holding pointer. I could probably name that better, but holding pointer is nice. And we'll say leader.next. Leader.next is 5. And this 5, we now have it referenced in this variable that we'll have temporarily. Next, because we have 5 saved to this variable, referenced in this variable, we can now update the leader.next to point to our new node. So I can say leader.next is going to now point to new node. And remember, because of how references work, we've deleted the reference of 5 here. So 10 no longer points to 5, but we've saved the reference to it in here, in this variable. So right now, if we go back to our example here, we've removed the reference to this, and now 10 points to this node. That's better spacing. There you go. Okay, what do we do next? Well, we now need this node, this new node, to point to this one. Like this. And that's pretty simple, right? We simply say new node.next is going to equal the holding pointer, the 5 that we are keeping in memory. And then finally we say this dot length plus plus because we've added to the list. And we can return this, or just so we know we did it properly, I'm going to say this dot print list. Once we insert something, we're going to just print the list. Let's see if that works. I'm going to remove this so the code works and we don't need the print list. Let's run this command. Hey, look at that. So before we had this list, and let's actually print list here so we can see it. My print or my linked list dot print list. This is what we had before, and we added 99 in here, just like that. And just to test it out one more time, if I do my linked list dot insert again, and this time we'll give it 20, which doesn't exist, index of 20, and add 88, that should be added to the end of the list. And because with this insert, when we do the if check, we're just adding the this.append, which isn't printing the list. Let's just add a print list at the bottom here to make sure that that is working. There you go. 88 at the end. Very, very nice. I know that was challenging, and insert is probably the toughest function to implement or method to implement in a linked list. But practice this a couple of times, really understand what each step is doing, draw it out if you need to. But congratulations, we just implemented an insert function into our linked list. And you might notice here that we had to traverse where we had a while loop. And this might make sense now, right? Why we had the insert as O of n? Because we had to loop through our list. And lookup, which can also be called traversal, was also O of n. That was our traverse to index, right? If we're looking for an item at index of 10, for example, we'd have to look up. And the worst case is that we had to go through the entire list. Same with insert. All right, now that we've done the insert, you should be able to do the next one on your own. That is delete. Using something very similar to what we did with insert, let's add a delete, or I like to call this remove. Let's have a remove that has the parameter index of what you want to remove. Good luck coding this, and I'll see you in the solution video. Bye-bye. Welcome back. How did it go with the remove method? It should be fairly easy since we got the insert method, right? All we need to do is first check the parameters. And we might want to check whether the index is a positive number, whether the index is higher than the length, but that's something we've already talked about. So let's get to the meat and potatoes, the main part of remove. All we need to do is once again get the reference to our leader. So that is if we want to remove, let's say 99. So that is index of 0, 1, 2. In that case, we want to make sure that we remove the 10 to 99 pointer and instead point 10 to 5. And because of how memory works in garbage collected languages like JavaScript, as soon as we remove that reference, 99 is going to get deleted. So all we're saying now is remove this pointer and then just update this to point to this list, and this gets deleted. I hope that my little diagram there makes sense. Let's code this out. Well, we first find the leader just like we did in our insert function by using this dot traverse to index. So I'm going to say this dot traverse to index, index -1, and we have the leader. Now, we have the leader, and we can point 10 to now point to 5, but we need a reference to this 5. And the way we get that reference is to say const unwanted node, that is the node we want to delete, is going to have leader.next. That is, the unwanted node is going to equal leader.next, which is 99. And we got that variable, so we can do leader.next to equal unwanted node.next. So we grabbed the leader, and then we said, this node that I want to grab it here by using leader.next, and then make sure that we get the pointer, that is 99 to 5, which is unwanted node.next, which equals to 5, the 5 node, to now be pointed from leader.next. And of course, so we don't forget, we have to decrease the length because we're removing a node by doing --. And we can just return this dot print list here. That wasn't too bad, was it? Let's go down here and make sure this works. I'm going to say that we want to my linked list dot remove at index of 2. So let's remove the 99. I'm going to run this. Look at that. We've removed 99. If I run remove again at index of 2, that is to remove 5. Oh, not print list, remove. And we click run, 5 gets deleted. Very, very cool. And once again, we know why delete is an operation of O of n, because we have to traverse to index. And going back here, we now have a better understanding of how this diagram works. If I remove the tail, we have to traverse through everything, one by one, until we hit the tail, and then just remove it, and there we have it. And I encourage you to play around with this animation a little bit more, having our linked list implemented. There are other methods that we can add to it, but these are the main ones of linked list that you can see. And this should give you a better idea of how we calculate big O notation with linked lists and where some of the drawbacks are. I mean, you can explain data structures for a long time, but without actually coding it yourself, it's hard to see why some operations take longer than others. And linked lists are very popular in interview questions. And now you have the tools to build your own linked list. in a language that doesn't even have it natively, like JavaScript. Well done getting this far. In the next video, we're going to introduce you to the second type of linked list that I mentioned at the beginning. Up until now, we've created singly linked lists. But there's also a doubly linked list. What does that mean? For that, I'll see you in the next video. Bye-bye. Welcome back. Up until this point, we talked about singly linked lists, and we should have a good idea of how they work. But what is a doubly linked list? Doubly linked list is similar, except that it links to the node before it. Let's have a look at a little animation here. We have a head node. Let's say we just have one node. You see that we have an extra block here. We're not really sure what this does yet. Now, if we wanted to add a new block to this list, a doubly linked list, and we wanted to add a node that contains the value 10, well, we would now have a pointer to the next node. We'd also have a pointer, this is the new part, to the previous node, and the new node is going to point to null. And this now becomes the tail. If we added another node, well, we'd have the 10 node point to the new node. We'd also have the new node point to the previous node. And then finally, that becomes the tail, which means it points to null. And that's what a doubly linked list is. It has an extra little block here, an extra piece of data that also links to the previous node. Now, why do you think that's important? Doubly linked lists allow us to traverse our list backwards. So up until now, we were only able to go from the beginning all the way to the end. With a doubly linked list, I can start from the end and go backwards. In a singly linked list, there is no way for me to know what comes before 10, what comes before this node. In a doubly linked list, that is no problem. It's exactly the same as a singly linked list, but contains this additional pointer to the previous node. And searching through a doubly linked list can actually be a little bit more efficient. And lookup can technically be O of n divided by 2, because we can start at both ends, and if we know in which half of the list what we're looking for is, we can pick the optimum place to start. Now, the lookup here is still O of n, because if you remember with our rule book with O of n divided by 2 is still O of n. But it's still technically a little bit faster. Now, the downside to a doubly linked list, as you can see, is that we might have to hold a little bit more memory, an additional block of memory. And we have a video talking about when to use doubly linked list and a singly linked list later on. But to understand this properly, I think we should convert our singly linked list that we created in the previous videos to a doubly linked list. So let's go have a look at how to do that. I'll see you in the next one. Bye-bye. Welcome back. We have our original linked list, and we just found out that our linked list is actually a singly linked list. But we want to convert this now into a doubly linked list so that we add that extra feature of an extra pointer. How will we go about doing that? Well, let's go line by line. And luckily for us, it's not that difficult. As you can imagine, if we go line by line and go into the constructor, the one extra piece of information that we need to add now is that we also have a previous pointer now. And this previous pointer will be null to begin with. So the head is going to point to null. And everything else stays the same. But what happens when we append something? Well, once again, we're going to add a new node that also has previous property, a new property that points to null. And we're still going to have the tail.next equal to the new node, and this doesn't change. But the only line that changes is that we need to add a previous property, because remember, append is adding at the end of the list. We want to add the previous property to equal whatever was at the end of the original list before we did the append. So all we would need to do is say new node dot previous is going to equal this dot tail, the very last item, before it gets updated over here to the new node. Let's see if append works the way we have it. I'm going to scroll down here and just comment out all of this code except for the first two lines, append 5 and append 16. If I click run here, I get a doubly linked list that has a head of value 10, okay, that points to next, which is the next node. We see value 5, that points to an object that we don't really know yet, and also points to a previous object. And within this 10 node, we see that previous points to null because there's nothing before the head. If we look at the tail, we see that the tail now has a value of 16. Next is null because it is the tail, it's the end. But the previous node is also pointing to this node 5. And the doubly linked list has a length of 3. Very cool. So all we've added is this previous reference. Let's do the same for prepend, that is to add at the beginning of the list. If we scroll up to prepend, we once again want to add a new property, which will be the previous. That will equal to null for now. And we want to keep everything the same. We want to make sure that the new node.next is going to point to whatever the head is currently. But we also want to say that this.head.previous, the previous should now point to our new node because it's no longer the head. And then we can update the head to be our new node, and this.length is going to increase, and we're going to return this. If I click run here, remember we're prepending 1, so we're adding 1 to the beginning of the list. We see that our doubly linked list now has a head with the 1 value. That's pointing to the next value, which is the 10. And our tail is still the same. Tail is 16. That points to the value of 5. So if we print list here, again, 1, 10, 5, 16, as we expected. What about the insert? How would that work? If we go to insert method here and go line by line, this first part, everything's okay. We have a new node, so again, we'll add a previous property. That will be null for now. We're still grabbing the leader and traversing to the index. But now we have to do things a bit differently. We need to grab the leader as well as the follower. So if we wanted to add 99 here, we need to grab a reference to 10, the leader, and also the follower, 5. So I'm going to change the name of leader.next, that is 5 over here, to say follower. So the leader of our new node and the follower of our new node. Now follower is now going to be the 5. We're going to update leader.next, so that is 5, or leader.next, which is what comes after 10, to be the new node, our 99. And then new node.next is going to equal the follower, that is 5. But we also want to make sure that our new node dot previous is going to equal the leader, that is the 10. And also make sure that the follower, that is the 5, has a previous value that points to our new node. So if I print list here with our insert, I've inserted the value, but just to check that everything is working, I'm going to console.log this, which is our linked list. If I click run, I see that our linked list has a length of 5, and I'm going to change this to index of 1 so we can see it in our output here. I'm going to say index of 1. If I click run, I see that head is now value of 1. The next in the item is value of 99, as we expected, and it has both next and previous properties. And that's not too bad, right? As long as you visualize the steps and draw your diagrams, all we're doing is saying add the new node or get the leader to point to the new node. The new node should now point to the leader, and the new node should point after it next to the follower, and the follower is now going to point back to the new node. You might have to go through this in your head or draw it out on a paper, but it should make sense now. And at the end of the day, singly linked lists and doubly linked lists aren't that different. As you see, all we're doing is just managing another pointer that points to the previous node. I'm going to leave the remove linked list up to you to implement your own in the doubly linked list as you've learned up until now. It shouldn't be very different from what we did in the insert. But I hope you have an understanding of how linked lists work now. Interviewers love asking questions about linked lists because it requires a lot of information to be held in your head. And as you can see, they can be really complicated if you're not the type of person that thinks clearly through their steps and understand what they're doing one by one. And the steps are really important. That's why interviewers love this question, because they really get to see how you think. And with linked lists, as long as you draw out what you're doing step by step, it becomes really, really easy as long as you don't just start coding it out from memory. Just draw out the steps, think about your steps, and the interviewer will be impressed. I'll see you in the next one. Bye-bye. Welcome back. We've learned about singly and doubly linked lists. So let's talk about when you should use one over the other. Let's start with the singly linked list. The pro of a singly linked list is that it's a fairly simple implementation, especially compared to the doubly one. It requires lesser memory, as we can see here, less block. And because there's less memory when we do things like delete and insert, because there is technically less operation, we don't have to move around the previous property, it's a little bit faster. Now, the downside with a singly linked list is that it cannot be iterated in reverse or traverse from back to front. If we ever lose the reference to this .head node of the list can actually be lost in memory forever. So singly list is appropriate to use when you have less memory or memory is really expensive and you want to be careful of how much you use. And your main goal is that you want to do fast insertion and deletion. And you don't really have that much searching, especially when you have insertion at the beginning of a list. A doubly linked list, well, the good side of it is that it can be iterated or traversed both from the front or from the back. Another beauty is that if you need to delete a previous node, you don't need to traverse from the head node and find what the previous node is, which a singly linked list has no concept of. You can do that fairly easily with a doubly linked list. Now, the downside is that it is fairly complex, as we saw, to implement, and it requires more memory and storage because of this extra property. And there are some extra operations that we need to perform to make sure that when we do insert and delete, that the previous property is updated as well. So doubly linked lists are really good when you don't have that much limitation on memory. and when you want good operation for searching for elements, such as searching backwards instead of just forwards. Most of the time in interview situations, you're going to see singly linked list. You may be asked a theoretical or broad question about the difference between singly and doubly linked list, but most of the time, this is what you're going to see. All right, I'll see you in the next video. Bye-bye. Welcome back. I have a fun little exercise for you. And I know I call every single exercise fun, but I think this one is especially fun. Now, one of the most popular interview questions when it comes to linked lists is to reverse a linked list. What do I mean by that? Well, an interviewer is going to say, we have a linked list here. How would you go about reversing this list? If I have a list over here that is 1, 10, 16, 18, how can you make the list, the linked list, go from 88 to 16 to 10 to 1? How would you reverse it and flip it? And we're going to use a singly linked list for this exercise. And all we want to do is create a new method that is going to say reverse. And this method in here will have to do some magic that will reverse this for us. Remember, we're not just printing out an array. We want a reversed linked list that now has 88 referencing 16, that has referencing or pointing to 10, and 10 pointing to 1, and 1 pointing to null. How would you go about doing this? Good luck with this exercise, and I'll see you in the solution video. Bye-bye. Welcome back. We have our list over here, and we want to be able to run my linked list.reverse that will reverse this list for us. Let's figure out the code here. The first thing we want to do is to do a bit of a check. Imagine if we only had one item in the list. If there's one node or item in the list, then, well, we don't need to really reverse it. It's already there. So if this list only contained one, just return whatever we have for now. So let's do that check here. And we can just say if this.head.next, and this exclamation mark means doesn't exist. That means if this head.next, if one is only one and it's null, this exclamation mark is going to turn this into the opposite, which the way JavaScript works will turn this into true. I know it's a little bit confusing, but hopefully you're with me on that one. All we're saying is if this is the only node and there's only a head node here, I could also do this by checking the length, and we have the length property. So I could do something like if this dot length is equal to 1, but let's just keep it the way it is for now. If there is only one element, just simply return this dot head, the node, or we can just return this as well. Otherwise, let's get into the fun coding part. The first thing we want to do is say we want to have the first item equals to this dot head. And we're just keeping track of it here. So we're going to say that we now have a reference to this dot head. And we also have a reference now to the second item in the list. So this is going to be first dot next. So now that we have first and second, we can do some looping. We can say while the second node exists, that is, as long as second is not null. So as long as that's happening, we're going to create a temporary variable that holds second dot next. So we can actually call this third if we want, but I'm choosing temp because this is going to change. So we have a reference to first, second, and third. So 1, 10, and 16. From here, we can now say second dot next is going to equal the first element. First is going to equal the second element. And second is going to equal the temp element. Oh boy, what just happened here? I know that was a lot of code without a lot of explanation. But let's go through it line by line. We're looping here after we've grabbed 1 and we've grabbed 10. And now I'm going to say as long as this second variable has a value and it's not null, if that node exists, then I want you to create a temp variable that holds 16. From there, I'm going to grab that second.next, which is the property inside of 10. And I'm going to say that 10 is now going to point, so second.next is going to point to the first. So 10 has an arrow pointing to 1. And the first variable, which was the head, now becomes 10. And the second item becomes 16. We've switched the pointers. 1 to 10 now goes 10 to 1. And we've switched the variables, first and second, to now have 10 and 16. And we loop through and do the same thing where we have the pointer 10 to 16 reversed, so that 16 points to 10. And we change the variable so that it's 16 and 18. So we loop through this, we loop through this, we loop through this. And then the final thing we need to do is to say that this dot head, because this dot head still has the value of 1 in it, we're going to say that dot next is going to equal to null. We're going to have 1 point to null, and this dot head now is instead going to be the first. And remember, by the time we loop through everything, first becomes 88 and second becomes null. So we are now changing at the very end 88 to be equal to the head. And we also want to make sure that the tail is now 1. And the way we do that, we have to go before the while loop and see here that this dot head, this first item, should be the tail now. So at the beginning, before we do the loop, the tail become this dot head. Right. I know that was confusing, but let's see if that works. This is one of those problems that you really have to draw it out. And just by looking at this code, it's really hard for you to understand what's going on. I recommend that you code this along and step by step, perhaps console log to understand what's going on. If I reverse this list and click run, I get undefined because we have to return something. So let's return this dot print list. I'm going to run this. All right, let me just make sure that we're reversing. I'm going to comment it out. So we have the original list, 1, 10, 16, 88. If we reverse it, we have 88, 16, 10, and 1. And just for good measure, instead of printing list, let's just return this here. So we get the entire linked list to make sure everything is working properly. I have a linked list that has a head value of 88 and a tail value of 1. Looks like it's working. Awesome. Good job getting this far. And if you're able to understand this, I think this is probably the most difficult concept to understand in this entire course. So if you're able to get this, good job. If not, you might have to watch this video a couple of times. In the end, and this is the beauty of programming, all we're doing is logical steps. And no matter what language you use, whether it's JavaScript, like we did in this case, the steps to create a linked list are the exact same. Syntax may differ, but the logic is the same. I'll see you in the next one. Bye-bye. Welcome back. In this section, we learned all about linked lists. We learned how it doesn't come pre-built in a lot of languages, such as JavaScript, but it does in others. That is because linked lists are low-level data structures. It's used a lot actually in other data structures like hash tables, and as we will see in some of the upcoming ones, such as stacks and queues that we're going to talk about. It is a fundamental data structure that is very, very useful in computer science, and also a very popular question when it comes to interviewing. We learned that when it comes to linked lists, there's no random access, in the sense that when looking for something, you have to actually traverse the list. With hash tables, we can find things right away. With arrays, we can find things through indexes. We have slow lookups. We have to traverse through the list if we're searching for something. However, they are ordered, unlike hash tables, and linked lists allow us to have this sort of order. If we had a large number of items in an array, and we keep adding to that array, we'd have to have excessive overhead costs copying the array in memory and doubling up the space when it reaches the limit to create a larger array. Versus a linked list where we can have a fast insertion and fast deletion, especially once we have a reference to where we want to insert or delete that node. This also becomes really, really fast when it's at the beginning of a list or the end of the list. And we're going to see that coming up when we talk about stacks and queues. The primary reason to choose a linked list over something like an array is simplicity and ability to grow and shrink as needed. Now, working with them, as we saw, can be a little bit weird and difficult to just manage all the pointers in your head, but they are pretty lightweight and self-contained in that they can be quite flexible as well. That's why you're going to see linked lists in a lot of places, like implementing file systems on your computer, or even browser history, right? When you go back and forth on a browser, you can think of that as a linked list because you can traverse one by one from one place to another. And remember with our hash tables, how we had this issue of collision. And when we had a collision, we had to do something like this, where we combined John Smith and Sandra D into two nodes, and the first node pointed to the second node. If we go back to our hash table data structure that we created, if we scroll down to the set method, where we set a key and a value in the hash table, we did a check here to check if this address exists, and then afterwards we used an array to push our items in case we had multiple items when we had a collision, because sometimes we can set our hash table memory size to be a lot smaller, like 2. And you might be able to see why now, instead of using an array, which every time we need to insert a new item, I mean, it works because we're pushing to the end. But if we had to delete an item on the hash table, we'd have to unshift the array, which, as you know, is very slow. So we can modify this now to something like a linked list so that a delete becomes a lot easier than if it was an array. And that's something that I'll leave up to you. But you should have a good sense of why these data structures exist now and why you might want to use a linked list over an array. We also added another piece of the puzzle in our mind map. We've talked about arrays, about hash tables, and now we talked about, if you see over here, linked lists. Our singly and doubly linked lists with their big O notation. And just a hint here, as you can see, linked lists are related to something we're going to talk about coming up. That is trees and graphs. But at the end of the day, we've just managed to add another data structure to our tool belt as engineers. Congratulations, and let's learn about more data structures in the next video. Bye-bye. Welcome back. Let's talk about some new data structures over here. We have stacks and queues. queues with probably the most confusing spelling of all time. Don't worry, even I, who am fluent in English, have a really difficult time spelling this, but it's queues. Anyway, don't worry, the data structure itself is not as confusing as the spelling of this data structure. We're going to learn two at the same time, stacks and queues, because they're very similar. They are both what we call linear data structures. And linear data structures allow us to traverse, that is, go through data elements sequentially, one by one, in which only one data element can be directly reached. And this will become more clear to you as we talk more about stacks and queues throughout the next couple of videos. Now, the reason that these are very similar is that they can be implemented in similar ways, and the main difference is only how items get removed from this data structure. You see, unlike an array, in stacks and queues, there's no random access operation. You mainly use stacks and queues to run commands like push, peek, pop, all of which deal exclusively with the element at the beginning or the end of the data structure. Now, after I said that, what was your first thought? Does it kind of sound limiting that with stacks and queues, we usually only can access the first or the last element in the data structure? Why would we ever want to use something like this? And this is an important topic in computer science. You will see that we can build things like stacks and queues, which are using arrays or linked lists. Except, unlike arrays and linked lists, we have less methods or less actions that we can perform on stacks and queues. And sometimes it's good to have these higher level data structures that are built on top of lower level ones like linked lists and arrays to limit the operations you can do on them. That's actually a benefit. In computer science, having this limited ability on a data structure is an advantage because you can control that whoever uses this data structure performs only the right operations that are efficient. If you give somebody all the tools in the world, it's a lot harder for them to operate than if you just give them 2 or 3, so that they know exactly what they need to do. Now, let's talk about stacks and queues throughout the next couple of videos to really understand how they work and then finally code our own. I'll see you in the next one. Bye-bye. Let's talk about stacks. Stacks is a type of data structure that, well, you can think of them as plates. That is, we have one piece of data, and then another piece of data comes along and gets stacked on top of that piece of data. And it keeps going, keeps going, keeps going, and keeps going. You can think of it as these plates stacked on top of each other vertically. And you can only touch the top plate. You can't really access anything from the bottom over here. The way you can access data from a stack is to grab the first plate, then the second plate, then the third, and you keep going and you keep going and you keep going until you've gone through all the stack. And this is called LIFO, or last in, first out, because the last item that comes in is the first one that comes out. And you're thinking to yourself, why is this useful? When would we actually use something like a stack? They're actually useful in quite a surprising number of ways. They're very good, obviously, when you need to know the very last value that was seen or added. And stacks are very important in language-specific engines. You might have heard of something called Stack Overflow, a website that a lot of engineers visit. And I'll actually include a bonus video after we talk about queues of how the JavaScript engine works using stacks and queues, and how you might get Stack Overflow when you write bad code. Now, most programming languages are modeled with the stack architecture in mind. And when functions get called in a programming language, usually they follow this model of last in, first out. A function within a function within a function gets called, and then we start popping those functions until we get to the very beginning. And don't worry, this is going to be a little bit more clear when we actually code our own stack. Another useful way that we might use stacks is such as browser history, right? When you go back and forth from one website to another, and then you hit the back button or the front button, that's using stacks. Or maybe you're writing a piece of text and you want to undo something. So you can click the undo option to go back, or forward to redo. Ever wonder how that works? Well, the idea comes from stacks. That is, you store the previous state of your work in the memory in such an order that the last one appears first. This is something that we can do with stacks. As you can see over here, stacks usually come with 3 types of methods. There's a few others, but these are the main ones: pop, push, and peek. Pop is remove the last item, that is, remove the plate. Push is add a plate, and peek is simply view the topmost plate. I've added lookup in here just to show you that it's big O of n, because you usually don't want to traverse through an entire stack. But just so you know, if we wanted to do that, it's going to be a heavy operation. Let's talk about queues in the next video. Bye-bye. Welcome back. Queues are our next data structure. And the best way to think about them is like an entrance to a roller coaster. The first person that arrives in line gets to go first on the roller coaster. And then the second person gets to go, and then the third person gets to go. Then the fourth, the fifth, and the sixth finally gets to go. So it's the opposite of stacks in that we access first in, first out. The first item in the queue gets access first, that is, first out. We call that FIFO. And queues are used, again, a lot in programming problems and interview questions. For example, if you had any sort of waitlist app to perhaps buy tickets for a concert, that uses queues. What about a restaurant app where you check into the restaurant to see if you can get a table? That uses queues. What about Uber or Lyft when you want to grab a ride? Well, the person that requested the ride first will get priority, and then you'll get second. And then finally, the most common example of queues is a printer, right? If you had a printer at home and you had 3 people on 3 different computers at your home, let's say your family members, and you press print and each person prints different items, the person that clicks print first should have their first printout. And same for the second person that goes next, and then the third person. Now, on the right here, I have a couple of words that are different than push and pop. And I'm using a bit of standard here. You can use push for enqueue, which means add to the queue, that is add a person in line, which is O1, and dequeue, which you can think of as pop, which is remove person from line. However, dequeue, unlike pop, doesn't take the last person in line, it takes the first person. So that's where stacks and queues differ, and we have these names to make sure that we understand the differences. But we have peek, which once again tells us what's the first item that's going to come out. That is the first person in the list, versus a queue that is the last plate, which was the last in, first out. And once again, lookup in a queue you usually don't do because you're only interested in enqueuing and dequeuing. You can see here that our big O notation is quite fast. We're actually going to demonstrate this in code, but I want you to try and answer this question. Why would you not want to use an array to build a queue? Pause the video if you want to think about it. Well, the answer is that it's very inefficient because we're removing the first item from the list. If you remember, arrays, if you unshift something, you remove the first item, you're going to have to shift all those indexes. So creating a queue from arrays, although you can do it, is really, really bad. And that's something we'll talk a little bit more about when we actually code it. Okay, that's enough for queues. Let's go on to our first exercise. Welcome back. Let's do a quick exercise before we actually create our own stacks and queues, because JavaScript doesn't have its own stack or queues data structure. Now, I mentioned that there's two ways that we can build stacks and queues. If we talk about stacks, we can think of it as our browser history. Let's say we visit Google first, then we visit udemy.com, and then we visit, let's say, YouTube. In a stack, because Google was the first item, it would actually be placed on the stack like this. Then we go to Udemy, so we'd be placed on the stack on top, and then we go to YouTube. Now, if we want to go to a new website, let's say we go to Twitter, but then we decided, no, that's not what I wanted to do. I want to go back. Well, we remove Twitter, press back button on our browser, and we get to YouTube. If we press back again, we get to Udemy, and then back again, we go back to Google. So Stacks has a top and a bottom, and we can build it with either arrays or linked lists. My question to you is, why would we want to build stacks with arrays? That is, we'll create a class of stacks that has the data being held in arrays versus using linked lists, and vice versa. Think about that. What about queues? Let's say we have a queue. I'm creating a waitlist app. And in here, we have a couple of people that want to get on the waitlist. The first person that shows up is Tim. And then after Tim, or you know what? Let's use our names. Let's use Matt. And then Matt shows up, but all of a sudden, Joy comes and lines up. And then perhaps we have Samir that comes and waits in line, and then we have Pavel. In this case, we want Matt to be first, then Joy, then Samir, then Pavel. And with queues, we can once again use arrays and linked lists to implement it. Which one do you think would be better for queues? Is there one better, or are they both equal? I want you to think about this. In the next video, I'm going to answer this for you, but I recommend taking time to think about what you know about arrays and linked lists and how they might benefit or might not benefit stacks and queues. I'll see you in the next video. Bye-bye. Welcome back. How did you do in that exercise? Let's have a look at the solution. Let's start off with stacks. I said that with stacks, they can be implemented using arrays or linked lists. In this case, both arrays and linked lists are going to work fairly well. In the end, it depends on what you prefer and what your priorities are. And by this point, you should understand the pros and cons of arrays and pros and cons of linked lists. So we don't need to go into much detail since we've talked about it before. But one major thing is that arrays allow something called cache locality, which makes them technically faster when accessing its items in memory because they're right next to each other, versus a linked list that has them scattered all over memory. And also, linked lists have extra memory associated with them because we have to hold on to those pointers. But on the other hand, they have more dynamic memory, right? And we can keep adding things to the list versus an array where you have either a static array or dynamic array that has a certain amount of memory, and as soon as it's about to reach its limit, it's going to have to double up that memory and create new space for it somewhere in memory. So you have to think about what sort of operations you're going to do and what your priorities are to decide which one you want. But they could both work. And we're going to build a stack data structure with both of these coming up. Queues, on the other hand, is a very simple answer. You would never want to build it with an array. Or if you do, well, that's not necessarily a good idea. And ideally, you want to implement them with linked lists. Why is that? Well, if you remember, arrays have indexes associated with them. So if we had Matt here, then we have Joy, then we have Samir, then we have Pavel that are in queue. If this was in an array data structure and Matt was the first in line and we need to remove Matt from the queue, well, once we remove Matt, we now need to shift the indexes over. So we have to go one by one and say, all right, Joy is now here at index of 0, Samir is at index of 1, and Pavel is at index of 2, and there's nothing at index of 3. We just unshifted those arrays. It's an O of n operation, a linear time. Versus something like a linked list, where all we have is a pointer to the head, and then perhaps we have a pointer to the tail. And all we need to do is say, head, well, is Matt. We want to remove Matt, and Joy is going to be the head, and nothing else changes. And that's an O of 1 operation, or constant time. I hope you are able to get the answer. Otherwise, at least now you know, and this is a very common interview question that you might get asked, that hopefully you have an answer to now. But enough talking. I think it's time for us to build these data structures from the ground up. I'll see you in the next video. Bye-bye. How does JavaScript actually work? Imagine getting this question during an interview. Or how about this? Explain the difference between asynchronous and synchronous in JavaScript. Or maybe they ask you to explain the statement, JavaScript is a single-threaded language that can be non-blocking. Oh boy. In this video, we're going to help you answer those questions. This is a video you may need to visit a few times as you progress to really get it. So don't feel discouraged if you don't feel 100% confident. Just keep watching it and you'll get it. Now, we don't need to know how JavaScript works internally to write a program, but it is important to learn. I see a lot of people who have been developers for years and not know this. It's like being a pilot and not knowing how an airplane can fly. Okay, that's a little bit dramatic there, but you get my point. So let's start. First, what is a program? Well, a program has to do some simple things. It has to allocate memory, otherwise we wouldn't be able to have variables or even have a file on our computer. It also has to parse and execute scripts, which means read and run commands. Okay, now we also know that from our previous discussion, there's the JavaScript engine that each browser implements. In Chrome, it's the V8. And the V8 engine reads the JavaScript that we write and changes into machine executable instructions for the browser. Now, the engine consists of two parts, a memory heap and a call stack. Now, the memory heap, this is where the memory allocation happens. And don't worry, we're going to talk about this. And then the call stack, this is where your code is read and executed. It tells you where you are in the program. So let's simplify this and show you what I mean. I have Sublime Text over here. And for us to allocate memory in the memory heap, well, it's as simple as doing const a equals to 1. We've just allocated memory. Now, when we assign this, the JavaScript engine is going to remember that, oh yeah, a has a value of 1. We've just used up the memory heap. And I can keep going on and on like this, right? I can keep copying and pasting and changing these variables to B and C, and I can change the values to 100, and maybe here will be 10. Cool. Now, what's an issue that we see with this? There's something called a memory leak that you're going to hear as you become a developer. And what we've done here is we've created all these variables, these global variables that are in the memory heap. But you see this box, right? And with all memory, we have a limited amount that we can actually have. So by increasing the number of variables that we have, imagine if I had just this page full of variables, and instead of just numbers, they're like very, very big arrays. Well, memory leaks happen when you have unused memory, such as, let's say we're not using the variable a, but it's still there. Well, by having unused memory just laying around, it fills up this memory heap. And that's why you might hear why global variables are bad. Global variables are bad because if we don't forget to clean up after ourselves, we fill up this memory heap, and eventually the browser will not be able to work. All right, so that's memory. Let's talk about the call stack. What is that? Well, again, with a call stack, we can have something like this. Console log, we'll go 1, console log 2, and then finally console log 3. If I run this code in my browser terminal, well, I get 1, 2, 3. So the call stack, if you remember, that's what reads and executes our scripts. So what the call stack does, it reads the first line, console.log, it gets put in this call stack. So the JavaScript engine says, ooh, console.log has been added. Let's pop it onto this call stack. And then it runs it and creates 1. Then it says, okay, I'm removing the first console log because I just finished running it. I'm going to place the second console log into my call stack, adds it on here, and says, yep, execute 2. And then it removes that, it pops it, and then gets console log 3, and logs console log 3, and then finally removes it. But let's have a bit more of a complex example here to demonstrate this point. Imagine I have something like this. I have a function, const1, and inside this function we have another function, const2, and for now it's not really going to do much. It's going to console.log 4. And then in here, we'll just say we run the 2 function. So if I copy and paste this and place it into our console, and I run 1, I get 4. And ignore this error here, it's just related to my app in the browser. But you see that we get 4. So what happened here according to the call stack? Well, if we have the call stack here, we first ran the 1 function. So on top of the call stack, the 1 function gets run. And as we enter into this call stack, we see that we run another function, 2. So 2 goes on top of the call stack. And now we run the 2 function, which is console.log. So we have console.log 4 that's run inside of the 2 function. So now that we've read this, the call stack is going to say, okay, there's nothing else inside of this. I'm going to run console.log 4. So it's going to print out number 4 here. It's going to remove that from the call stack and then remove the 2 and then remove the 1 because it's just been called. And the call stack is now empty. All right, awesome. Now let's revisit the statement from the beginning of the video. JavaScript is a single-threaded language that can be non-blocking. Single-threaded means that it has only one call stack and one call stack only. It can only do one thing at a time. And as you saw, call stack is first in, last out. So whatever's at the top of the call stack gets run first, then below that, below that, below that, until the call stack is empty. Now, other languages can have multiple call stacks, and these are called multi-threaded. You can also see how that might be beneficial to have multiple call stacks so that we don't keep waiting around for stuff. Why was JavaScript designed to be single-threaded? Well, running code on a single thread can be quite easy since you don't have to deal with complicated scenarios that arise in multi-threaded environment. You just have one thing to worry about. And when I say issues with multi-threaded environment, you can have such thing as deadlocks. Now, guess what? You just learned what synchronous programming means. Synchronous programming simply means line 1 gets executed, then line 2 gets executed, and then line 3 gets executed. The latter can start before the first finishes. So this console log 2 doesn't start until console log finishes. And console log 3 doesn't start until these above 2 finish because, well, we've looked at the call stack because of the call stack. Now, you may have heard of the site Stack Overflow. If you're a developer, you use it on a daily. And have you ever wondered what Stack Overflow means? Well, Stack Overflow is this: when a stack is overflowing, kind of like we talked about memory leaks and how the memory heap of a JavaScript engine can overflow. Well, with Stack Overflow, this happens when the call stack just gets bigger and bigger and bigger until it just doesn't have enough space anymore. How can we do that? Can we recreate a Stack Overflow? Yeah, I can show you quickly that to create a Stack Overflow, all you have to do is function foo, like we have in here, and this function will just have foo. And we're just going to run our foo function. All right, that looks confusing. What is happening here? This is something called recursion. And recursion means a function that calls itself. So if you look at what this function does, we run foo and foo gets executed. What foo does is, well, we run foo again. So it just keeps looping over and over and over, having a recursion, but there's no end in sight, right? We keep adding foo to the call stack. We keep adding it over and 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 over. And we have a Stack Overflow. So if you want to have fun, go into your browser, go into your console, and run something like this and see what happens. You're going to get a Stack Overflow. All right, so hopefully this now makes sense. The JavaScript engine, which is the V8 engine in Chrome, has a memory heap and a call stack. Now, JavaScript is single-threaded. Only one statement is executed at a time. But there is a problem now, isn't it? What if line 2 was a big task we needed to do? Maybe loop through an array that had millions of items. What would happen there? Well, we would have this console log execute, then the second line that is a massive job will just work there. And console log 3 will take a really long time to get logged. And in our small example, that doesn't mean much, but if you had this on a website, well, the user wouldn't be able to do anything. The website would pretty much freeze until that task is done and the user just waits there. That's not very good, is it? Well, with synchronous task, if we have one function that takes up a lot of time, it's going to hold up the line. Imagine a buffet restaurant, right? If all the people want to eat, but Bobby says, hold on guys, I have to keep eating and putting bacon on my plate, well, everybody has to wait in line. So it sounds like we need something non-blocking. Remember, our first statement that we made in this video, JavaScript is a single-threaded language that can be non-blocking. Ideally, we don't wait around for things that take time. So how do we do this? Well, asynchronous to the rescue. Think of asynchronous like a behavior. Synchronous execution is great because it's predictable. We know what happens first, then what happens next, what happens third. But it can get slow. So when we have to do things like image processing or making requests over the network like API calls, and don't worry, we're going to talk about this in future videos, we need something more than just synchronous tasks. All right, so you're thinking to yourself, Andre, how do we do asynchronous programming then? Well, let me remove some of this clutter. We can do asynchronous programming by doing something like this. Set timeout, which we're going to talk about, is a function that comes within our browsers, and it allows us to create a timeout. And we can just give it the first parameter is the function that we want to run, and then the second parameter is how many seconds we want to wait. So let's say I want to wait 2 seconds, so 2,000 milliseconds. If I do this now, let's run it into the console and see what happens. Whoa, what just happened? We have console log 1, then console log 3, and then console log 2 seconds later. It looks like we just skipped this whole step and then put this at the very end. Well, you've just witnessed asynchronous programming. In order to understand this and what just happened, I need to take you to the next part. And that is, in order for JavaScript as we know it to run, for the JavaScript engine with memory heap and call stack to run, we need more than just the JavaScript engine. We need what we call a JavaScript runtime environment. And JavaScript runtime environment is, again, part of the browser. It's included in the browsers. They have extra things. On top of the engine, they have something called web APIs, callback queue, and an event loop. And as you can see here, set timeout is part of the web API. It's not technically part of JavaScript, is it? It's what the browsers give us to use so we can do asynchronous programming. Okay, so looking at this diagram, let's see if we can figure out what our code was doing. We can create here our own call stack. We'll have web API, and then we'll have a callback queue and an event loop, just like we have in our JavaScript runtime environment. So what's happening here? Well, first we have console log that goes into the call stack, and that gets run. So we log console log to the browser. We then get set timeout into our call stack. Because we finished this first task, we're going to the second one. And with set timeout, what's going to happen is, well, the call stack is going to say, okay, I have set timeout. And because set timeout is not part of JavaScript, but part of the web API, it has this special characteristic. What's going to happen is it triggers the web API and says, hey, set timeout has just been called. And because we notified a web API, we can pop it out of the call stack. Now, the web API starts a timer here, a timer of 2 seconds. It's going to know that in 2 seconds, you have to do something. And because the call stack is empty, the JavaScript engine now goes to console log 3 and executes this. So that makes sense, right? Now we've done 1 and 3, but we still have set timeout 2 seconds in the web API. Now, after 2 seconds, when our time limit is up, the web API is going to say, okay, set timeout should be run. Let's see what's inside of it. Well, we have console log 2. So what's going to happen is it's going to say, hey, set timeout is done. We have a callback. And this callback of set timeout, we added to the callback queue, saying that, hey, we have to run something, we're ready to run it. Now, the last part, the event loop. The event loop over here checks and says, hey, is the call stack empty? And it keeps checking all the time if the stack is empty. And if the call stack is empty and there's nothing running right now on the JavaScript engine, it's going to say, hey, do we have any callbacks? It's going to check the callback queue and say, is anything in there? Because the call stack is empty, we can throw something in there and make it do some work. In our case, we say, oh yeah, I do. Let me put this into the call stack. So now we move the callback into the call stack. And then the callback, we run it. And by running it, we see that we have console log 2. So it's going to say console.log 2. It's going to run this function, and once it's done, it's going to pop it out of the call stack. And again, we're done with the callback, so we remove it. And there you go. We're done. Everything is empty, and we've just run this 1, 3. It's going to go through the entire web API callback queue event loop, and then it's going to run console log 2. Whew, that was a lot of information. So you might need to watch that a few times, but hopefully that makes sense to you of why we notice this behavior. And I want to challenge your understanding here. Knowing what you know and what I just taught you, what happens if I change this to 0? That means 0 seconds. I'm going to give you a second to think about what will happen, and then we're going to try this out. I'm going to clear the console, copy and paste this, and run it. Whoa. 1, 3, and 2. Did you guess right? Now, think about why that happened. Even though this is 0 seconds, it still went through the process. It still got entered into the web APIs, and then the callback queue, and then the event loop. And by the time that was happening, the call stack had already moved on to the console log 3. And only after console log 3 was done and the call stack was empty, the event loop said, oh yeah, we can call console log 2. Hopefully that makes sense for you. And if you're able to understand that, you'll actually have a lot of people that hire for JavaScript roles ask questions like this on an interview, and you have to explain why that is. So I hope that made sense to you and you can use that to your advantage at the next interview. So let's recap. If you wanted to load your latest tweets onto a web page and you do this synchronously, then visitors to your site won't be able to do anything until those tweets are loaded. This could cause a long delay before they even get to see the content of your site. They may not be able to click anywhere and the page will feel like it's frozen. Not a very good user experience, is it? Another way to think about this is calling your teacher with a question. Synchronous way is you call the teacher, you wait on the phone until the teacher answers the phone and ask him the question. And hopefully you get an answer. So you let the phone ring until he picks up, but you're not doing anything else in the meantime. Asynchronous means you send a text to a teacher with a question. And then when the teacher, he or she has the time, will respond to you and call you with the answer. So you can do other stuff in between. So JavaScript is asynchronous when you can leave it a message. And a callback tells you, hey, Mr. Teacher has a message for you when you're not too busy. And that's why we call it a callback function and a callback queue. We're calling back to let them know that, hey, there's some stuff waiting for you. Now, we see over here that we have DOM, AJAX, and timeout. And there's a few other things. But you also see in the callback queue that we have onClick, onload, onDone. Do you remember the event listeners? Well, with an event listener, we had something like an element, and we added event listener. And in this event listener, we could say listen for a click, and it will have a function that perhaps just console.log click. Well, similar to an asynchronous way of programming, we've created this click function, and now we're just listening to it. And every time a click happens on the web page, so on the DOM, well, we run the callback function, which console logs click. All right, so to finish things off, when is asynchronous happening? It happens a lot when you try and talk between machines, like speaking to a database, making network requests, image processing, reading files, and don't worry, we'll go through this in future videos. But to recap what we just learned, JavaScript is a single-threaded language that can be non-blocking. It has one call stack, and it does one thing at a time. In order to not block the single thread, it can be asynchronous with callback functions. And these callback functions gets run in the background through the callback queue and then the event loop to bring it back into the call stack. So, next time you get asked, what is the difference between a synchronous or a synchronous program? Or how does JavaScript work? You should have a little bit more confidence to answer that question. And I hope that this was helpful. I'll see you in the next video. Bye-bye. Welcome back. It's time to code our own stack. And I have a little exercise for you here. I've created the template of what we want our stack data structure to look like. And we also have a class of node if you decide to use that, and you should be familiar with it from our linked lists exercise. Or you can just ignore it and then create a new node yourself in here. Now, this stack is going to have in its constructor 3 properties. We have the top, which is, remember, the top plate. We have the bottom, which is the bottom plate. And then we have length of 0. And both top and bottom are currently null. Now, we're going to be using linked lists to fill these values. But we don't need to use the linked list class that we've used before. Instead, you can just use the node class to simply assign different values and make sure that the .next points to a different node as we add things. Now, your task is to create 3 methods that work for this data structure. Peek, which lets us see the very top element or top node. The push, which lets us add a node to the top of the stack. And a pop, which lets us remove from the top of the stack. And if you want, optionally, you can also do an isEmpty method, which is common with a stack, to check that our stack is empty. We'll start off with a myStack that gets instantiated. And your code works if it can do something like this, where you say myStack.push, let's say Google, then push Udemy, push Discord, just like a browser history. And then you can pop Discord, then pop Udemy, pop Google. Good luck, and I'll see you in the solution video. Bye-bye. Welcome back. Let's have a look at how we would want to solve this question. That is, how do we create a stack data structure that has peek, push, and pop? Now, peek should be fairly easy, right? We just want to see the very top item on the stack. So I can just say peek is going to return this dot top. That's it. Nice and simple. So that if we run myStack.peek, it's going to return null because, well, there's nothing in our stack. This dot top is null. That is empty. Let's go to the interesting one. That is push. How do we add things to the stack? Well, the very first thing we want to do is to create a new node. And like I said, we can create a new object here if we want, or we can just use the node class that I provided for you here. We can use the class by saying new node, which instantiates the class and gives it the value that we're going to push with. Next, we want to check if this is the very first item, because if the stack is empty and this is the very first item, well, top and bottom are both going to point to the same node. So in that case, we can check for if this dot length is equal to 0, In that case, we can just say this.top is going to equal the new node. And also this.bottom is going to equal the new node. Otherwise, we have to do something a little bit different. But not that different because we've seen it in the linked list example. We just have to change some pointers around. In our case, we want to say const holding pointer to the very top node, because whatever on top now is going to get replaced by whatever we're going to add to it. So we're going to hold the reference to what was top originally. And then we're going to say that this.top is now going to equal the new node. And this.top.next, which is now the new node, is going to point to what was top beforehand, but now is below it. So we just say holding pointer, so that is the old top, is now going to be right after our new node. And then finally, we do the this.length plus plus to increment the length by 1. And then finally, we want to return, let's just return this, which will return us the linked list. Let's see if that worked. I'm going to say peek first. Well, there's nothing here. But if I want to push to my stack, I'm going to say push, and we'll push Google first because we're visiting Google first. And if I run this, I get a data structure that has top, that has the node value of Google. Next is null because we only have one item. And the bottom is also the same Google with next null. And our stack has a length of 1. What if we keep adding here? Let's go to Udemy next. If I click run, I now have a length of 2 stack that has top node as Udemy and bottom node as Google. Because remember, with a stack, we stack plates on top. That is, Udemy came in last, so Udemy is on top. Remember LIFO, last in, first out. Let's add one more. Let's say that we next visit our Discord community. So let's say push Discord. And I click run. And there you go. We have our Discord community at the top. At the bottom is node. And just to make sure that our peek is working, if I do peek, we should get Discord, because it was the last in and the very top of our stack. Very nice. I hope you got that. Let's continue with pop, that is to remove whatever is on the top of the stack. Well, let's first check to make sure that there is an item, because if there isn't and we just have null, well, we just return null. So in this case, we can just say if this.top, if it doesn't exist, in that case, we'll just return null. Then next, we can just do our const holding pointer to this.top. So what is currently at the top, which is Discord. And we'll say that this.top is no longer what it currently is because we want to remove it. It's going to equal this.top.next, which is underneath Discord. And then finally, we say this.length minus minus because we want to decrease the length by 1. And then finally, we can say return this. Now, remember, because JavaScript is a garbage collected language, if I didn't do this and said holding pointer to this.top, well, Discord, this node that contains Discord, wouldn't be referenced by anything and not used by anything, which means in a garbage collected language like JavaScript that it will get automatically removed from memory during garbage collection. So if I run this, well, I haven't done anything yet, but right now for pop, let's just return the holding pointer. If I click run, or let's first do my stack.pop to remove Discord from the list. If I click run, I get back the Discord node, which is the holding pointer, in case we still want to have access to it. Otherwise, if we just want it to disappear and we don't need it anymore, we can just return this. We can even comment out the holding pointer. And if I click run, we now have just Udemy at the top and Google at the bottom. And Discord is disappeared from memory. So let's keep going here. Let's say I want to pop one more. And if I run this, I now only have one thing, the Google, which was original item on the stack. So what we just did was we went to Google, then we went to Udemy, then we went to Discord. And then we popped whatever's on the top, and then we popped Udemy, and now we're just left with Google. If I do one last pop here, and I click run, we have top, which is null, but we have bottom node still having Google because we never removed in the pop our bottom node. All we did was replace the top. So we just need to add one conditional here, which is if this dot top equals this dot bottom, that means there's only one item on the list. I could have also done this dot length equals 0. If both of them are equal, which means there's just one node left, in that case, we want to say that this dot bottom is going to equal null. Because after we remove the only node left, we want bottom to equal null. So if I do this and click run, there you go. We're back to our original empty stack. I hope you got that and were able to make sense of it. We have another exciting exercise in the next video. I'll see you in that one. Bye-bye. Welcome back. We just implemented our own stack. And hopefully you're able to code along as well in your own language. Now here's my next challenge to you. What if we used arrays for this stack? Up until this point, or what we've coded in, has been with a linked list that we've created. How would you change the code if you want to implement this in an array? And the hint here is that it's going to be super simple. It's going to involve deleting a lot of this code because, well, arrays already have push and pop. So my challenge to you is to convert this stack data structure to use arrays instead of linked lists. Good luck, and I'll see you in the next video. Bye-bye. Welcome back. Let's convert our stack data structure to use arrays. And this is going to be fairly simple. All we're going to do is remove all of this in the constructor and have this dot array equal to an empty array. We don't need the length property because that comes built in with arrays in JavaScript. Obviously, this may be different for different programming languages, but for now, we have this available to us in our language that we're using right now. So there we have it. That's our constructor. What about peak? Well, peak simply means we want to see the very end of the array. Remember, with stacks, it's last in, first out. So when we do a peak, we want to see the very top thing, the latest thing that we've added. In our case, we can just simply say this dot array, and we're going to access that array with bracket notation, and it's going to say this dot array dot length, which is the length of the array, minus 1. Because we do minus 1 because our index starts from 0 to 1 versus the length that starts from 1 to 2. That's it. We have peak implemented. Let's just comment this out and make sure that peak works. If I run this, we get undefined, well, because there's nothing in the array. And we can probably give better errors if we wanted to here, but for now, I think this is fine. What about push? Well, with push, we get to delete all this code and simply say this.array.push value. How nice is that? That was nice and clean. Comes pre-built with arrays. We can just use push. So if I do my stack.push and I click run, well, peek here is giving me Google, but let's just run push only. I get a stack that has an array with Google in it. If I push to Udemy, I've added Udemy. If I do push Discord, I've added Discord. And if I do peek here, I should get Discord back because it's the latest entry. There you go. How simple is that? That means that pop is also going to be very simple, right? Absolutely. Feels good deleting code, doesn't it? All we do is this.array.pop. That comes already in JavaScript. We can just return this if we want. If I click run, well, we'll have to run the pop here. Let's run pop, which removes Discord from the list. If I run pop again, I get Google. And if I pop this and I click run, we have an empty array. Look at that. Nice and simple. We don't even have to use the node class, and that's pretty nice, right? So you can just use arrays as stacks quite easily. And we've already discussed the pros and cons in using linked lists versus arrays. One of the nice things about using an array is, well, arrays, at least in JavaScript, already act like stacks, and it makes things very simple for us. But enough about stacks. Let's implement our own queue this time around. I'll see you in the next one. Bye-bye. It's time for another exercise. We've learned how to create a stack data structure, but what about a queue data structure? Luckily for us, a lot of the principles are going to be the same. And if you are able to understand how the stack data structure works, then you should have no problem building a queue data structure. I've created a template to start us off here, and your job is to create these three methods. Peek, which we're familiar with. We want to peek and get the very first item in our queue, or our line, as I like to call it. And in our constructor, instead of having top and bottom, like we did with a stack, we have first and last. Who's first in line, who's last in line. And obviously a length of 0. And your job is to create and fill out these methods. OnQueue, remember, is to add to the queue, and DQueue is to remove from the queue. Remember that the difference between a stack that uses pop is that DQueue removes from the front of the list, whatever is first. And again, if you want, you can create another method called isEmpty. And your goal is to create this queue so that you can create a waitlist app where Joy gets in line, then Matt gets in line, then Pavel gets in line, then Samir gets in line, and then you're dequeuing them one by one with first come, first serve basis. Good luck, and I'll see you in the solution video. Let's implement our queue data structure. The very first thing we're going to do is the nice and simple peek, which simply tells us what is the very first item in our queue. So this dot first is what we want to peek into. If I run my queue dot peek, I should get null because, well, there's absolutely nothing in our queue. What about onQueue or enqueue? I'm not sure how to pronounce that. Let's go with enqueue. In there, we want to add to our waitlist. Again, similar to what we did with stacks, we're going to create a new node. And we're going to instantiate this new node with a value. Remember, we have the class here. And this value is going to get added to a node that has this dot value and this dot next. We then want to check and say, hey, if this dot length is equal to 0, that means there's nothing in our queue, then simply say this dot first is going to equal the new node, and same with this dot last, because there's only one node in our list. This is very similar to what we implemented in the stack. Otherwise, we can say that this dot last dot next, so that is whatever is at the very last of the line and whatever the next value is, which initially whatever is last is pointing to null, but we want to update that to say this time, instead of pointing to null, point the new node as the last in line. And we want to update this dot last to now equal the new node, so that whatever was last in line is now pointing to the new node, and the new node is now last, which is going to make sure that this dot last points to null. Finally, we can't forget to increase the length by 1, and then we can just simply return this, our data structure. So let's have a look. We want to create this line, queue. So all we're going to do is say we want to onQueue joy. If I click run, first node, I get joy with next null, and last node is again joy with next null and length of 1. So far so good. What if Matt comes and gets in line as well? If we add Matt, we now have first node that is joy and last node that is Matt. And you can see here that the first node of joy is pointing to the next node that is Matt. All right, let's add a few more. We'll add Pavel, who just got in line, and then finally Samir, a little bit late, but he got in line as well. If I click run, perfect. Our last node is Samir. We have a length of 4, and we have the joy node, which is the very first item in our queue. Now let's say we open the door and we start letting people in. We want to dequeue this list and go from the very first in, first out, all the way till the end. Once again, it's very similar to a stack, except that we grab the node from the beginning instead of at the end. So we're first going to say if there's no this dot first, if there's no first item, we can also check the length here if we want. So the list is empty. In that case, just return null. And by list, I mean the queue. If the queue is empty, then return null. We also want to check if this is the last node in our queue. So we can do something similar with what we did in stacks. We can say if this dot first equals this dot last. Again, we can just check length here as well if we want, but for now this should be fine. If that's the case, I want this dot last to equal null. Remember, we make sure that now last points to null. And regardless, as soon as we dequeue, we want to say this dot first equals this dot first dot next. That is whoever is first now, because we're going to remove joy. We want who's ever after joy, that is Matt, to be in first priority now. And then we simply say this dot length minus minus to decrease the length, and we can return this. If I run this, well, it's the same thing because we haven't run it here. So let's go ahead and do that. Let's first of all run my queue.peak to see who should be coming out of the queue, and that is joy. So if I do my queue.dequeue, and I click run, we see that now Matt is first in line, Joy has been removed, and length is of 3. And one thing to point out here, once we run DQ here, we've completely lost the Joy node from our memory because we have no more reference to it. Nothing is pointing to that memory space. And JavaScript, the way it works, is going to garbage collect and remove Joy. If we wanted to hold a pointer to Joy, then we could say const holding pointer and say this dot first, so that before we update whoever is first, we can reference it with this variable so that we could potentially, if we still want to use Joy, for example, in a waiting list app, maybe we still want to do something to the user, we can do this and still have access to the Joy node. All right, let's finish this queue. Let's DQ everybody from here. If I do DQ, and let's return this back to this so we see what's happening. If I run, now Pavel is first in line and Samir is last in line. If I click, or if I had DQ again, and I click run, Samir is the last person on the list, but then we can finally let him in as well. There we go. Now we have an empty queue, and we've just implemented our own queue data structure. Well done. Hope you had fun. I'll see you in the next video. Bye-bye. Welcome back. One of the most common interview questions when it comes to queues and stacks is this one. Implement a queue using stacks. Huh? Yep, you can implement queues using stacks. And it's especially easy if you create a stack using arrays. Now, this question is on LeetCode, which is really, really nice because we're able to see the solutions explained, as well as solutions in different languages. If you go to discuss and type in, let's say, JavaScript, we get solutions that people have submitted. You can see votes as well of the answer of how to do this. If you want to check Python, because let's say you're writing in Python, well, they have that too. Any language you want, you can find here. Now, I have the answer for you as well. And in this video, right around here, in the available resources, you'll see a REPL with my answer on it. But I want to challenge you and pretend you're in an interview to implement queue using stacks. How would you go about doing it? You can actually even code it on the LeetCode website if you want, using whichever language you want. And just a heads up here, if you are using JavaScript, that they use the prototype way of adding methods. But the class syntax that I showed you is the newer version. It's underneath the hood. It's the exact same thing as doing .prototype. However, it just looks cleaner using the class syntax. So that's what we did. So good luck with that. Have fun. And I'll link to the solution code for you right over here. And there we have it. We've learned stacks and queues. And an easy way to remember them is just simply plates and a waiting line. We learned why they're built on top of other data structures like linked lists and arrays. And we also talked about how to build stacks with arrays and linked lists, and also why we might not want to use an array to build queues, and also built a queue data structure with linked lists. We learned that stacks and queues are great for some fast operations that they have, such as removing or inserting, such as at the end of the data structure. We can also access the very first item in a queue or the very top item in a stack. And we also have all our data ordered, which is really, really nice. But we don't usually use our stacks or queues to really do any sort of lookup or search through the data structure. All we're interested in is the end bits of the data structure. So they make it really useful by restricting our use of what we can do when it comes to stacks and queues, but making sure that what we're allowed to do with these data structures are going to be really, really fast. And there we have it. We've continued to expand our mind map of data structures. So we completed our stacks. We learned how to create stacks with arrays and linked lists. We've learned about their big O notation. And we also talked about queues and how we wouldn't really want to use an array for a queue, a very common interview question. We learned how to use a linked list to create a queue. And also we learned about the big O implications, which is very similar to stacks. We're getting closer and closer to filling out this mind map. But before we do that, we still have a few more data structures to go. But the end is almost near. We only have trees and graphs to talk about. For that, I'll see you in the next part. Bye-bye. Welcome back. It's time to learn another data structure. This is a big one, and an exciting one at that, because it's going to introduce a lot of new topics, especially when we get into algorithms as well. They're called trees. And no, not these kind of trees, more like this. Trees are a data structure that have what we call a hierarchical structure. As opposed to something like linked lists or arrays, which are linear, trees can have 0 or more child nodes. You see, a tree usually starts with a single root node or a parent node, and every child of the tree descends from this root node. So it's kind of like an inversed tree, really. And every child of a node descends from only one parent. So you have a parent-child relationship that you see is unidirectional, that is, it's going one way. And you also have leaf nodes, which are the very end of a tree data structure. Finally, within a tree, you can have things like subtrees, such as the area over here circled in red. 3, 6, 7 form a subtree. And tree data structures are very important because you work with them every day. If we go to twitter.com or any website for that matter, and we open the developer tools, just like I did here, if I go to the Elements tab, you see our web pages are created by something called the DOM, or the Document Object Model. And this is a tree data structure. It doesn't look like a tree that I just showed you, but the browser is just making it look nice. But underneath it, we have head and body that are children of the HTML tag. Inside the body, we have all these children. And inside these children, we have more children, and they're all connected hierarchically to one another. I'm sure everybody has tried to play chess online versus a computer. Well, a computer in a chess game, at least back in the day before we had things like machine learning, used a tree data structure to make a decision. Should I make this move? Or should I make that move? Or should I make that move? And it would pick moves based on which move had the better outcome. Facebook comments, for example, are a tree data structure where I can comment on a friend's photo and that friend can comment on my comment. Family trees can be represented in a tree data structure. And for us engineers and programmers, you might have heard of the abstract syntax tree. If I Google abstract syntax tree here, well, this is how programs or code is usually being run. Usually we write code and then it gets broken down by the machine into this abstract syntax tree so that it understands what we wrote down. And this, as you can see, uses a tree data structure. The beauty of trees is that we use the same principle as we did in linked lists. That is, we have nodes. And these nodes can contain any type of information that we want. We can have user information, we can just have numbers like we have here. Anything we want, we can contain within a node. Now you might be thinking, this kind of reminds me of a linked list. And you'd be right. Linked list is technically a type of tree, but with just one single path. And it's linear. There's only one way to go from top to bottom versus what we've seen before in a normal tree, like this one. Now, a thing to keep in mind here that might be different than a linked list is that a node can only point to a child. As you can see, all the arrows point down. There's always one entry point, which is the root, but nodes don't really have to reference their parent. Now, just like in real life, there are many types of tree data structures that we can have. And if you go to Wikipedia and you look for all the tree data structures, it's going to, well, intimidate you, that's for sure. Because look how many different types of trees we have. Just like in real life, how we have all these different types of trees, there's different types of trees that we can have for a specific use case. But don't get overwhelmed. In this course, we're going to go over the main ones that get used, I would say, 90% of the time. And the ones that you're most likely going to encounter during an interview. Because at the end of the day, once you understand what a tree data structure is like, how to create it, how to perhaps use some actions on it, then all the other trees that you saw are just minor alterations to what we know. Now, I want to warn you. Back in the day when I took a class on data structures, this part, especially trees, really dragged on and made me not interested in data structures because there's so many things you can talk about when it comes to trees. I'm going to try and keep you engaged to the best of my ability and try and be efficient through this section and show you the important aspects that you need to know for an interview and to lay the foundation, not to teach you every single tree that there is, which is not going to benefit you. With that in mind, I'll see you in the next video. Bye-bye. Welcome back. We're now into the tree data structure section, right over here. And as we can see, trees or linked lists are a type of a tree that we've already talked about. But there's a few others over here that we have yet to talk about. So we're going to cover that and get familiar with the main different types by starting off with binary tree. Let's get into it. A binary tree is something you've likely seen before. And it's a type of tree with a few rules that are applied to it. But they're quite straightforward. Each node can only have either 0, 1, or 2 nodes. And each child can only have one parent. This is a binary tree. However, this is not a binary tree because it has 3 children, or at least one of the nodes has 3 children. And each node represents a certain state. And this is very similar to what we've done in the past, especially with linked lists. If we take a look at an example here, in order for me to create a binary tree, well, I can just create a function, say binary tree. And this binary tree perhaps will get a value. And the binary tree, or in our case, let's just do a binary tree node, will simply have a this.value associated with it, which is the value that we give it inside of the function. And then we have 2 other properties, which is a pointer to the left side of the tree, which for now will be null, and a pointer to the right side of the tree, that is this.right equals null. And that's it. We can represent a binary tree node as simply having a value and then a left and a right property. Very similar to what we did, or a very similar principle to what we did with linked lists. Now, we're going to actually code a tree and create a tree data structure just like we have for past data structures. But I want to also point out a few terminology that we might come across and that are important. In this case, we're looking at something called a tree that is completely full. That means there are no gaps in the tree. Let me show you what I mean. A perfect binary tree has everything filled in. That means all the leaf nodes are full, and there's no node that only has one child. A node either has 0 children or 2 children. And also, the bottom layer of the tree is completely filled. Nothing's missing. Versus a full binary tree, which simply says that a node has either 0 or 2 children, but never one child. Now, why is this important? Because this type of binary tree, especially a perfect binary tree, is really, really efficient and something that is desirable. When binary trees are perfect like this, they have 2 really interesting properties. One is that the number of total nodes on each level doubles as we move down the tree. For example, here we have 1 node. In the next level, we have 2. So we've just doubled the nodes. In the next level, we have 1, 2, 3, 4. So we've doubled 2 to 4. If we had another level that's a perfect binary tree, we'd have 1, 2, 3, 4, 5, 6, 7, 8. So we were doubling every time. The second important property is that the number of nodes on the last level is equal to the sum of the number of nodes on all the other levels plus 1. All right, that was confusing. What do I mean? Well, here, if I take the bottom level, that is 1, 2, 3, 4, the second property states that all the nodes above it plus 1 is going to equal the bottom level. So 1, 2, 3 plus 1 equals 4. That is what we had on the bottom. Which means, in other words, that about half of our nodes are on the last level. And this brings up a really interesting point. By organizing our data in this way, we have half of this data in the bottom level. If somehow we can avoid visiting every node, even if the node we're looking for is at the very bottom, perhaps there is some efficiencies that we can have. And you'd be right. Because of this type of structure, you're going to see a new notation of big O. Something that we've been waiting for a long time, O log n. And when we start talking about something called binary search trees, you're going to start seeing this notation. Yes, we finally got into another big O notation, but what does it mean? In the next video, I want to talk about O log n and why trees allow us to have something like this and what the implications are. I'll see you in the next one. Bye-bye. Welcome back. In the previous video, we talked about a special characteristic or properties of binary trees. And because of the way binary trees are structured, there's a certain way for us to calculate the number of nodes that they have. For example, on level 0 of a binary tree, that is the very top level where we only have one root node, we can calculate how many nodes there are by doing 2 to the power of the level, which is 0. So if I do 2 to the power of 0, it's going to equal 1. That is, we have one node. If we go a level down and say, what about level 1? How many levels do we have? Well, we have 2 to the power of 1, which equals 2. All right, let's keep going. What about level 2? How many nodes in total do we have on that level? Well, we have 2 to the power of 2, which is equal to 4. And then one last level, let's say level 3. How many nodes are we going to have in level 3 in a perfectly balanced binary tree? Well, 2 to the power of 3 is going to equal 8. Oh boy. We just did some math here, and I promise that this course is going to be that mathy, but bear with me here. I want to explain to you what O log n means. Knowing what we just did now and knowing that these are the total number of nodes. If we imagine that this data was in an array, that means we have 8 places that we need to iterate through, 8 nodes that we need to check, perhaps to search for something. Well, based on this formula here, that means that we can find out the number of nodes in a tree by doing 2 to the power of h, or the height, that is the level. If we know how many levels our binary tree is, we can find out how many total nodes there are. 2 to the power of h minus 1. Now, why this minus 1? Well, if we go back to our diagram, this binary tree, we have 1, 2, 3, 4, 5, 6, 7. We have 7 total nodes, and the tree is 1, 2, 3. The height of the tree, well, it's 3 levels deep. So 2 to the power of 3 minus 1 is 7 nodes. Now, if we actually simplify this, we can just simply say that the log of nodes is going to equal the height, or the steps. And I use log here. Just in case you're wondering, log simply means that log 100 is equal to 2. Because 10 to the power of 2 equals 100. So all I did was, using this, I simplified and said that log nodes is equal to the height, and we've dropped -1 here because it's insignificant. But log nodes is the number of steps, or height, and let's change this to steps that we would use in a tree. Let me show you again in our diagram. Log n simply means that based on the height, the maximum number of decisions, let's say we're looking for a specific node, that we're going to take is going to be log n. That means, is this the node we're looking for? Nope. Then we either go left or right, and let's say we go left and say, is this the node that we're looking for? And that's our second step. If the answer is no, then we either go left or right, and we say, is this the node we're looking for? Yep. So we have maximum 3 steps here, instead of if we went 1, 2, 3, 4, 5, 6, 7 steps. You see that there's some sort of efficiency here. And coming up, we're going to learn about binary search trees, where we're able to minimize those steps instead of visiting every single node. So when you see the notation of O log n, don't get startled. All it's saying is that the choice of the next element on which to perform some sort of action is one of several possibilities, and only one needs to be chosen. We don't have to check both. And a good way to think about log n is when you're looking through a phone book. You don't actually check every single person in a phone book, do you? Instead, you can simply do what's called divide and conquer by looking based on where their names alphabetically begin. You would open up the book to where you think the letter will start with, the name will start with, and then keep dividing and conquering until you get to that person. You only need to explore a subset of each section before you eventually find someone's phone number. So just think of that. O log n is just like looking through a phone book. And the reason that I just talked about O log n in such detail is because it's an important concept. It's really, really fast. As you can see here, O log n is this light green good area. That's even better than O of n, linear time, because we don't need to check every single element. And in the next video, we're going to talk about the most common tree that you're going to see in a lot of places, called binary search tree. And as the name suggests, it allows us to search really efficiently. And just by looking at this graph, you might be able to think about how a place like Google and Google search might find this extremely useful, right? When we search through Google, they have a ton of websites, a ton of nodes to search through. How are they able to give us an answer to our searches so fast? If they used O of n, time complexity, it's going to take a lot of time and it's going to be really expensive for them. So instead, they use a tree structure or a tree data structure so that our searches can be a lot faster with something like O log n. I'll see you in the next video. Bye-bye. Welcome back. Let's continue our discussion with the most common tree data structure. That is the binary search tree, which is a subset of binary tree, which we talked about. What is a binary search tree? Well, a binary search tree are really, really good, as the name suggests, at searching. They're great for comparing things. Now, why would this be better than, let's say, a hash table where we can just give it a key and get the item right away? Well, this data structure preserves relationships. Just like you wouldn't want your folders on your computer to be in a hash table data structure because there is no sort of relationship. Instead, you want your folders to have relationships, to have a parent folder and a subfolder and then a subfolder. A thing like binary search tree allows us to preserve these relationships. When it comes to binary search trees, these are the rules. 1. All child nodes in the tree to the right of the root node must be greater than the current node. That means if I keep going to the right, the number or the value of the node constantly increases. You see over here, I go from 101, 105, 144. If I keep going to the right, let's say here, 33 to 37, that is increasing. If I go to the left, 101, 33, 9, that's always decreasing. Same with here, 105 to 54. If I go to the left, it decreases. To the right, it increases. And then the second rule is that a node can only have up to 2 children because it's a binary tree. The advantage of a binary search tree is that, well, it should be obvious with the name, right? Searching and lookup is very easy to find what you're looking for because if I'm looking for, let's say, number 37, I can start at 101 and say, is 37 less than 101? Yes. Okay, then go to the left. Is 33 less than 37? No. Then go to the right and I find 37. I don't have to iterate in a linear fashion through each node. And that is what lookup means. Lookup simply means that I can search for an item a lot faster than, let's say, an array where I have to iterate and loop through every single item. But what about insert and delete? In a hash table, I can do insert and delete really fast at O1 or constant time. But with a binary search tree, it looks like I can only do O log n. And that should be obvious, right? Because in order for us to insert or delete something in a binary search tree, we need to figure out where to insert the item or where the item is before we delete it. For example, with 105, let's say that we want to delete 105. Well, we have to first, from the root node, get to 105, and then we have to decide which node is going to take its place. In this case, because 54 is less than 144, 144 is going to come up over here. But as you can imagine, this operation, although seems simple right now, if we had a lot of children and a lot of nested nodes, a lot of reordering needs to happen and shift our nodes around. And don't worry, we're actually going to code this so you understand this just like we have in previous data structures. But I want to demonstrate, instead of me just using my cursor here, a nifty little tool to visualize how binary search trees work and how their operations are O log of n. We're going to use Visual Go again, and I'll link this, and I highly recommend that you all play around with binary search trees. But let's do a couple of operations here. See that it generated a random binary search tree for me. Let's say I wanted to do an insert, and I want to insert, let's say, the number 1. If I click go, it's going to traverse, figure out where it wants to insert, and it's going to insert 1. What if I want to insert perhaps number 44 this time around? If I hit go, it traverses, figures out where 44 should go, and places it down here. So we're always traversing and figuring out, using O log n, where we should place the item. What about removing? Let's add one more. I'm going to insert 51 this time, so that it places it right over here. Perfect. Now, let's say we want to delete 50 now. If I remove 50, I hit go, I find 50, remove it, and then I have to replace with 51 and go up. So there's a bit of a tough little logic happening there that we're going to have to incorporate. And we're going to get to that. But for now, as I end this video, I recommend that you go to Visual Go and play around with binary search tree so that you get accustomed to it. And as you play with it, see if you notice a problem that we might encounter with binary search tree, because we're going to discuss it in the next video. Welcome back. While playing with Visual Go, did you notice a problem with binary search trees? If not, let me demonstrate something to you. Let's say I keep inserting here. Let's say 86. And then while that's going, I'll also insert 90. And finally, I'll insert 99. All right, what is the problem with this? Well, you can imagine a situation where we have this really unbalanced binary search tree where all the nodes just keep getting added to the right, to the right, to the right, to the right. If we imagine that we didn't even have this section, this all of a sudden turns into a linked list where we're just looping through every single node. This is a big problem that comes with binary search trees. That is, you can have balanced search trees, like the one right here that gives us this log n performance, but then also have unbalanced ones, where it sort of turns into a long linked list, where instead of being able to do the log n operations, you now have to loop through every single node, and lookup and searches become O of n, or linear time. And you even saw in our Visual Go demonstration how slow it took to insert items because it had to loop through so many things. One of the keys that you'll have to remember, and this is a question that you might get asked in interviews, is why an unbalanced binary search tree is bad. And I hope this demonstrates why it's not a good idea. Ideally, we want to balance our search trees so that we can have this performance optimization. If we go to our Big O cheat sheet, we see that with binary search trees, that we have O log of n for most things, which is average. But when it comes to worst case, when we have an unbalanced tree, that all operations are O of n, or linear time. So you might be asking yourself, how do you balance a tree? And luckily for us, there's algorithms that help us do that. It is really advanced, and we will talk about it after we build our own tree and some of the options that we have. For example, we have things like AVL trees and red-black trees that allow us to make sure that our binary search tree is going to be balanced. Luckily for us, they're built in most programming languages, and in interview questions, they won't really ask you to balance a binary search tree because, well, it can get pretty complicated and time-consuming, and interviews, usually don't have enough time to get you to do that. The idea is to be able to talk about it and know that there are ways to balance a search tree and be able to talk about the trade-offs just like we did. Now, we're going to talk about these two ways of balancing the search tree in an upcoming video. But for now, let's just focus on the basics. In the next video, I want to talk about the pros and cons of using something like a binary search tree, and then finally implement our own. I'll see you in the next one. Bye-bye. Welcome back. Before we code our own binary search tree, let's just go over the performance implications and why we might want to use it over other data structures. Its strengths are that it has really good performance across the board. You saw that most operations or all operations in a binary search tree are better than O of n, assuming that the binary search tree is balanced. It is also ordered. And because we can place the node anywhere in memory, we can just have flexible size. We can keep growing our tree. The downside is that, as you may have noticed, it has no O1 operation. We usually have to do some sort of traversal through the tree for any sort of operation. So compared to an array, a lookup, for example, will be a lot faster because we have O log n for searches versus if we iterate through an entire array, if the array is unsorted. Inserts and deletes are also faster than an array, unless the array is adding to the end. Otherwise, arrays have to shift all the indexes versus a binary search tree that is just O of log n. What about compared to hash tables? Well, although hash tables allow us to insert and search at constant time, with binary search trees, we have sorted data. And we also have this structure of parent-child relationship that you won't be able to get too much with hash tables. A good thing to keep in mind is that binary search trees aren't the fastest for anything. Remember, their operations are usually always O of log n. On average, an array or an object will have faster operation. But there are certain conditions where they do outperform objects and arrays. So binary search trees do perform really well, as long as you make sure that you stay away from the edge cases that we discussed and we balance our binary search tree. But enough talk, enough slides. I think to fully grasp and understand how trees work, we should code our own. I'll see you in the next one. Bye-bye. Welcome back. It's time to write our own binary search tree. And in this exercise, I'm going to challenge you to write your own before you watch my solution video. Now, keep in mind that just like with linked lists, it's going to require us to keep track of the nodes to the left and to the right of the current node. And also, we have a value associated with a node. I recommend you actually draw this out on a piece of paper to understand, because keeping everything in your head and the calculations might be a little bit difficult. But I have started you here with all the essentials you need. We've created a binary search tree class. We have a node class that we can use. We start our binary search tree with this.root of null because we don't have anything yet. But remember, we have the root, which is our topmost node, which currently is empty. We're going to initialize our binary search tree, and hopefully we're able to create two methods. One is insert and one is lookup. And our goal is to create this tree over here. 9 as the root node, then 4 and 20 as its children, and then 4 has 1 and 6 as its children, and 20 has 15 and 170 as its children. So ideally, if we implement insert correctly, we can say tree.insert 9, then insert 4, then insert 6, then insert, let's say, 20. We'll insert 170. Last two, we'll insert 15, and we see we have one left here, so let's do insert 1. And ideally, after running these commands, you're able to create this tree data structure. Now, at the bottom here, I created a small little function for you. And for now, I want you to just ignore it because we're using something called recursion here, which we haven't gotten to yet. But I only created this function for you to be able to test out your code to make sure that it actually works. All you need to do in order for you to verify that this is working is to say json.stringify, which is a JavaScript specific way to create a JSON string. And we're going to say traverse tree.root. We just give it the root node of our tree, and it's going to traverse and print out everything into a string so that you can check in the console that your tree actually is working. And in the solution video, I'm going to demonstrate how this works, but I've added this as a little helper for you in case you want to double check your work to make sure that it's correct. And by the way, the lookup method should simply return the node that we're looking for. And if it doesn't find the node, then we can return null or false, whichever you want. And I've added the remove method here, which we're going to talk about later because it's a little bit difficult. So for now, just worry about insert and lookup, and I'll see you in the solution video. Bye-bye. Welcome back. Hopefully that wasn't too bad. Keep in mind that when it comes to interviewing, interviewers want you to know that you understand the concepts. You won't necessarily have to code a binary search tree from scratch, most of the time, at least. Because in real life, you have things like this library that somebody else created that allows you to use tree traversal and manipulation techniques. Because this has already been done before. And you can see by using a library like this that you can just use it and create the tree that you want. Most likely, you're not going to implement it from scratch by yourself. But we do want to understand the fundamentals and how it works. So if this was challenging to you, don't get frustrated. This doesn't make you a bad engineer or a bad coder. You're just working towards building those fundamentals so that you can use tools like this in the future and still understand how they work. But enough talk. Let's get to the answer. I want to create a tree that looks something like this. So the first thing I'm going to do is work on the insert function. Now, within this insert function, the very first thing I want to do is to say, well, we want to create the new node. And we'll say new node will be the value. So we're just creating the new node class, instantiating it with the value, and that's our new node now. So we have a reference to it. The first thing we want to check, well, if the tree is empty and there's no root node, well, we should add this as our root node. So I'm going to say this.root equals null. If that's the case, then simply make the root node our current node that we inserted. Nice and easy. And just to check that this is working, if I comment all of this out and click run, there you go. Our root node has a value of 9. Left is null, right is null because it's the only node. And by the way, to show you how this stringify works, it's really, really useful because if I copy this and just point out here that I'm not copying the quotation marks, which makes it a string. And if I open up Developer Tools in Google Chrome, and I go to my console tab, I can copy and paste this, press enter, and now I have access to this tree. And it's a lot easier for me to view. And once we insert other nodes, you'll see that it's very easy to traverse this tree this way and check your work, which is why I added this function. So we'll come back to that. For now, we see that our insert is working, at least for if the root node is null, but let's continue if that's not the case. We'll say else. If the root node is already filled, we'll say that the current node will be the this.root, because we're going to have to traverse this node. And we won't know how long we're going to traverse this node for. We just want to keep traversing until we find a place to insert this. And this is a bit tricky, but something you'll get used to when you're building trees. We want to use a while loop, and the condition we're going to use is true. That means just keep looping every time, because true is always going to equal to true. And we have to be careful here. If we do this, we want to make sure that there is a way for us to exit out of this loop. Otherwise, we're going to have an infinite loop and we'll crash our little page here. So what are the conditions that we're going to loop through? We want to traverse through the tree. Well, the first check we're going to do is say if value is, remember, value is what we insert. If that is less than the current node dot value, so we'll start from the root node and say, hey, is the value that we're entering less than the current node value? If that's the case, we know the rules, so we're going to go left if the value is less than the current node. Now, in here, we want to check, first of all, if there's no current node dot left. Is there an element already to the left of the root node? Because if there isn't, in that case, we can just assign the current node dot left to our new node that we want to enter, because there's nothing there. And we can just return out of this loop and just return our this, which is the binary search tree. However, if there is something to the left of our node, let's say in this case 9, in that case, we'll say current node is going to equal current node dot left. So we're going to update and shift over so that the current node is no longer 9. It's whatever is to the left of 9. And that's going to keep us looping. So we're just going to keep looping, keep looping, keep looping until we hit a node that doesn't have a left-hand side, so that we can place the current node or our new node into its place. But that's for the left side, if the value is less than the current node. If the value is greater, or in this case equal to our current node, and we can decide here where we want to place values that are equal. That's up to us and how we want to implement it. We'll say that we'll go right if value is greater or equal to current node. In that case, well, we want to do the first check first, which is if current node dot right, there's nothing to it, there's nothing next to it, to the right of it. In that case, just like above, we can say current node dot right equals the new node. And we're also going to return this because we want to stop looping. Remember, as soon as we have a pointer to null, that's when we want to exit out of this while loop that's going to loop forever. Otherwise, we simply say current node is going to equal current node dot right. And there you go. Hopefully this works. But before we test this out and see if we made any minor mistakes, I do want to warn you. If you are just coding along, I encourage you to pause the video and think through line by line, maybe even drawing things out, maybe using Visual Go to see what we're doing. Because it's really hard to keep this in your head. Even myself, I can't code this from scratch. It takes me a bit of time to think things through and see how we want to structure the code. So don't feel frustrated if this is a bit overwhelming. I encourage you to pause the video, try to code along, and understand what's happening step by step. All right, let's test this out. I have an insert of 9 here. If I click this run, that's working. If I insert 4, all right, looks like 4 got inserted. What about 6? All right, I'm just going to comment all of this out and see if that works. I'm going to click run. All right, looks like we've logged out everything, but I want to test, make sure that everything is working as expected. So what I'm going to do is I'm going to copy and paste this, remember, without the quotes at the end, because I don't want to copy the string. I want to copy the object, and I'm going to, again, open my developer tools, go to console, clear my code, and then just copy and paste, hit enter, and now we can test our tree. Let me scroll down here. This is the tree that we want. We have 9 at the top. To the left and to the right, we have 4 and 20. Look at that. That's good. And when we go to the 4, we have left is 1, right is 6. Awesome. And 1 should have null null to the right and left. Perfect. Same with 6. Perfect. And if we scroll down, let's look at 20. It should have 9, or it should have 15 and 170 as its children. We have 15 and 170, and both of those pointing to null. Hey, not bad. Not bad at all. It wasn't too bad. Once you get a hang of it and code this on your own, you'll see that it makes sense. It's all just logic, and something that we've learned when working with linked lists. In the next video, we're going to try and tackle lookup. If you weren't able to implement insert, please try and do that now before we get to lookup. Otherwise, try to implement lookup on your own, and I'll see you in the solution video. Bye-bye. Welcome back. Let's try and implement the lookup function, or the search function. We want to check if an item or a node exists in our tree. Let's see how we would go about this. The first thing I would want to do is to check if there is such a thing as a root node, if it's empty. So I could have done this dot root equals null to check if the root is empty, or I can use the exclamation mark in JavaScript. And we'll just say return false, because if the root doesn't exist, then it doesn't really matter. We're not going to find that node. Otherwise, we're going to say, once again, let current node equal to this dot root, very similar to what we did above. Remember over here. And you'll notice some similarities with what we did when we did the insert. We still need to traverse through our tree. But instead, our while loop is going to stop whenever the current node no longer exists, or we no longer have a node to go through. Because once we've gone through our binary search tree and it's null, that means we didn't find what we're looking for. So in this case, I'm simply going to say if the value that we're looking for is less than the current node dot value. In that case, current node is going to equal current node dot left, because we now want to go left. If the value is less than the current node value, that means it's not the same. It's not the node we're looking for. So go left, because that's where I can find something that might be less than the current node. Otherwise, and we'll use an else if statement here, which says another condition. So if that doesn't match, if the value is greater than the current node dot value, what do you think we do here? Well, we go to the right. So we're going to say current node is now going to be current node dot right. So we can keep checking to the right of us. And then finally, else if, that is another condition, and we can say if current node is dot value equals the actual value that we're looking for, that means we got a match. That means that node exists, so we're just going to return the current node. Nice and simple. And then finally, because we're not returning anything, we're just looping through the while loop until we find the current node, where we return the current node, or current node becomes null because we cannot find anything. If we don't find anything, just return false. The only way we return something other than false is when we find our node with the matching value. So let's see this. If I now run tree.lookup9, and I'm going to comment this out because we don't need to check that our tree is being made. If I click run, there you go. I get the 9 node that has reference to all the other nodes beneath it. If I look up 90, I'll get false because it doesn't exist. What about 20, which exists? Yep, we found 20. What about 170? Yeah, we found 170. It's a node, but has no left and right references because it's a leaf node. And then finally, 171 is false because it doesn't exist. Well done getting this far. Hope you're able to implement your own binary search tree. Once you get the hang of it, it's really not that bad. At the end of the day, each line should make sense, and traversing a tree should make sense to you by now. We also understand why we have big O of log n. Although we have loops here, like while loops, we're not actually iterating through every single node. We're only iterating using divide and conquer, something that you'll hear a lot of. Divide and conquer simply means we're dividing up so that we don't visit all the nodes. Each node that we visit, we make a decision to go left or right. I'll see you in the next one. Bye-bye. Welcome back. We have a bit of a bonus exercise. Now, you can skip over this exercise because it is a little advanced and you most likely won't encounter it in an interview. But for those who are curious, that is how to implement the remove method in here. If we wanted to remove an item from a tree, how would we go about doing it? Now, if you want to try and implement this, I want to give you a heads up. The best way for you to visualize and see what steps we need to do is to go back to Visual Go. Make sure that you move the speed to the slowest so you see what's happening. And you start removing some nodes to see what the logic is in removing nodes. Some steps are really easy. If we wanted to remove one, for example, we simply traverse and find one and just remove it. But then there's other cases that gets really complicated, such as what do we do when we remove 51? Well, if I click play here and say remove 51, well, you'll see that we're going to start traversing to find 51. And notice what happens when we find 51. We actually keep going to 55. And then we keep going to 54. And watch this. We split things and move 54 up. And I know that's really, really confusing. You might want to do this a couple of times to see what the logic is. But essentially what we're doing is we're finding what we want to replace, going to the right of it, then the left, and placing that left item to the top. Like I said, this is going to be a little bit advanced. But if you want to challenge yourself using the Visual Go animation, try to figure out how to implement your own remove method. And in the next video, I'll show you my solution and go over the steps that we take for this to work. I'll see you in the next one. Bye-bye. Welcome back. How was the remove method? It was pretty tough, wasn't it? Now, I don't expect you to be able to get this. Even for me, it took quite a lot of time to get this working. And I'm going to give you another chance to finish it if you want. I have my code minimized here just to show you the if statements and the steps that I'm taking. So you could always pause this video. But let me just go over the steps I'm going to take. And usually I like coding step by step, but when it comes to this function, it's really hard to go step by step when you're not coding yourself or you don't have a diagram to point to and show. So I'm going to leave the code for you so you can implement it on your own and actually, like I always recommend, draw it out with a piece of paper to understand what's going on. Otherwise, if I just coded this along, it would be a 30-minute video of you getting bored, and then you're not going to have fun with data structures anymore, and we don't want that. So all we're doing is, well, if we remove, we're going to check if there's anything in the root. If there isn't, well, the tree's empty, there's nothing to remove, we're going to return false. Otherwise, we're going to grab the current node as this.root first, and then we do something new here that we haven't seen before. We declare a new variable called parent node. And this is something you may have realized as you coded this along. We need a reference to the parent. Because if we remove something from here, such as 14, well, we need to, before we get to 1, get a reference of 14 so that when we get to 1, we have access to 30 so that we can link 30 to 1. So if we go back here, now that I have parent node variable, and I do my loop to check if the value is less than the current node, in which case I'll go left, and this should be familiar. But this time I'm also keeping track of the parent node. And otherwise, if we need to go to the right, well then we go to the right, but also keep track of the parent node. Now this is the interesting part. We're looping through everything here and nothing's too crazy until we get to a match. Once we get to a match and we find the current node that we want to delete, we have a match, we need to get to work. And we have 3 options here. The first option is that the current node has no right child. If the current node has no right child, let's have 55 as an example, or let's do 14 as an example. If I remove 14, you saw that all we did was we remove 14, but we kept a reference to the parent node and just moved 1 up. That was nice and easy. And in here with option 1, that's really all we do. We first make sure that the parent node doesn't equal to null. That means we're modifying the root node. Otherwise, the root variable gets updated to our current node. Otherwise, if parent is greater than the current value, then make current left child a child of the parent. If parent is less than the current value, make left child a right child of the parent. Again, I know this is confusing, and like I said, this is something that you might have to go on your own. I'll leave comments out here for you so you can actually play around with it and play around with Visual Go so you understand what's happening. So that's the first option. If that's the case, then do that. If the right child, if we have a right child, but that right child doesn't have a left child, let's find an example that has that. So we have a right child that doesn't have a left child. So that is 54. What happens when we remove 54? If I click on this, 54 gets removed, and we just place 55 instead of 54 now. So in that case, we go, again, check if the parent node is not null, so that we have to replace the root node. Otherwise, we go through similar steps to reassign the node. What about the last option? Right child that has a left child. So if we go here, we have a right child. Let's say if we want to delete 30, that has a left child. 38. So if we want to delete 30 and hit go, we still traverse until we get to the left, and then, oh boy, we do a bit of a magic. This will require you to read through the code, and I've left some nice comments for you so that it makes sense. But we're essentially finding the right child's leftmost child and looping through this, changing the subtrees of the tree. Like I said, this is quite a bit advanced and really hard to explain just on the screen. So I do recommend, if you weren't able to get the remove function, to go through this step by step. I'll link to the code right in the resources so you can play around with this and see that it works. But to check that remove does in fact work, let's say I'll remove 0 from this list. If I click run, I get undefined because there's nothing to remove. But if I remove, let's say 170, and I click run, I get true. And if I traverse our list and try and grab our tree now, let's open up Developer Tools. Paste this, press enter. And now if we go to 9, 20, and we see that the right node is now empty where 170 should have been. So we're able to delete the node successfully. That's enough for now. You can play around with the remove method if you want. You can try and code it yourself. It will take a bit of time. I know I keep saying this. I do encourage you not to get disappointed if the remove method was really difficult. I didn't really want to include it in the course because it is overly complex and not something you want to get too worried about when it comes to an interview. But I thought some of you might be interested in it. Just make sure that it's not something that discourages you. As long as you can do the inserts and lookups, that's what matters for interviews. I'll see you in the next one. Bye-bye. Welcome back. Now that we've implemented our binary search tree, I want to talk a little bit about balancing our tree. Usually in production, you want to have a balanced search tree. There are two types of trees that are very popular when it comes to this. Although we built our own binary search tree, you'd most likely in production use something like an AVL tree or a red-black tree that automatically rebalances itself so that we don't have those edge cases where our balanced tree turns into a linear unbalanced tree. Now, these topics, we don't need to code ourselves because they are a little bit complex, and most of the time you're using some sort of a library that implements it. But I do want you to understand how it works, so I'll leave resources for you for both red-black tree as well as AVL trees, where if you click here, you see that Visual Go also has it. To demonstrate for you how it works, if I want to insert, let's say, 77 into my AVL tree, nothing's different. We're adding 77 to the tree. But if I now add, let's say, 80, which will make our tree a little bit unbalanced. If I hit go, you'll see that I'm traversing down, I add 80, and then all of a sudden, oh, it's unbalanced. It's going to go back and do a little bit of a switch or rotation to balance out the tree, to make sure that the levels that we have in a tree are always balanced. And then we have red-black trees as well, which does things a little bit differently. If, let's say, we inserted 9 here, then let's say we insert 10, and then finally let's insert 11. You'll notice that, oh, it's not balanced. We need to balance it out. And once again, automatically make sure that our tree does get balanced with something called red-black tree. As you can see, the nodes are red and black here, and that's something that we use to keep track of when we need to rebalance. I'll leave resources for you if you want to learn more about them. Just keep in mind that these two are usually the most popular for balancing binary search trees, and in interviews, you won't have to implement them. You just need to be able to talk about them and why they are useful, something that we should know by now. I'll see you in the next one. Bye-bye. Welcome back. We've talked about binary trees, binary search trees, and then we learned about how to balance those trees and some of the time complexities involved with a BST. And I want to talk to you about two other common type of trees. One is a heap and the other one is a trie or tree. In this video, let's get talking about heap. Now, when it comes to heap, we're most likely going to talk about binary heaps. Just like we had with binary trees, that means there's only going to be two children to a node. Now, why are these useful and how are they different from binary trees? Let's go have a look. A binary tree, every child belongs to a parent node that has a greater priority or value. If you look over here, every child, that is 72 and 33, is lower than 101. 72 is higher than 2 and 45, and 33 is higher than 5 and 1. This is actually called a max heap. There's also something called a min heap, which is the exact opposite, where the root node is the smallest. Now, this value can be anything you want. It can be a person's name, it can be a number, it can really be anything because it's a node. But as you can see, all we're dealing with is that in a binary heap, every node on the top level has a greater value than every node on the next level down. And a heap can be used in any algorithm where ordering is important. And as we're going to discuss, it's commonly used when it comes to priority queues. Now, with arrays, we had random access. It allowed us to randomly access any element within them using an index. In a linked list, we can change things dynamically, unlike an array, but finding something within them is O of n, linear time, because we had to go through the linked list. Heaps are a little bit different. You can't do O of 1 random access like we did with arrays or hash tables. As we know about trees, we have to do some sort of traversals. Now, compared to a binary search tree, we see that, well, lookup is O of n. It's not O of log n because it's less ordered than a binary search tree, right? A binary search tree actually had meaning between left and right child. The left was always less than the right. In a binary heap, that doesn't matter. Left and right can be any value as long as it's less than the top value. So if we're looking for, let's say, 1, we have to check the parent node. Then we have to check because 101 or because 1 is less than 101, we have to check both nodes underneath it. And then because 1 is less than 72 and 33, we have to once again check every single node. And looking for 1 becomes O of log n. So it pretty much turned into searching through a linked list or iterating through an array. So why would we ever want to use a binary heap? Well, it turns out that binary heaps are really, really great at doing comparative operations. Just like saying, I want people that have a value over 33. Because in that case, we can just grab these items quite easily instead of going all the way down through the nodes. Heaps are actually used a lot in data storage, priority queues, sorting algorithms. So let's have a look at how a binary heap is implemented visually. We have a binary heap here using Visual Go. And if we wanted to add, let's say insert 26, we hit go. All right, that was really fast. But what if we wanted to insert, let's say, 51? If I insert 51, I had to do a bit of a switch. You see, heaps add value on the tree in order from left to right, and then bubbles up if it's not in the same order or the priority order that it wants, kind of like we did here. So if I add, let's say, 70, or you know what, let's add 100. What do you think will happen? Well, if I hit go, you'll see I add 100 and then it bubbles up. So as you can see, inserts, although it looks fast, can still take log n. And this is the same case with deletes as well. It's O of log n. Now, in order to truly understand why we need something like a binary heap, why they're so useful, how they're different from binary search tree, we need to talk about priority queues. So let's talk about priority queues. Welcome back. I wanted to add a quick gotcha when it comes to heaps. That is, when you hear memory heaps, that's not the same as the heap data structure. You might have heard of memory heaps in something like a JavaScript runtime engine, where we have a stack and a heap, the two locations where we are able to keep memory. Now, this heap you can think of as free storage. It is a region in our memory where we can store arbitrary data. Languages like C also have this heap. Now, the naming is just coincidental, and heap has no real relationship with the data structure that is named heap. Keep that in mind. Heap is simply a heap of memory if you're talking about a language runtime, for example, versus a heap data structure, which is what we're talking about now. I wanted to clarify that for you because when I was learning about heaps, for some reason I always thought they were the same thing, but they're not. Just throwing it out there. I'll see you in the next video. Bye-bye. Now, we learned about binary heaps. And we mentioned that unlike a binary search tree, there's no order from left to right. This 33 and 77, we can swap them and it'll still be a binary heap. The beauty of binary heaps is that they take up the least amount of space possible because it's always left to right insertion, as we just saw. So there's no concept of an unbalanced binary heap. We don't have to rebalance it like a binary search tree. Because of this, because they do left to right insertion, as we saw in the previous video, they preserve this order of insertion, which is pretty amazing, right? And you can actually implement binary heaps using arrays versus what we did before with binary search trees where we used nodes. So the only guarantee that binary heap gives us is what I mentioned. The parent is always greater than the children. Now, besides being memory efficient and just compact because it's always a complete binary tree, binary heaps are really, really useful for things such as priority queues. And you might be asking yourself, priority queue, didn't we just learn about queues and isn't that the same data structure? Well, no. Because with queues, we just assumed that it was first in, first up. You were the first person in line, you should get to go first into the roller coaster or the movies. Priority queue is something different. It is a type of data where each element has a priority. And elements with a higher priority are served before elements with lower priorities. You can think of this as a club. Let's say we have a nightclub that is very, very popular, and there's a long lineup. And we let some people in. Everybody's happy. But then all of a sudden, we have some VIPs that showed up. Well, they pay a lot more money than the other customers, so we're going to let them in first. So now we have a different priority, where even though they arrived later, they get to go in. They have higher priority. Another good example is an emergency room. You want to treat the patients that have the most severe symptoms or conditions, right? Another way to think about it is, let's say we're lining up to get into an airplane. We have the first person coming in, lining up, and then all of a sudden the captain shows up. And because the captain should get on the airplane before a normal passenger, the captain gets now put as priority, as the root node, because the value is higher, or at least in this case, the value is higher than the passenger. So let's say now their passenger comes on. Because we're doing left to right insertion, we put the passenger to the right. So now we know we're going to let the captain go in, then the first passenger, then the second passenger. Next, we have a stewardess that came in. He or she should get to go before the passengers, but not before the captain. Well, in that case, once again, we place the stewardess below the captain, but to the right or to the left of the passenger. And then we have another passenger that comes. We do left to right insertion. We see a right spot down here, so we place them down here. So we see how everything gets balanced, which is nice, but it's also really, really easy for us to now let people into the airplane because we know the order. We go from the top, then left, then right, then left, then right, left, right, and we just keep going, keep going, keep going. We know the priority very easily. I'm sure you see where this might be useful in a lot of situations. To review, we learned what binary search trees are. They're great, but sometimes binary heaps or priority queues are even better. Although searching through a binary heap is a lot slower than a binary search tree, you have an idea of priority because insertion is done in order. So you know who should be first, who should be second, who should be third. And although we might have to bubble up inserts every once in a while if there's somebody that has really high priority, most of the time you get really fast inserts with binary heaps. And as we mentioned, lookups are slow, but you want to use binary heaps when you're just interested in finding the max or finding the minimum if it's a min heap. And a lot of the times in binary heaps and priority queues, you have a method called find max or find min that is O of 1 because you know right away that the top root node is the max or the minimum. So for those operations, it's really, really fast and great. And there you have it. I'll see you in the next video. Bye-bye. Welcome back. We have one last tree that I want to talk about, and that is a trie or a tree. Pronunciation here varies on who you ask, but let's have a look at what it is. A trie is a specialized tree used in searching, most often with text, as you can see here. And in most cases, it can outperform binary search trees, hash tables, and most other data structures we've been talking about, depending on the type of search you're doing. And just by looking at this image, you might understand what it does. Tries allow you to know if a word or part of a word exists in a body of text. You see, a trie has usually an empty root node, which is the starting point. And from there, letters are added. You see that it's not a binary tree. It can have multiple children. In this case, it'll most likely have 26 children because there's 26 letters in the alphabet. The power of the trie is when we search for something such as N. If we had this dictionary, we know right away that there's 2 words associated with the word N. Another name for a trie is something called prefix tree. It's a tree-like data structure which proves to be quite efficient in solving these problems specific to strings. You can think of it as autocompletion, right? When you search something on Google, it knows what you might be searching for, or it tries and completes the word for you. And this is what it's used for searching words in a dictionary, providing auto-suggestions on search engines, or even IP routing. If I typed in A, I know immediately that all the children are related to A, and I can print out ARE and then AS. The benefit of this type of data structure is speed and space. What do you think the big O of finding a word in this data structure is? We're not going to go through every single node. Instead, all we need to do is find the length of the word. So the big O of a trie is O of length. That is the length of the word. If I'm looking for the word are, A-R-E, all I do is look for A, then look for R, then look for E. All I'm doing is hitting 3 nodes which are associated with the length of the word. When it comes to space complexity, tries also have a major advantage. Because we use prefixes such as N here is used in different words, and same with A, we don't have to store it multiple times. It's stored in one location and you have children linking to it. Because of these prefixes, you save a lot of space. Because you don't have to store the word not in use, you get to avoid storing that extra N. Although there are a ton of trees, as you saw, and we even talked about a lot of trees, the way they work though, beyond some small logic, such as the differences you saw in binary search trees and binary heaps and priority queues, as long as you understand how to build one from scratch like we did, the small variations are fairly easy to pick up, so that now you have the ability to construct other trees as needed. Remember that Wikipedia page with a ton of tree data structures. They shouldn't look as intimidating to you anymore. At the end of the day, they're just tree structures with a few different rules applied to them. Something that you should easily be able to do with a bit of research now. Let's learn about the last data structure in this course, graphs. Graphs are one of the most useful and most used data structures in computer science when it comes to modeling real life. In short, a graph is simply a set of values that are related in a pairwise fashion. And you can see over here, it looks like a little network. There's connections to different nodes. In a graph, each item is called a node or a vertex. So this is a node, this is a node. Nodes are then connected with edges. So that's an edge, and that's an edge. And as you can imagine, graphs are great data structures to model real-world relationships, representing links. Graphs are ideal for cases where you're working with things that connect to other things, kind of like how the internet works, right? We can use graphs to represent maybe friendships, maybe family trees. We can use graphs to represent networks and the World Wide Web. Or we can use graphs to represent roads, one city to another, and the roads that connect it. As you can imagine, Facebook uses it for their social network, Amazon uses it for their recommendation engines, and Google Maps uses graphs for determining the shortest path to where you want to go. So let me ask you a question. Do you think this is a graph? Well, yeah, obviously, we just went through it. What about this? What about this? And this? And this? What about this one? All right, finally this. Just kidding, a few more this, and this, and this. Yep, they are all graphs. Even this one that kind of looks like a linked list, that's a graph. And as you can see in our mind map, graphs encompass things that we've learned before, such as trees and linked lists. Linked lists are a type of tree. Trees are a type of graph. So in the next couple of videos, let's learn all about graphs. As we saw, there are many types of graphs. But there are certain characteristics that allow us to describe graphs. Let's go over them. One thing that you really want to get yourself familiar with is the idea of directed and undirected graph. These types of graphs are useful for describing traffic flow, for example, of some kind of a system in which movement is not bidirectional. That means, unlike here where I can go back and forth between nodes, I can only go in one direction. A good way to think about undirected graph is to think of as a highway between two cities where you can go back and forth. On the other hand, directed will be a one-way street where you can only go one way. Another way to think about it is Facebook. What kind of graph do you think Facebook has? Well, it has an undirected graph because when I'm connected to a friend, that friend is also connected to me. It's not one way. What about Twitter? Twitter is more directed because if I have my profile, people can follow me and I can follow people, but if somebody follows me, I don't automatically follow them. So Twitter is more directed. Another way to describe graphs is the idea of weighted graphs, unweighted and weighted graphs. And as you can see from the images, values can be applied to various aspects of a graph, not just the nodes. Remember, the nodes can carry any type of information, but with graphs, you can also have information in the edges, in the connections. Maybe you're going on a trip and trying to figure out the most efficient way to visit sites that interest you. Well, in that case, Google Maps would use a weighted graph to decide what is the shortest path for you to get there. And these sort of graphs are used a lot in calculating optimal paths, the fastest way to get to, let's say, 1 to 6. Lastly, another way to describe a graph is cyclic or acyclic. When you have vertices connected in a circular fashion, it's called a cycle, when you can go from one node to another, and then back to that original node, versus acyclic, where you can't do that. And cyclic graphs are really common in especially weighted graphs, such as Google Maps, because most of the time there is a way to get back. So now that we understand a few ways to describe graphs, let me show you my favorite graph of all time. This is my favorite graph. It's by the Opti project and it is a partial map of the internet. If you look here, you see that we have IP addresses connecting to IP addresses, and these are all nodes connected to create the internet. Pretty spectacular, right? That is the best example of a graph. So now that we understand, or at least have a basic understanding of graphs, let's do a nice fun exercise. Welcome back. We have our best friend, Visual Go. And once again, they have a great diagram for us to play with. Now, I'm going to give you 4 different graphs, and you're going to have to tell me what type of graph it is based on what we've learned so far. Whether it's weighted, cyclic, undirected, directed. So let's start off with this one. What do you think this one is before I show you the answer? Ready? All right. Well, this is an undirected, there's no arrows, unweighted graph. And you can see that it's also cyclic because you can go 0, 1, 2, and back to 0. What about the next one? What type of graph is this? Well, this is an undirected, weighted graph. That's also cyclic. So you can see that we have weights on the edges here. There's no arrows. We can go anywhere we want, back and forth. And we can also make cycles. What about this one? This is a directed graph, but unweighted. And yes, even 6 and 7 are a graph. But we see here that it's not cyclic, it's acyclic, because there's no way for me to go back. Let's say 0 to 1, I can't go back to 0. All right, last one. What about this one? This is a directed, weighted graph. We have the weights, it has direction, and when it comes to cyclic, nope, there are no cycles, so it's acyclic. All right, the final challenge. What type of graph is this? Ready for the answer? This is a directed, acyclic graph. There's no cycles, it's directed, and it's a graph. And this directed acyclic graph is quite common and called DAG. And actually, a project like IOTA, which is a pretty popular blockchain project, uses this and uses fancy words like directed acyclic graph. But at the end of the day, that's not that impressive anymore, right? We know what that is. Just simply a graph that goes in one direction. I think it's time for us to learn how to build our own graph. I'll see you in the next one. Bye-bye. Welcome back. Let's learn how to build our own graph. Graphs, when you look at them, look very intimidating. But here's the thing. We've actually learned the tools necessary to build graphs, because graphs are built on top of other data structures. Remember this diagram of the directed acyclic graph? Well, many of the data structures that we've been playing with up until now can create something like this, using trees and linked lists. I mean, it looks pretty similar, right? You have a node with children and different pointers. Using that knowledge, let's talk about how to start thinking about graphs, or at least how to think about building them. There's 3 ways that you can think about it. The first is called an edge list. And I have an example for you that we can use to build something like this. Let's say we want to build this graph. How would we go about doing this? With an edge list, we can say const graph equals to something like this. Now let's see what I did here. I have an array, and within this array I have 1, 2, 3, 4 items that itself they are arrays. But if we look at the graph, the array simply states the connections. That is, we have 0 and 2 as the first item in the array. We have 2 and 3 as the second array inside of the array. And then 2 and 1 and 1 and 3. An edge list simply shows the connection, that 0 is connected to 2 and 2 is connected to 0. 2 is connected to 3, 3 is connected to 2, 2 to 1, 1 to 3, so on and so forth. Quite simple. There's another way called adjacency or adjacent list. And in this case, we can create a graph where the index is the node and the value is the node's neighbors. What do I mean by that? Well, in here, we can use arrays, we can use objects, we can use linked lists. But let's say that in the index of 0, the first item, 0 is connected to 2. The index of 1, that is node 1, is connected to 2 and 3. Index of 2 is connected to 0, 1, and 3. And then finally, index of 3, or node 3, is connected to 1 and 2. And you can also do the above with an object, where it might even be clearer. And if a node value is something other than a number, you can actually give it a value, so a key and a value. And this is extremely useful with object if you have, like I said, not a sequential number as we do in this example. And when we implement our own graph, we're going to use an adjacent list using an object, and you'll see what I mean. Finally, I want to show you the last method to represent graphs. It's called adjacent matrix. And an adjacent matrix is going to look something like this. This matrix is simply going to have zeros and ones indicating whether the node X has a connection to node Y. 0 means no, 1 means yes. And if you have a weighted graph, you can actually add weights here instead of 1 and 0, so they can actually be numbers. I'm not going to type this out because I'm going to bore you to death, but here is the same representation that we've done with edge list and adjacent list, this time with adjacent matrix. What does it mean? Well, index of 0 has connection with 0, 1, 2. So 0 is connected to 2. Then node 1 is connected to 2 and 3. Node 2 is connected to 0, 1, and 3. And you can see how it's very similar to here. And node 4 is connected to 1 and 2, just like over here. And once again, instead of arrays, you can use objects here and actually give it a key and a value. So that this, if it was an object, would be 0, 1, 2, and 3. And if we go to Visual Go, you'll actually see that they have these 3 ways to describe graphs. The adjacency matrix, and because it's weighted, you see that there's numbers here instead of 0 and 1. We have the adjacency list, where it looks like here they have a hash table with the values, and also an edge list with an extra property of the weights because this is a weighted graph. And you can see the weights as well in the adjacency list. But we've just taken a look at a lot of numbers. I think it's time for us to build our own graph to finalize our understanding. I'll see you in the next one. Bye-bye. Welcome back. It's time to create our own graph. And I've created the template here for you. You can also create your own if you want, but I've only included things that let you focus on the critical part. We have a graph class and a few methods that we're going to have to add. Now, we're going to recreate a graph right here. A undirected, unweighted graph like this using adjacency list. And for the adjacency list, we're going to use a hash table. So how are we going to go about doing this? Well, I have a few things that I've set up for you. One is that in the constructor, we have simply number of nodes that we'll have to increment just to keep track of how many nodes or vertices we have in our graph. And also, I've created the adjacent list for you, which is an object. And as you do this exercise, you're going to realize why we want to use, let's say, an object versus an array. Because if we start removing things from the graph or placing things in the graph that's out of order, it's going to cost us a lot. Remember, arrays on shifting and shifting is expensive. With objects, we can quickly find items and see their connections. So that ideally, in this case where we have 3, or let's look at 0, in this case we'll have 0 is going to be connected to an array of its connections, which will be 1 and 2. So it'll have something like this. Your task is to add a new method called addVertex that adds a new node or a vertex. The naming here kind of goes back and forth. And then also addEdge. That is to add a connection between node 1 and node 2. And keeping in mind that this is undirected, if I could spell. It's an undirected graph. So both node 1 and node 2 point to each other. And if you scroll down here, I've actually created the calls, the function calls that we're going to do. We've created the graph, and then I'm creating 0 all the way through 6, just like we have on the graph here. And then we're going to add the edges, that is the connection between everything. 1 is connected to 0, 0 is connected to 2, 6 is connected to 5. Simply just saying this. I'm never repeating myself. That means I'm never saying add 3 and 1 and then saying add edge 1 and 3. I only say this once, and that's the key. And also the order doesn't matter. If I switch the order of these calls around, it should still give me this graph. All right, I know you're excited to get coding, but the final thing, and this is only optional, if you want to do this yourself, you can also code it yourself, but it's not really that important for this video. I've created a small helper function called showConnections. And you can look through this function if you want. It's not really important to the core of the course, but I've made this so you can check your work. Because if I run this using, at the end, my graph, show connections, it's going to print out the answer like this. And it's going to show all the connections of the graphs that you've created. And this way, you can check that these connections, that is, node 4 is connected to 3, 2, and 5. Node 4 is connected to 3, 2, and 5, just like we have here. All right, that's enough for me. Good luck on this exercise, and I'll see you in the solution video. Bye-bye. Welcome back. How did you do in this exercise? Were you successful? Were you not? Here's the thing. This is actually extremely simple, but it looks overly complex. And that's a general trend with graphs. They look really, really intimidating at first and really hard to really think about them in your mind. But once you put things down, understand things, maybe draw things out, they're actually quite simple, and they're very similar to what we've learned up until now. Everything we've learned about hash tables, arrays, trees, linked lists are all part of graphs, and graphs simply use those data structures. For those of you that weren't able to solve this problem, it might be because you were a little bit intimidated as to the task at hand. But let me show you how simple this can be. In order to add a vertex to our adjacency list, all we need to do is to simply say this.add, or this adjacency list is going to have node. So we're adding the key into this object of the node that we want to add, and that's going to equal an empty array. Because when we enter a new node, it's not going to have any connections initially. We want to add the edges afterwards. And then finally, we want to increase the number of nodes by 1. Now we have one more. That's it. We've just created our nodes. Look at that. We have 0 all the way through 6, and they are in our graph. Unfortunately, none of them connect to anything. We've just created the nodes, but none of the edges. So let's go ahead and do that. With the edges, because this is an undirected graph, what we'll have to do is say this dot adjacent list is going to say node 1, that is the first node that we're giving. And the node 1 is going to push. Remember, this is an object, so we're getting the key. So that is, let's say this is node 0. It's going to push to the array of connections that node 0 has and say that it's going to be connected to node 2. And because this is undirected, that means we have to do it the other way around as well. So we simply copy this. Let's make this a little bit bigger so you can see. And we simply reverse things. So node 2 is also connected to node 1. If I press run here, look at that. We have our graph. How simple was that? That wasn't bad, right? And I mean, we could create this in a linked list if we wanted to, but the concept is the same. If we look at 0, that is connected to 1 and 2, we can confirm that 0 is connected to 1 and 2. If we look at 1, 3, 2, 0, 1 is connected to 3, 2, 0. And let's check maybe 5, which is connected to 4, 6. 5 is connected to 4, 6. And there it is. We've just created our very first graph. When it comes to interviews, graphs aren't as big of a topic as the other data structures, mostly because they take a bit of time. And questions regarding graphs can be overly complex. That doesn't mean that you won't see them, but they are rare. However, by knowing the basic fundamentals, what types of graphs we have, and how you might create graphs, how you might want to hold data in graphs, such as adjacency matrix, adjacency list, and edge list. You already show that you have the ability to understand graphs, which is an advanced concept. Now, because graph questions aren't that big a part of interviews, we won't be spending any more coding time on it. But also keep in mind that we have a section coming up on algorithms where we're going to dive a little bit deeper into things such as breadth first search and depth first search, which can be applied both to graphs and trees. So if you feel like you can still learn a bit about graphs, don't worry, we're still getting there. But for now, congratulations on creating your first graph. I'll see you in the next video. Bye-bye. Welcome back. What are the pros and cons of graphs? Well, when it comes to performance and big O, it gets a little bit complicated because there are so many different types of graphs. You can think of graphs as really useful when it comes to relationships. They're simply indispensable because some data just needs to be in a graph form. There's no other way around it. And there are algorithms around graphs, such as the ones that we're going to be talking about in the algorithms section, that allows us to perform operations, such as finding the shortest path or traversing a graph. But when it comes to graphs, because they can get complicated, scaling is pretty hard. You need a big company, or at least a lot of resources and engineering power to make sure that you build graph data structures that scale well. But luckily for us, you usually will never have to implement your own graph in production, or at least for 99% of the population. There are tools like Neo4j, which is a popular database that allows you to build really fast graph databases. And most of the time, you'll use tools like this to build complex structures to contain our data. Congratulations! We've now covered another part of our data structure mind map. That is graphs. We learned about cyclic, acyclic, weighted, unweighted, directed or undirected. We were also able to build our own graph. Now there's still a few things left that I see up there and perhaps over here, which we're going to get into in the algorithm section. But for now, take a break, drink some coffee or tea, and I'll see you in the next video. Bye-bye. There we have it, our end to the data structures section. Was it as scary as you initially thought? Hopefully, by the end of this section, if you've watched all the videos and done all the exercises, you feel a lot more comfortable. You can use the tools that you've learned to be a better engineer and make better decisions. Hopefully, you don't look as scared as this emoji did at the beginning of this section. And we've learned that these data structures, at the end of the day, are our friends. And by the way, I'm really proud of this slide. I spent way too long creating this little thing that I have. I have Mr. Hash Table here. That's Mrs. Array. That's the little linked list. That's Mr. Q, Mrs. Stacks, scary looking graph, and of course, Professor Tree. Anyway, I hope you're no longer intimidated by these subjects, because all around us, when we look at technology, they're all built by data structures. We hold information in data structures. No matter how many data structures there are and there will be in the future, most of the building blocks are right here. You see, something like blockchain that has become really popular in recent years are just data structures that we've learned about. It has some aspects of linked lists. It has some hashing that it does, which we know about. And it also uses some trie data structure and trees. Having the fundamentals that you have now, one day, maybe you'll build your own data structure. I'll see you in the next one. Bye-bye. There we have it. We've just completed our data structure section. We went through all these data structures, even some sub-data structures. And you know what? We've completed a lot of this mind map. We've talked about arrays. We've talked about stacks and queues. We've talked about hash tables, linked lists, trees, and all the types of trees that we have. We even talked about graphs. All these little boxes that are data structures, we now have an understanding of what they are and how they are used. But there's a few other pieces of this mind map that we need to go through, and that is algorithms. And you'll see algorithms depicted here in rocket ships. Our last piece of the puzzle. But you might still have a few questions that haven't been answered. And there are some things that I left out because they apply more to algorithms. When it comes to sorting, we're going to use arrays and trees. When it comes to dynamic programming, we're going to be talking about hash tables. When we talk about breadth first search and depth first search, that's used in graphs and trees. Recursion, well, that comes up a lot in trees as well. So now that we have our fundamentals for data structures, we're now ready to talk about these algorithms that come up a lot in interviews. Because we now understand how data structures work, we're able to talk about algorithms intelligently and understand them at a fundamental level. I'll see you in the algorithm section. Bye-bye.